Good morning. The technical done. Welcome back to the third day of this exciting meeting. Over the past 2 days, we have many exciting lectures, works, and public lectures. Public lecture. So before starting, some words from Professor Rufini.
Yes, today lecture is serious as usual. They are very important and people are following from here and from far away. I just received a notice from Sampio Kim, who is in Australia and is following the activities. And today is very, very important everything, but in particular the first two meetings, because they are clarifying some of the key issue about the BDHN model and lead finally, I don't know if we will present this, but they have led finally to the first identification in a GRB of a baryonic black hole form of baryons of 2.35 solar masses, which grows all the way to we are compounding this black hole all the way to reach 2.65 solar masses. Therefore, the first lecture will be on the BDHN model. Especially attention will be given to the synchrotron emission, and then followed by a second lecture, which is very, very new, on the possibility to have not only one supernova triggering the GRB, but a very powerful supernova triggering a second supernova and leading to the first time to a pulsar from a GRB. This is the high point of today, of this morning. There will be other high points that I will stress during the meeting.
Okay, thank you. So since we are short in time, let's start with the first speaker, Yerlan Aymuratov from Fesenkov Astrophysical Institute, Kazakhstan. He will be talking about GRB supernova association within the binary-driven hypernova model developed in ICRANet. Please go ahead.
Okay, thank you. Thank you for inviting me. So hello everyone. Today we're going to talk about GRB supernova association. It's the subclass of well-known GRBs. And the motivation comes from the association, of course, which is for long-standing belief that it is long gamma-ray burst associated with the type 1c supernovae and the classical collapsar model, which stand for decades, struggles to explain few cases and causing the vast diversity in GRB energies versus the homogeneity of the association of the supernova. We will show this later. And we will revisit GRB supernova within a binary-driven hypernova model and support this with some statistics and some published results and also ongoing results. So, as I told already, the GRBs are extremely diverse. So the total energy is varying more than 6 orders of magnitude, actually, from 10 to the 48 to more than 10 to the 54. So there are ultra long, very energetic bursts and low luminous, closely located GRBs also. But despite that, the association of the supernova coming like somewhat 30 years ago discovered, they show more or less single and homogeneous energy release and light curve similar to each other. So in this talk, we will overview and recap the sample and analysis we have done. We show some statistical findings and interpretation within the model. And we will briefly discuss what happened after. This is the main publication of 23 we did, and the new results, new observations, and how it questions this model and other models as well. So with all the conclusion and future outlook. To start with the optical emission of the GRB, which is also present as a counterpart and as an afterglow, late afterglow. It was seen like the structure, the peaking structure with a jet break and lowering the power low and the bumps happening in the late time. So all these features should have been related to the physics and to the mechanisms happening on site. So, but to start with, we do the phenomenology of this supernova association, how it started. So there are two methods exist to detect the supernovae while doing the observations. The first is photometric identification, and it strongly relates to the optical light curve behavior. It is easier to obtain since many telescopes is working in photometry regime. And unfortunately, sometimes it is the only observations we have, I mean the photometry. So you can see here's that optical, here's the X-ray, and for different cases of GRBs, we have this light curve happening with the beginning and fading upon the time. So having the peak somehow related with X-ray and other counterparts. And the supernova association usually comes with the optical bump and the late time at 10 to the 6 days. So it's roughly 10 to 15 days in observer frame. So this brightening gives its contribution to the overall light curve in optical, and it is interpreted as the nickel decay, which is propagating over the time in the ejecta of the supernovae. This was known well before. The model developed by David Arnett, and it is common and everyone uses that. So observationally, there are many bumps happening in the late time for the optical counterpart. There are many, but relatively to the total number of GRBs, there are very much less, because not every GRB has its own optical counterpart observed. But when we have that, we can see the bump. So another method is the spectroscopic identification. When you trigger big telescopes and you have observed the spectrum of the absorption emission lines of the spectrum, it is harder to obtain since it is involved dealing with the big telescopes, which is fully duty loaded. But the observational features present, they have signs of typical emission and absorption lines of special iron and other elements. So there are much less spectroscopically identified GRBs. Okay, so our goal was to sample this subpopulation and do the analysis to find some correlations we have, and then do the interpretation on the work. Okay, so we compiled the sample. I'll show in the next slide. Then select the well-studied objects and did the methodology for standard photometric magnitudes, converting to the bolometric flux and dealing with the energies. All the standard procedures for key correction and so on. Okay, so the sampling itself, it was up to the 2023, now which is 10 more, I guess. So it is around 60 associations, 30 happening before Fermi telescope and 30 plus happening after the launch of the Fermi telescope. Okay, the cross correlation comes with many, many sources, catalogs, and GCN circulars in the literature, of course, because at the time, there was sparse pieces of the observation which should unite. It's quite kind of work. We should have done that. And 60 plus objects coming for association goes with that optical and spectroscopic. So we need to deal with it. Most of them, not most of them, practically 95% of them happening within the redshift 1 before 1. So it is close by located GRBs, relatively close by. So this is the numbers. Then we did the bolometric light curve reconstruction according to the work by Lyman, 2016, 2014, to unite this bump structure and see, shifting to the phase 0 to have it in the peak. Similar to another work where we noticed that this bolometric peak magnitude and isotropic energy of the GRB shows some strange features. We use that for our sample indeed the following correlations. One of the correlations we obtained is related to the isotropic energy of the GRB itself, the prompt emission, versus the peaking time of the supernova in the rest frame. Okay. The similar one for the same sample, we did isotropic energy versus the peaking luminosity of the supernovae, and it shows the alignment. So, and similar for the redshift, there is independence of the redshift of the luminosity peaking time of the supernovae. And we can draw some preliminary conclusion that the peaking time clusters around 13.8 days in the rest frame. The peaking bolometric light curve is doing somewhat 9 to 10 to the 42, much less than the isotropic energy of the GRB, independent of the energetics. And the energetics vary 6 orders of magnitude more or less, but the peaking times still stay at the same level. And we draw as ansatz that it could be an entirely decoupled supernovae from the GRB prompt emission. And it is so, since the community says that if there is a collapsal model, then there is a ejecta happening, and it is independently evolving in time. But there should be a subtle that the more energetic GRB you have, then the burst happens, and the ejecta should be affected by this energy of the GRB itself from the beginning. So the more energy you have, then the more energy you have in the ejecta, and it is affected by. Finally, it should affect the luminosity of the peaking of the supernovae, but it doesn't seem so, not in every case at least. So this independence points us to the possible binary nature of the progenitor. So the single star can explain some cases, not all of them. So, and for the cases we cannot explain with a single collapsal model, we use binary, which is also dealing good with the other cases. So we point to the two physically independent components of the mechanisms, which is generally true. So, and the binary dream hypernode paradigm comes with the neutron star surrounding the massive, at least 10 solar mass CO core, which is collapsing and expanding. And the expanding ejecta comes to accrete to the neutron star and creates the black hole, and there the GRB happens, while the rest of the ejecta is evolving and thermalizing, giving that nickel decay at 10 to 15 days time. Okay, so this is shortly saying, so there are two main phases, but we divided this model into the 7 episodes where the typical GRB is evolving in time. And we can see and we can track it through the spikes and the counterparts activity. Okay. So as a result, we say that the supernova is powered by CO core collapse for sure. And the GRB itself is powered by the creation of the black hole out of the neutron star companion. So this model works well. And we did case study for exceptional GRBs. We selected, for example, 1901-14C, which is one of the first, I guess it's first associated with the TeV emission of the magic. So you can see it, you should see it somewhere here, okay? So the question again stands how you can create the TeV photon at the same time create the standard, more or less standard supernova emission. And that binary model gives some answers to these questions. So another is 1908-29A, these irregular structures for the X-ray, also giving that TeV emission by Hess. And here's the later, bolometric optical peak of the supernovae. And here's the early case of 060218, which is categorized as BDHN2 model. So there's a slight change in the model, which gives a slightly different scenarios. Okay, so what happened after this correlations we did and published in the work? James Webb Space Telescope came into operation, big surveys came into the operation, and they are, breaking all paradigms as well for the association of the GRB supernovae. One of the famous examples is the boat, brightest of all the time supernovae, which stands, on the outskirts of the energy, giving the highest, one of the highest possible energies we observe, and with that very, very high fluences, and even the optical emission coming to contribute. So there is a connection. We can see there is a connection between the prompt emission, which give rise of the prompt emission of the gamma ray, then the optical emission, which is coming afterwards. Of course, there is a connection, but this connection should be slightly modified, and that later association of the supernovae 22XIW also shows that it is bright enough, but it is nearly identical to the first identified GRB of the 1998 BW, okay? Which also gives some questions, raises some questions to interpret. We're still working on that model. And there is also the second superluminous supernova occurred within the association of the supernova. So there's also the bright, and it is interpreted as a magnetary activity. There's also some struggles, and we use that binary-driven model to align the dynamics of the new neutron star, which is happening after the collapse of the massive star. There's an outcome of the new neutron star, and it gives some activity which can goodly interpret the physical origin of the emission we see. So in the classical supernovae studies, and not related to the GRBs, for the long stand there was a problem of progenitor, which was not seen before. So the James Webb recently helped to discover that high mass giant star, red supergiant, which comes to be a superluminous supernova, and helping its sensitivity, it can go deep and dive into the dust of in the infrared range of the spectrum, and finally saw the giant star. So it also supports our model, and there is like a massive CO core and with possible binary neutron star surrounding it. Okay, so here's the supernova 25 PHT, which is the massive star, which is hidden in dust shells. Okay. For the future outlook, we see that new telescopes and surveys will, especially surveys, will give us hundreds to thousands supernovae. And part of them will for sure be associated with the GRB. And, you know, the more diverse we have, the more data we have in hand, then it will be diversity also in the model struggling. So this binary model works well till the moment, but for super energetic cases, we introduced that there should be a second supernova triggering the burst, which is the talk after me by Professor Miturabi, next talk. So there is a tendency to unify that all the cases in one into single model with slight diverse cases of scenario, but it seems to be quite hard at the time. So this binary model becomes triple model, and that collapsar, you know, with the leftover of the new neutron star, or nothing left over after that. So it gives this diversity in scenarios and can, you know, interpret some of the unique cases. Okay, so thank you.
Thank you. We still have some room for questions.
It's more a comment. So for GRBs, because the emission is collimated, so we don't. So what we measure is the isotropic equivalent luminous energy, is not the total energetics. So for example, both GRB very bright, but the open angle is very narrow. So in terms of total, it may not be that substantial. So I would not really expect that the GRB and isotropic energetics to some scale with the supernova. Supernova is like more isotropic, non-relativistic component. And the Einstein probe recently detected a lot even softer trend and low energetic transients. Their associated supernova are quite similar to the GRBs. And there's also a viewing angle effect. For example, if the jet is structured with the same jet, if you look down at the jet axis, it's very energetic. If you are looking at a large angle, then it's relatively moderate, but they're more or less the same thing. So yeah. I will not jump in to immediately say that there's a crisis or something.
No, of course there is no crisis. I mean, that collimated jets and isotropic estimated energies, they vary within maximum 3 orders of magnitude. So even if you have 10 to the 54, it goes down. If it is very highly collimated, it goes down to 10 to the 51. So it's still very high. If you compare with other GRBs. And of course, there are struggles with that, you know, since there's no more long type and short type, there's type 1 and type 2. So we deal with that collapsars with the short GRB, with the short duration GRBs, and we deal with the binary neutron star giving the long GRBs. So there is, you know, a lot of divergence these days. So it needs a bit of interpretation more. Okay.
I think the most interesting part of this family of sources is the fact that there is this very clear value of the nickel decay and at 10 to the 6th second is typical of all these core collapse. And it's remarkably, maybe you can show the diagram here, where independently of the GRB, the occurrence of the supernova or of the at the 10 to the 6th second, show the other diagram, is extremely clear and impressive. And we are discussing right now on this aspect, which is present in all these sources, which are, can I have the other slides that you show? Yes, in all these slides, which we have examined, there is this difference between the BDHN1, the BDHN2, and the BDHN3. I think this we understand is the fact of the presence of a binary neutron star companion in the case of BDHN1, which is not present in the other cases. And the correlation of this binary is very clear of neutron star, because in all these systems which are more energetic, the 10 to the 43, 10 to the 45, you see also the JEV emission. And the JEV emission is a sign that there was a neutron star companion, which by accretion, it creates a black hole. And you see the JEV emission. Therefore, this is quite clear because it proves both the BDHN, the core of the massive star initial, and the binary neutron star companion, which manifest in the JEV emission. And the situation now is somewhat, and always there is this nickel present. This is the summary of this beautiful work done by Muratov. The presence of a typical iron nickel decay at 10 to the 6th second, and the presence of a companion neutron star in the case of progenitor, due to the fact that in the more massive you have the neutron star companion, and by accretion you have the black hole, and you see that. Therefore, this is a self-consistent, very self-consistent treatment, and we are happy about that. But at the same time, this does not appear to be the case for the most energetic GRB. Namely, this is okay for GRB of the order of energy up to between 10 to the 52 and marginally 10 to the 54, but it's clear that once you go over that limit, like in the case of GRB 220101, the model is not sufficient. And in particular, the most striking aspect for the more massive star, the more massive system, you don't see any longer the nickel decay line. And this is the attempt that is justifying a new approach. We are working very much. We have been working also yesterday in a team on these new systems, with Rueda and with all the other people, and also with the, 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 the work of Yerlan. And we will attempt now to present you, although to us it's very clear, but we are still working on explaining the richness of this system, and we will just give you a test today.
Okay, thank you. Since we are exactly on time,
It's quite revolutionary, this new part. We present something, but we have not, you can be inspired, but refer to us eventually, because has not been submitted yet. Last time.
okay, so before going to the next presenter, these ancient probes are available, the data, publicly.
After 1 year.
Okay.
But
So,
the published ones are there. Just ask legal author.
okay. So he mentioned some new data by ancient probes. I was curious to see them.
Absolutely. We need to share some student of the Einstein probe to collaborate with us, and we could consider in receiving them, because I think absolutely for these sort of sources we are going to speak now, the data from the Einstein probe are essential. For these sources, the GRB 220101, we will just tell you some interesting thing which we feel confident that we can, although has not been published, it cannot be just reproduced without a deeper understanding, which we're going to grant in these days. Okay.
Okay, thank you. Let's start second presentation by Tarimir Torabi from Al-Zahra University and ICRANet. Please go ahead.
Yes. A second pulsar from the a pulsar from the second supernova GRB 220101. This is something like a brand new idea, but we just done a rough estimate of that calculation. And we look at the 220101. This is a very exceptional GRB with isotropic energy about 10 to 54 ergs, which is very bright, and it is leaving Z equal to 4.61, which is far from us. Then it's in high redshift. When we are looking at the high redshift, we not only we are looking on the past, but everything is happening slower, because 1 second on the Earth is 1 second on this GRB is equal to 5 seconds on the Earth. Because of this, we can see the physical process in very early time, and also because of that, this GRB has been seen in a very comprehensive multi-wavelength luminosity. The light curve extended from the high energies. We have the light curve in MEV, and also the optical light curve, which I am working on. And the optical light curve is as a rising part, it goes to a maximum and then decay. That's a very specific feature that we can see in this GRB. here is the Fermi GBM light curve of the 220101. It is 2 overluminosities in the first 10 seconds, and then an extensive and long UPE, the episode 3 here, and then it decays. These 2 overluminosity make a prompt idea that it may be due to the not only one supernova, but there is a second supernova. There is another supernova in this process. The root of this idea is in the simulation that have been done by Ruffini and collaborators about 7 years ago to explore the process underneath the classical PDHN. In the classical PDHN, you have a supernova, a core, a massive core that turned to a supernova and a neutron star companion. After the massive core explodes to the supernova, it shed matter to the neutron star and turn it to a black hole and try to explore all the phenomenon in the GRB by this binary system. That I've taken this slide from Rahim's slide, that the progenitor is a 9 to 10 solar mass core, CO core, and a 2 solar mass neutron star. And after the 10 solar mass explode to supernova, it accrete matter to the neutron star and turn it to a black hole. And this black hole made all of the other process. By the light with the light that we give from the clarification that, the ideas and clarification that yesterday Rahim gives us, that the UPE, you see that this, yes. Oh. No, I should go back. Why it doesn't go back? Oh, yes. In the light that the self-similarity of the UPE, it doesn't need any more to a black hole, because these self-similarities simulate that this self-similarity simulate that the process we are involving are all interpretable by, not by general relativity. We don't need the general relativity. Then we to simulate. Oh. And just what we should do is to take out that neutron star from this simulation and put a smaller mass. It's a core of 1.3 solar mass. And then when this core of 1.3 solar mass, it's like something like a white dwarf. When this white dwarf absorbs matter from the accretion, it turns to a new supernova. This is the second supernova. That this process will make the optical light curve. The optical light curve is starting from a rising part, and then it decays. We assume that all of the optical light curve coming from the new neutron star made by accretion of that white dwarf. Then our system consists of a very huge supernova starting first at early time, and then it accrete matter to the companion, and the companion is a white dwarf that, after absorbing it, like a process like like a process like the supernova type 1a, it explodes as a second supernova. This second supernova then radiate optical light curve. I try to simulate this optical radiation using a collapsing white dwarf which turned to a supernova. I assume that the free fall evolution that give us a radius profile that taken from the free fall, and then using a flux freezing assumption that magnetic field conserve the flux, and then assuming a dipole and quadrupole radiation from the system. And then here is our simulation that show that the luminosity of this optical starting from 10 to the power 33 and goes to 10 to the power 46. And the neutron star take matter from the supernova and speed up to about 80 milliseconds. Here at the top of the red curve, it is 80 milliseconds. And then we add the accretion to this process. After adding the accretion, the neutron star develop alpha 1 radius around it, which the pressure or ram pressure of accretion is equal to magnetic pressure. When in the early time with the ram where the accretion, the magnetic field is weak and the accretion from the supernova is high, this alpha 1 radius is shorter, is smaller than the co-rotation radius. This means that the angular momentum can transfer from the supernova to the neutron star. And the neutron star developed, it spin up to, as it spin up, it develop a stronger magnetic field, and as the magnetic field magnify and amplify, it extend its alpha 1 radius. As the alpha 1 radius extend, it goes and it can be bigger than co-rotation radius, and it stops the accretion, it stops the angular momentum transfer. Then it shows that we have a limited time for absorbing the angular momentum and speeding up of the neutron star. We calculated that this time is about 10 seconds. During the 10 seconds, this accretion can speed up the neutron star to a 1 millisecond pulsar. With this needs an amount of mass about 2% of the solar mass, and the final period of the neutron star is 1 millisecond. This is plots of luminosity, omega, and also the energy and the magnetic field that amplify during this process. Finally, we found that this curve can go up to the maximum of the green observation, which is Swift observation, is a 10 to the power 52, which is equal for a neutron star with a period of 1 millisecond. And this, if we add accretion to this process, we can finally have a very fast 1 millisecond pulsar, and this to interpret this rising part of the light curve. Also, we have done we assume the spin evolution of the new neutron star from 1.3 millisecond to 6 millisecond after 10 to power 6 second after the evolution of the pulsar for longer times. With this scenario, the 7 episodes of the supernova is changed to this. At the first episode, the first explosion happened, and it's collapsed the CO core and make a huge supernova. Then we have the white dwarf collapse, which make the second supernova, and then when we have the accretion, which is finally change make the pulsar a millisecond pulsar. At the final episode, we have an optical afterglow, which made by this pulsar. Yes, and also we have the neutron star spin up at 14 to 21, which the neutron star take matter, absorb the matter from the supernova and speed up to 1 millisecond. I'm done by this.
Okay, thank you. Questions? So, oh, one question there.
Just a short question. Thank you first for the nice presentation. It's just like, so you assume a massive star and a white dwarf. Considering the different evolutionary timescales of these two objects, how do you think this system has been formed?
Yes.
Is it like some kind of capture? Because like a closed system would not produce a white dwarf, as far as I know. So that's it, yeah. Thank you.
Yes, but we call it white dwarf, but it should be, if for the 220101, the GRB is a very early universe. When the age of the universe is about 1 billion years, there is no possible to have a white dwarf at that time, because a white dwarf normally takes 5 to 7. At 4220101, it could be a lower mass core of about 1.3 solar mass. That, yes, but for late GRBs at small z's, you can have such system, because it may be take by capture or maybe or other type of evolution.
Sorry, I didn't fully get how the gamma rays are produced. You have the light curves, the GRB light curve, how each peak of the gamma ray emission was produced.
Can you show the slides?
Yeah, so 1, 2, 3. So those 3 episodes, how the gamma ray emission was produced.
Yes, you want to answer this, because that was your idea.
Yes.
Moment.
Well, I think the idea is quite new, and I would like to answer, clarify. The greatest change of paradigm came from a lecture given by Michel Mayor a few weeks ago. I mean, all this was done before, the thing you are seeing. But the understanding of the philosophy, of the model and justification came from this fundamental presentation of Michel Mayor about the formation of exoplanet. And the idea in this Mayor idea is that contrary to what we have been thinking, always taking the work of genes and fast rotating object and evolving in pear shape and all this work, Mayor introduced a different point of view that that you could have an old idea due to oil and to we are writing the history of this, that you have a very massive object non-rotating, and around this object you have very fast rotating additional object. Well, we need this approach to understand the BDHN. And in particular, coming to the question which was just asked before, is looking at the telephone. Yes. The idea is that you have a very massive object characterizing the PDHN, but you have around fast rotating object. You don't need to, at the moment, captured. And you could have many of such objects. Like in the planetary system, you have many planets, and so many of them have even gone away. This is the latest understanding. We are adopting this philosophy, namely that you have a very massive CO core of 10 solar mass, which for some reason had an earlier phase in which objects were captured around this system. And one of them is a neutron star in very fast rotating, giving the BDHN, but also the possibility that among others you have another neutron star, a new neutron star, but even a white dwarf. This is the key idea. And we are still working on this aspect. But for this reason, what we found, we have shown, is that if there is around this object in the moment of explosion, a white dwarf-like system, which gravitationally collapses, then we have recreated, this is the beauty of the work done by Taghi. Where is Taghi? Oh, yes. The beauty of the work done by Taghi in these curves that he has shown. If you have a white dwarf in this condition, it can gravitationally collapse and at 14.6 seconds reach a millisecond pulsar. Now, I don't want to bother you and to prove all the details. Yes, you can look at the diagram. But let me tell you what for me is exceptional. That that we have that this process from you have the first supernova, which we call the OB supernova after Baba, Omi Baba, which generate the UPE, which you have heard on Monday and following. You have this first supernova, OB supernova, which is by far the most powerful. But in the field of this OB supernova, there is also a white dwarf around, which accretes and from a white dwarf form a neutron star, which is pinned up after 14.6 seconds and reach a millisecond pulsar. This is the result that he has shown. This is the key result of TAGI. And this 14.6 seconds, now I want to tell to the specialist of GRB, this 14.2 of appearance of a very fast rotating neutron star pulsar, which we have modeled, exists in all the family of GRB, like 220101. Namely, you take all of them, and we will develop this. But in all of them, there is a signature at 14.6 seconds. There is always the beginning of a pulsar emission, which very, very slowly decreases and finally is observed as a pulsar. Only in the GRB of this family. And the signature is this process occurring at 14.6 seconds. We will have to do a lot of writing to make you aware of all this. Everything is done, but it's a question to write and explain. But the signature, I tell you already, there is a very powerful supernova to start with, but then there is a second supernova, which independently of all the detail, after 14.6 seconds, in all of them appears. This is a very, very, very strong signal. Yes.
They are all,
Excuse me.
supernova in the same distance.
Excuse me.
Okay. You said that the signal is 14 seconds after something. You said already. The signal is 14 seconds
After the first supernova.
Yeah. But it may mean that all of them, supernova you're referring to, are in the same distance.
No.
Well, if not, how do we know that this 14 second, because we are getting this information now only. In a cosmic sense, our existence is zero. So they must be, well, all of these signals are coming in just today.
Well, it takes quite a lot of explanation. We of course, one of the key point is you have to define a frame for the gamma ray burst. And once you define the frame of in the local frame of the GRB, in that local frame, you compute the 14.6 seconds. But you have to do can I see can I see the general picture of the, yes. But as Binzang was mentioning, there are a lot of peaks in the MEV, in the JEV, and so forth. And there is a lot of physics to be done and to do properly done. But if you put yourself in the frame of the GRB, this is necessary. It's up to you how to do it, but we know how to do it, okay? Then, after 14.6 seconds, there is always this millisecond pulsar appearing. And it's very, 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 it's maybe I think the most beautiful result, which together with the evidence of the first black hole of 2.3 solar mass and so forth, which comes just after this 14.6 second, okay, down here you have the black hole, the JEV radiation, but this characteristic of 14.6 second here is the most distinguished signature, because at the end is a pulsar, like in the crab. In other words, you will hear the last lecture, when you listen, please, the last lecture tomorrow by Constantino Sigismondi, where we propose that the initial supernova of the crab, there we propose was similar to a GRB 190114C, okay? But now we have something more, namely we prove that all what we wrote in that paper is okay. But what we prove today with this source is that GRB in the beginning was really a system like this with the GRB 220101, because there has been a pulsar coming out of the Crab Nebula, and this fits perfectly this verification of the 14.2 second, if you do things in the rest frame and so forth. Therefore, this is the reason I feel very, we gave you some detail by Tagi, but we have not explained to you the beauty yet of the entire system, which clearly is manifested by this essential result.
Okay, thank you. If there is no more question, okay, let's thank speaker again. Okay, next presentation. Is this one, right?
I should use it?
Yes, let's.
What is it? Thank you.
Okay.
And this is a pointer.
Yes,
Does it? Oh, maybe. It is here. Thank you.
Okay, so next presentation from the ELI Beamline facility, Professor Bulanov will be talking about photon acceleration in magnetized plasma, which serves as a possible mechanism for fast radio burst. Thank you, and let's start. Please go ahead.
Thank you. Thank you for the introduction. Approximately a month ago, I heard from Grigory Vereshchagin that you are here are going to organize and conduct a workshop, Zeldovich workshop. And I said immediately that I would like to participate in this workshop. And Remo invited me
And I appreciate very much him for this opportunity to present our results. I remember very well Yakov Borisovich Zeldovich from my student time. You see, at that time in Moscow, we had a very active life of theoretical astrophysics, led by prominent scientists. And Zeldovich had a team where he had several of my friends from Moscow Physical Technical Institute of my age who worked actively there. At the time, I was a member of Ginzburg team. You can find his portrait in one of these pictures, which Remo collected here of prominent scientists, Ginzburg team. And I worked on astrophysics, on supernova explosions, on acceleration of cosmic rays, magnetic reconnection, solar flares, etc. And I saw Zeldovich many times at the seminars, various seminars. At the seminar at Sternberg Institute of Astronomy at Moscow University, and also he with his team regularly participated in the seminars at Lebedev Institute, led by Ginzburg, seminar of theoretical physics. For many years, I was one of the secretaries of that seminar. And astrophysical seminar. I remember him very well, and what I learned during his presentations also made very important effect on my formation as a scientist. I frequented his lectures on general relativity when I was a student. My wife, who is here, she also frequented such lectures from Zeldovich. And that's why, for me, it was a great chance to be here. And I decided to present here our work, which we are working with my colleagues, on acceleration, photon acceleration, in connection with fast radio bursts. Photon acceleration sounds like oxymoron, because a photon, it doesn't have a mass, but actually it is just a terminology. We work not in quantum regime. There are no, strictly speaking, there are no photons. There are very short wave packets of electromagnetic radiation interacting with relativistic modulations of the parameters of collisionless plasma, which change the frequency and amplitude. And we use this idea of changing and frequency of radiation and frequency upshifting and intensification to formulate a problem, to formulate one of the approaches how to explain generation of coherent ultra-short pulses of high intensities. And fast radio bursts, it's a great modification for us. And then motivation, it's publications by Lorimer and his colleagues of discovery of fast radio bursts. And if to say about physics of radio bursts, are used quite efficiently, quite actively, Wing-Zhang review, which has been published several years ago. So far, it's the best review in this field. And even I borrowed these pictures from this review, and you saw these pictures on yesterday, certainly. According to this, what no experts in this field, astrophysicists, the idea of formulation of explanation of fast radio bursts can be subdivided in two mechanisms. One of them, magnetar, it's pulsar-like mechanism with curvature radiation of relativistic particles, or it is called also like a gamma ray bursts, associated also with maybe magnetar, particularly magnetospheres, where we have a magnetic reconnection process, which can generate beams of high energy electron positrons. It's an idea stems from Lubarsky work, and then it is quite actively discussed by the experts here. Then they generate shock wave, collisionless shock wave, and I don't know how to remove this part here. If you help me, it would be great. Okay. It will be less safe, but maybe less better seen. And in this case, this collision-less shock waves forms layers, electron-positron layers, which move with high density, relatively high density, which move with relativistic velocities. And it results in the modulation of refraction index. And as I repeat again, that the interaction of electromagnetic waves with such layers can result in the frequency upshifting and intensification. And for at the end, I will use the key parameters which follow from the observation, that the energy of fast radio bursts is of the order of 10 to the 40 ergs. Frequency, it is hundreds of megahertz to 10 gigahertz frequency, and duration about millisecond, and it may be coherent radiation. Then, if to say about photon acceleration, photon accelerators, this idea has been formulated by a team of John Dawson, and this paper in Physical Revelators, Scott Wilkes, John Dawson, Warren Murray, Tom Katsulios, and Jones, first time brought into our attention an idea of photon acceleration. They have just, this team, they just have formulated a paradigm of laser wake field acceleration in the paper by Toshi Tajima, my friend, and John Dawson. I knew also very well John Dawson. I had a chance to communicate with him. He was an outstanding scientist. And of acceleration of electrons. And they found that a short pulse of electromagnetic radiation can behave similarly, interacting with nonlinear plasma waves. And you see this, it confirms this picture. Is here electromagnetic pulse propagating in collision-less plasma can generate strong plasma wave in the wake of the electromagnetic pulse or in the plasma. It makes modulation of the electric field, which accelerates electrons, and modulation of the density of electrons. And if we inject the short pulse of electromagnetic wave, and its momentum also changes. And you see the similarity of phase space of accelerated electrons and accelerated photons. It's our old paper with Iserkepov, Yamagiva, and Tajima. We published it many years ago in Physical Revelators. And this analogy is widely used. But I think another analogies may be even more fruitful, more useful. One of them is a Thomson scattering. But it is not Thomson scattering of single electron, but it is collective Thomson scattering on a moving cloud of electrons and positrons. And due to Doppler effect, frequency of radiation changes. Rashid Sunyaev mentioned about effect of Doppler effect on Thomson scattering. But here we will say about double Doppler effect. By the way, if to remember old time, when I was a student of the first year at Moscow Physical Technical Institute, in student dormitory, I shared a room together with Rashid Sunyaev. I remember him since that time. He was a PhD student. I was a student of the first year. I didn't know that I would be working also on relativistic astrophysics, but then it happened. And I remember him since that time very well.
But you are together with him in this meeting.
Yeah. Thanks to you.
Space-time coincidence.
Yeah, thanks to you. You made this coherence. Yeah. Remo, thanks again. And then a most fruitful for me analogy is use of an idea of relativistic mirror. Relativistic mirror has been thoroughly described in classical paper by Einstein. You can find his pictures here as well. In 1905 as an illustration of special relativity. If I have a mirror moving with relativistic velocity, and if it collides with counter-propagating electromagnetic wave due to Doppler effect, it changes its frequency, and its frequency becomes dependent on the beta factor, its normalized velocity of the mirror, or it is proportional 4 gamma squared associated with relativistic mirror motion, frequency upshifted. And then, since we have invariant of electric field over omega is a relativistic invariant, electric field of the reflected wave is proportionally increased. It's a way of intensification of electromagnetic waves which people want to realize. I don't have time, it's not subject of my presentation, but we have realized it theoretically and experimentally in Japan several times with high power lasers. And it's a power way towards super strong fields, but it is again not my topic today, maybe in future will do. And then to illustrate this mirror, for example, we have a relativistic mirror which moves in this direction, and we have an obliquely incident electromagnetic wave. What we will see? We will see frequency upshifting, shortening of the pulse, increase of its amplitude, and it becomes more propagating and more closer to the normal, to the mirror, and it becomes collimated, more collimated in a factor 1 over gamma squared. 1 over gamma and then intensity 1 over gamma squared. Then, if we consider the relativistic mirror with not sharp interface, but smoothly dependent parameters on the coordinate, here the modulation of density or refraction index, if you wish, which moves relativistic velocity, but it is not sharp interface, but it is determined by kW. It's an inverse width of this interface. Then, if we work in the regime of lambda k much less than unity, it means that wavelength of electromagnetic wave is shorter than scale of inhomogeneity of the mirror. We can use geometric optics approximation. And photon accelerator is nothing more than relativistic mirror in the case when the interface has a finite width, and we use geometric optics approximation. Let's use this to derive quantitatively the parameters of reflected radiation and for the regimes which I think relevant to astrophysics. First of all, we use the dispersion equation for the electron-positron plasma. It is simpler than electron-ion plasma case, but more relevant maybe to magnetospheres. And here we have omega b Larmor frequency, omega p plasma frequency here, and this dispersion equation for the waves, which gives a relationship between the wave number and frequency of the wave, and the long wavelength or low frequency limit, the dispersion equation becomes simpler, and we have a relation such a dispersion equation which describes Alphen-type, Alphen-like waves, which are of interest for me during this presentation. And then I would like to consider first for simplicity, for it's more easy to understand, more easy to present the case of unmagnetized plasma. But next slides I will devote to the case of magnetized plasma, which is relevant to astrophysics. First, let's consider this geometric optics equations for k dot. It's k is momentum of wave number of wave packet, and x dot x is position of the wave packet, here group velocity, and the relationship between omega and k and coordinates and time of moving refraction index is given by such the dispersion equation. And we should solve this equation. Sometimes it's possible to solve, but more constructive and more useful to find the integrals of the motion and to analyze the behavior of dynamic system in this case. It's integral, it's known in Lagrange mechanics as Jacobi integral. And how to find it? We should use these equations and express k and omega as a function of x dot, and then to cast the equation of motion of wave packet in such a form. It is a Euler-Lagrange equation for Lagrangian, which has a form such the form. It's a nice expression for the Lagrangian. It looks like the Lagrangian of free relativistic particle, but with a mass, here it has mass in commas, which depends on x and t, which is important for us. And then, if you introduce such a variable x minus beta t, beta is normalized velocity of the mirror, we can calculate, express here Lagrangian as a function of psi and psi dot. Then taking derivatives, we can find that such the expression is conserved. It is Jacobi integral, the Jacobi integral. In an unmagnetized plasma, it has such a form, and we will use these expressions in future. Then, if we have at hand this Jacobi integral in terms of omega and k, it has very simple form, and omega is function of psi and k, and we can let's use such a profile of the density of refraction index as a function of psi. It's like a transition layer, or it models, mimics the shock wave. And then we plot the phase space of this dynamical system. It's contours of constant value of that Jacobi integral. And what we'll see? We'll see here that this phase space has separatrices, which are plotted in blue. It's subdivided into three subdomains. Here it's transparent, and then reflecting waves. And to find quantitatively what happens with frequency, we need to analyze critical point of this dynamical system, which is here, at infinity minus infinity. And to find the parameters of that separatrix, and then to calculate the Jacobi integral, and then we can calculate all the frequencies which we need analytically. And here there is an expression for frequency upshifting, which is function of modulation of density and the velocity of the mirror. And if we consider maximum and minimum change of the frequency, it follows Einstein formula. And here we can find acceleration length, how long does it take to frequency upshift, which is also we should keep in mind what size of the system which is required in this case. Let's implement now the magnetic field, which is more important for astrophysics. Here we have a change of that dispersion equation, and we have expression for a Jacobi integral, which contains omega b, Larmor frequency, again such the profile of density of plasma, and we see what happens with the phase space. It becomes more complicated qualitatively. We have four subdomains. We have a stripe where the electromagnetic wave cannot propagate. We have two separatrices. We have here such the behavior of these trajectories, reflected radiation and transmitted radiation. For comparison, here you see a red dotted separatrix, which shows a comparison not magnetized case. And as a result, we see that in magnetized plasma, situation is more complicated, and if you wish, we can get even higher frequency than in the case of unmagnetized plasma. But for applications, which I have in mind, we can consider this case, and here we see that maximum frequency is limited by the Larmor frequency. And we can find, as I said, to find the parameters of the separatrices, critical points, and position and value, and to calculate what happens. And we should find the dependence of group velocity of electromagnetic wave in the electron-positron plasma as a function of omega. And here it's a plot, and you see the stripe where electromagnetic wave does not propagate, and critical points are determined by the places where the group velocity is equal to the velocity of propagation of the mirror. And we can find all these critical points to calculate the frequency upshift. And it is here. You see this frequencies we can find, and frequency upshift minimum, maximum is cyclotron frequency here. We don't know what happens with electromagnetic wave, but which wave we want to upshift frequency and to intensify. In the physics of collisionless shock waves, which is actively under the development now, analytically, experimentally, and with computer simulations, particularly in application to fast radio bursts, it is known from computer simulations. I borrowed it from the first paper at Iwamoto. Masahiro Hashino, whom you know, he is one of the authors of this activity. You can see typically when we have collisionless shock wave, we have precursors in the upstream region ahead of the shock wave, which are formed by fast particles. It is a modulation of density, modulation of magnetic field, electric field, and it's a low frequency, relatively low frequency electromagnetic waves. And we have a beam of particles here which excites these waves. And you see this very active work here. It's just few papers, but much more here. The most recent is a 2026 paper. And what is the mechanism of generation of precursors? We have fast particles, fast electrons accelerated the shock wave front. There are several mechanisms. It's a drift acceleration, surfatron acceleration, and then a Fermi mechanism of acceleration of charged particles in turbulent plasma, depending on the parameters of shock waves. It's a special zoo and a special activity in this phase. But I consider that we have already this beam of particles, and when it propagates in an upstream region through the magnetized plasma, it becomes this beam becomes unstable with respect to the beam plasma instability. And we can write, and it was preliminary discussion here in these papers about such instability, but here you see how to derive the dispersion equation. Here, the part which corresponds to the electromagnetic wave which we want to excite. Here, the mode corresponds to the beam propagating in the magnetized plasma, and on the right-hand side, there is a term which gives you coupling between these two modes. And I am interested in low-frequency radiation in this case, and dispersion equation becomes simpler in this case, and we can find analytically the growth rate. Here it shows that we have excitation of alpha-like modes, which I mentioned before, low-frequency modes, with maximum growth rate here. And it is analytical result, but we can solve this full set of equations numerically. And you see here real and imaginary parts of the frequency of these waves. Blue is the real part, red is the imaginary part, it's growth rate. And we have the development here of instability. Here the parameters are chosen to be in the so-called non-resonance regime of such instability and the low frequency, which I want to have. And here it's a wider range of parameters. We can see growth rate, it's the same in different presentation. Growth rate is a function of K wave number, and omega B is the parameter. In highly magnetized plasma, we can get from non-resonance to the resonance regime of generation of such instability. In principle, I don't know what I need about photon acceleration or frequency upshifting, about generation of low frequency waves. And what I would like to make a next step to say about astrophysics of these findings which we have found. Against, we use the parameters which we know from the observation. It's the energy of fast radio burst, approximately 10 to the 40 ergs, frequency of order of from 300 to megahertz to 10 gigahertz, duration 10 minus 3, it's 1 millisecond here. And then we can calculate estimate the energy of fast bars. It's amplitude of the wave in second power times the volume. Volume, it's a transverse size of the pulse of electromagnetic radiation, and shorten it longitudinal. It's like a pancake that propagates the pulse. Here, shortened due to the reflection from the mirror. And from the frequency here, approximately 1 gigahertz, we can calculate the magnetic field. We can calculate the magnetic field, which is here, it's approximately 60 Gausses. Local frequency where we have generation of fast radio bars. By the way, I should say that I'm working here with physics which we have revealed for a photon acceleration in lower subdomain, which I want to intensify lower frequency radiation to high frequency, and high frequency is cyclotron frequency. Then nonlinear wave propagating inside the plasma when its amplitude becomes of the order of background magnetic field, it starts to change, maybe saturate. That is why I say that the frequency of precursor should be maximal. Amplitude should be of order of background field. And then intensified field of the reflected wave, it's high in the factor 4 gamma squared of the shock wave velocity corresponding. Then we know this duration of the gamma ray burst from the observations. It is of the duration 1 millisecond. It corresponds to duration 3 times 10 to the 7. You can find in Bing Zhang review this value as well. It's very well known for the experts. And but we keep in mind that this duration length of the pulse, it is compressed pulse. That's why initially this cloud of photons had larger volume. In 4 gamma squared size, in transverse size, it remains the same. And then we can calculate these parameters here, B, fast radio burst, volume of fast radio burst. And then we should keep in mind that the radiation is collimated and directed in the narrow angle, again, due to relativity effect. That's why here appears the factor 4 gamma squared again. Again, 4 gamma squared. And what we have as a result? We have known size of the gamma ray burst. Not gamma ray, but sorry, it's maybe next time gamma ray, but now fast radio burst. But its amplitude, this is number which we calculated. And the left-hand side also known from the observation the energy. This equation for the gamma factor, which corresponds to the velocity of the shock wave. We can solve it, of course, it's an arithmetic equation, and we find the typical gamma factor for the parameters for 40 erg, energy 10 minus 3 second duration, and the frequency approximately gigahertz, gamma factor 16. It's reasonable. It's reasonable.
How much it comes?
16, it's no, it's relativistic, but not a huge. And people who, astrophysicists who discuss what happens in magnetar, they say about this 10, 100, it's reasonable. It's not too small. It's not huge. If it would be huge, it would be a disaster. It will, how to break this theory. But it is acceptable.
This is very good point.
Yeah, thank you. And another good point that I calculate the size, or typical size of cloud of photons, which also is, comes from these estimations. And we can find it's of order of 3 times 10 to the 10 centimeters. It doesn't contradict to the size of magnetosphere of pulsar, of magnetar. It is not, does not contradict. It can be larger, smaller, depending on what we choose, 10 to the 40 ergs, 10 to the 35, 10 to the 43, etc., but not very sensitive. And the size of magnetar typically is 10 kilometers. And here we see that it is magnetosphere, it's larger, several orders of magnitude, but it is acceptable. Then we should calculate the magnetic field. this B0. We know what is a magnetic field on the surface of pulsar, of neutron star or black hole, I don't know what, and it is 10 to the 14 Gausses, if it is here. This magnetic field we have found already, but here we should calculate also, place the radius of magnetar, and then the length of the fast radio burst. To make something reasonable, which doesn't contradict our expectation, we should take into account that the magnetic field doesn't have a form of dipole, but it has different structure. It's a so-called twisted magnetosphere of the magnetars. In the papers by Beloborodov, he introduced this idea, this approach, and this expression gives that we have no contradictions between everything which we have here, provided we have finite twist parameter. It's 0.75. It is from 0 to unity. It's acceptable also. I don't see huge contradictions between our model and what we do know from the observations. Of course, in observations, the experts know much more, but I do. But nonetheless, what I know, I didn't find huge contradictions. Otherwise, I would not present here these results. And in conclusion, it's a summary. I can read, you can read it, but maybe it's better to see this picture. It is the same. You see, we have somewhere the magnetar in some galaxy. Then this magnetar, due to some activity, it's a rotating magnetic field. It's this magnetosphere, and it will have some activity, star quake or magnetic reconnection. Here I make this magnetic place where magnetic reconnection could be. It generates a beam of electron positrons, relativistic. Usually it is gamma factor, which I said it's approximately 10, 20 gamma factor. It's a tenth of MeV. Then it makes collisionless shock wave. Here, due to some acceleration mechanisms, we need to consider it more details. We generate fast particles which excite, due to beam plasma instability, we excite precursors, electromagnetic precursors. And then these precursors, they propagate with a velocity slower. It's one of the parameters which we should respect. Slower, the group velocity is smaller than the velocity of shock wave, and shock wave kicks them forward and generates a short, high amplitude, high frequency coherent path of radiation which propagates in space and detected on the Earth. This is a summary of what we have been considering now. Thank you for your attention.
Fascinating. Thank you. At least it gives an additional theoretical framework on which to tune the data.
Yes, I think so. It is. I can say that I learned what people did for maybe 30 or 40 years in this field. First idea was from Colgate and Nordlinder. They considered relativistic layers which can intensify low frequency or static fields. I found immediately that fits perfectly what we're doing. I'm doing in relativistic mirrors for laser plasma, for fundamental science, etc. Then it was a paper by Yelenevich and Penn who also touched the problem of relativistic mirrors. But I think our team, together with my colleagues, we made it more systematically and attracting, gathering together and other processes. And what at the end we found, I don't see huge contradictions, unless you know same as this.
I have questions. on the dispersion relations.
Which relation?
Dispersion relation.
Yes.
I want to see asynchronous resonance and width, and also condition for omega become emergent to see the instability.
Yes, exactly what I said. What I said, you see that here, dispersion relation, what I analyzed here, dispersion relation, even, where it is? No, it is.
Yes. So there's width and resonance, and how it become emergent, become instability. I want to see more.
Yeah, I understand. You see the instability is here. It's a beam instability. For electron, you can find some previous papers where they touched such a type of instabilities. An electron ion plasma in plasma physics is very well known. And even you can find in Landau-Lifshitz books by Lifshitz and Pitaevsky book, electron ion instability discussion. Here, I think it's more systematic what we did considering this instability. And this dispersion equation has a real and imaginary part of waves, and they're here. You see blue, it's a real part, red, it's imaginary part. This is instability. It's low frequency instability, but here, if the magnetic field becomes much higher, we can have more complicated structure of resonance instabilities, which is also maybe for future in the future we will consider them also.
Okay, so very nice talk. So the slide of astrophysics of FRB, can you go to that slide? Astrophysics of FRB. Third last slide. Yeah, this one. So can you explain the difference between B0 and BFRB?
B0 we take from the frequency of this 1 gigahertz. It's a B0, it's a 60 Gausses from this case. It's a background field in the place in magnetosphere where everything happens. And then the precursor which we generate due to the instability, it has the frequency which is of order of this omega B2. No, sorry, B0. And then and the amplitude also of order of B0, because of if the wave has a amplitude higher than background field, our theory of instability is not relevant. It's absolutely nonlinear. It's a different regime. Today I don't know how to solve it.
Final result, where is the shock? What the B field in the shock region? So based on the last equation.
It changes, but it changes from 10 to the 14, I don't know, 10 to the 12 to 16, but typically it's 60 because of it is main region size where everything happens when we form this pulse.
It's very close to the magnetic surface?
No, it's at a distance 10 to the 10 centimeters. Here it was 10 to the 10 centimeters. It's far. That's why it is.
If that's the case, then B should be much lower, right?
Yes, it is lower, but it is 60 Gausses. It's lower than 10 to the 14. But we estimate that at this distance we should have 60 Gausses, and that is why we should play with dependence on the size in such a form with twisted case. Otherwise, it would be more difficult to respect it.
Okay. Thank you for nice talk.
Thank you.
If I may. What is the relation between the plasma frequency and the Larmor frequency? Is there any correlation, or is just two independent? And another question about the correlation. The correlation. I mean, you have coherence probably also in the incoming radiation before amplification to explain a fast radio burst. Do you need the coherence as well?
I see. The density of plasma, what I learned from various papers, including your paper as well, 10 to the, on average, it also changes, but on average 10 to the 11. It corresponds to gigahertz frequency of plasma frequency. Again, it is not too small, it's not zero, not much higher. If it was much higher, it would be absolutely different scale. That's why it is acceptable. But about coherence of various, there are many open questions. For example, magnetic reconnection, how it happens. I should confess that I consider myself as an expert in magnetic reconnection. I published maybe 100 papers on magnetic reconnection and acceleration of charged particles. But how to make the beam, relativistic beam of electron-positron beam flow, for me, it's attractive but not yet solved problem. How to make it consistently. Then I agree that there is other mechanisms of generation of coherent, not coherent radiation, turbulent, not turbulent, but step by step let's address these questions. Today I'm not ready to answer on all possible questions. I like to see that my talk excited questions.
So you have, that doesn't work.
First of all, let's thank very much for this and the other presentation, but I would like to, we will share all this presentation. People can go back and listen to them. But at the same time, I would like to encourage the people who are participating to write the key point of their derivation with a very as complete as possible, because we are in evolving field. At least indicate the existing reference around in this house, in these days, which support your own work. This is by far the most important, because we will have the record. Everybody can return to that. But I ask from each author a set of, not too many, you indicate already during the talk, but give the reference to the key idea which have managed to bring you to this presentation.
I try to do.
Excuse me?
I try to do. First of all, it's
yes.
Einstein first.
Yes. Yes, we are not new to this, because the key reference given by the first person who spoke at the meeting on Einstein and Fermi-Einstein and Bose-Einstein statistics was a good example. And you are, of course, among the people who can refer to the classic work. Okay, one duty for every one of the speaker is to go back. For example, we have made a special effort in going back to Einstein work, but also we have made a special effort in going back to Heisenberg work. And you are and to the Bose-Einstein Fermi-Dirac. I mean, this is the crucial aspect which we are going back to, the continuity of this fundamental work and their manifestation in astrophysics. Okay?
I try to do, but limited time, of course, I cannot do full, but you can find in these two papers
Good.
First of all,
But
we just published a paper called Photon Acceleration in Electrolyte Plasma in New Journal of Physics that appeared
Yes.
a couple of weeks ago. And here we submitted for publication in Australian Astrophysics this paper, which I can present it here. But you can find it in the internet as archive preprint.
yes,
The difference is.
but again,
There are approximately like 50 or 100 references.
yes, that
But you can
just
find much more references in a review by Benjamin.
yes, but still guided to the fundamental work. Take this occasion.
Yeah,
Thanks.
thank you.
Okay, thank you. Thanks again. Let's thank the speakers again. So we'll have coffee break for 10 minutes. 15.
The gentleman was referring to supernova.
Oh,
2110101.
220101.
Yeah. Do you know what was the? Oh,
Ah,
sorry.
List of the beach. 2000 Pescara is in this list. Last year it was in the list. It's a good beach list. I don't know.
linear Compton scattering. Actually, to me, this opportunity is quite special because in 2015, I attended a conference in Pescara and a workshop and delivered a talk. And I mentioned then that we will work on nonlinear Compton scattering. And so after 10 years, I'm happy to bring some result for my work 10 years ago, 11 years ago. Okay, let's start. Okay, nonlinear Compton scattering is actually Compton scattering is scattering of radiation by electron. And in this case, when the radiation intensity becomes very high, and then it becomes nonlinear, it means that the multiple photons can be scattered into one photon and so on. So this is a kind of a toy simulation for the case. Assume that we have 2.5 GeV high relativistic electron bunch, and we have a laser field here. It is focused around at 0 position here. And then when these two interact, it generates the gamma rays. And initially, electron has a spectrum, more or less monochromatic spectrum, but through interaction, it generates a gamma ray photon. At the same time, there is just some decrease of its energy. Okay, this is this is a toy simulation is for the condition of the nonlinear Compton scattering experiment to be reported in the literature 2 years ago. So, but if now we can increase the laser intensity. At this time, the laser intensity was 6.10 to 20 watts per square centimeter. But the important dimensionless parameter in this case is chi value. It means this is kind of a quality parameter. So when chi is around 1, that we are in the strongly nonlinear regime in the sense of QED. I will explain it what it means later. So we can increase the laser intensity, and then now let's increase the laser intensity to 5.5 10 to 21 watts per square centimeter, and then the chi value is 1.5, so definitely higher than 1. And in this case, in addition to gamma ray generation due to Compton scattering, we have a generation of positrons. So not only gamma ray, but we have the positrons. And the highest laser, we can increase the laser intensity further, and then at the highest intensity, like 2.10 to 23 watts per square centimeter, and then we have the scattering of the initial electron beam, and we have copious generation of gamma ray photons and the positrons, and they are all scattered out very well. Previously, the electron did not scatter much by the intense laser pulse because the inertia of these high relativistic electrons are so high. So even though intensity is as large as 10 to 21 watts per square centimeter, but it is not sufficient to really jiggle vigorously this electron. But at this high intensity, the intensity of the laser field is so strong that it can really scatter out the laser electron beam, and at the same time generate a lot of gamma rays and positrons. And at the end, we have some medium consisting of electrons, gamma ray photons, and positrons that is called the QED plasma. So this is the general idea of what I'd like to present today. Okay, but I will show you the experimental results, not the theoretical one. Okay, these are the works from contributions from many people. Here I just listed all the people, the name of the people who contributed to this work in the past and the present. I hope that I did not miss anyone here. Okay, so the question is, what is the strength of the field which can be considered strong in the sense of QED? And then we can just think about defining parameters of 3D. So these are C, H bar, M sub E, and E. And out of this, we can cook out some quantity which has dimension of the electric field or magnetic field. Its magnitude is 10 to 16 volt per centimeter or 10 to 13 Gauss. And this value is called the Schwinger field. So if we cannot deliver some external field which is as strong as this Schwinger field, then we are in the regime of we are under the influence of a strong field in the sense of 3D. So the well-known conventional 3D is a very, very weak regime. And now we are talking about the high strength regime where the external field can compete the 3D's intrinsic field scale. And this meaning is that if you have this Schwinger field and then over one quantum length, you can generate real pairs of electron and positron. That's the meaning of the Schwinger field. Then the question is, what the laser is the laser is the method we can use to generate the strongest electromagnetic wave. Then the laser intensity, the required laser intensity is 10 to 29 watts per square centimeter, and it is larger than, by order of 6, than the current record of the intensity. Actually, this intensity was achieved by my colleagues, but because of the multi-petawatt laser facilities in Europe, China, in USA, I think that sooner or later we will see the values much larger than this one. But anyway, still, the required intensity is larger by 6 orders of magnitude than we can achieve at the moment. So then the idea is, the solution is that instead of the rest electron or vacuum, consider the electron which is moving almost at the speed of light. And then in the rest frame of the electron, and because of the Doppler shift of frequency and amplitude, actually the electron sees a huge enhancement of the electric field in its own proper frame. Then we introduce, so if we can make a setup in which the highly relativistic electrons collide with ultra-intense laser pulse, and then we have a chance to achieve this Schwinger field in the frame of electrons rest frame. So that's then we introduce the so-called quantum nonlinearity parameter, and it is nothing but the electric field seen in the electron's proper frame compared to the Schwinger field. So when this chi value is around 1, then we are in the strongly nonlinear regime of 3D. And another parameter is so-called classical nonlinear parameter A0, and its meaning is that the work done over the number of photons relative with the work done over one quantum wavelength, because the 3D process happens over a length scale of quantum wavelength. This is a parameter which shows the multiphoton nature of the process. So in this sense, the strong field 3D regime, or 3D in the strong nonlinear regime is chi is around 1 or larger than 1, and the A0 is much larger than 1. So it is so these 2 parameters define the strong field 3D regime in that way. for example, typically the laser wavelength is 800 nanometer. So if we have just a rest electron and we want the chi value is 1, then we really need 10 to 29 watts per square centimeter of intensity. This is a huge value, and as I said, it is not available at the moment. But if you have 2.6 GB electron, then you just need 10 to 21 watts per square centimeter. It is definitely well within the level of what you can achieve at the moment. So there is actually nonlinear Compton scattering is a highly non-perturbative process, but its theoretical formulation has been done over a long time. And so make it short, in typical QED calculation, electron propagation is represented by this so-called free electron propagator. But in our case, the electron is not free, but it is under the influence of the very strong electromagnetic wave. And then instead of a single line, we represent it in the double line. And this double line is actually the superposition of the single line and the single line interacting with the external field 1 time, 2 time, and so on. So this double line is a so-called dressed electron propagator. So in a very rough sense, if you replace the usual electron propagator in the conventional QED by a dressed electron propagator, you are more or less get the right result in the strong field regime of QED. But the calculation is very complicated. So, and the lowest order strong field QED process is nonlinear Compton scattering. So we have addressed the electron comes in and generate electron gamma ray photon out, and then it is scattered. So here N is the net number of the observed photons, and I need some explanation about the meaning here. Actually, in this form, one may say that, okay, let's assume that the N is 2. Then the electron interacts with 2 laser photons and generate 1 gamma ray photon. And it is not the correct way interpreting this formula. Actually, when, for example, N is 1, it is a superposition of all these processes. It means that the one laser photon is observed and 1 gamma ray photons are emitted. 2 laser photons are observed, but the 1 laser photons field and the electron, and it generates gamma ray, and this gamma ray photon can interact with the laser field again, and then generate the electron-positron pairs. And one higher order process is the combination of these two and called the trident process. Okay, these are the basic process, and its kinematics and its dynamics are well understood in the literature. But the question is, let me just summarize the basic pictures. Actually, from the theory of nonlinear Compton scattering, you can calculate the transition rate. And this is n value, the order, and this is a transition rate. So when the chi value is small, because the intensity is small, and then we have a sharp drop as the order increases. And this is the typical behavior of pottably or weakly nonlinear system. As your order increases, its rate becomes dramatically drops. But as you increase the chi value by increasing the laser intensity, you see that it stretches out so that at the end we have kind of slow, gradually decreasing or kind of a plateau structure as a function of order. And at the same time, not only low orders, but also high orders are generated quite strongly. So this is the typical behavior of any physical system which make a transition from weakly nonlinear regime to strongly nonlinear regime. So this picture is the generic. This is the general feature of all nonlinear physical system, and the nonlinear Compton scattering is not an exception to that. And, but in experiment, we do not measure transition rate as a function of nonlinear order. We measure in terms of gamma ray photon energy. And then here, this is the electron energy was fixed to 2 GeV, and we increased the laser intensity from 10 to 14 watt per square centimeter to 10 to 22 watt per square centimeter. And then initially we have this well-known edge structure of Compton scattering. This is first order edge and the second order edge. And as we increase the intensity, actually these edges are red shifted, because when the electron is it is driven by strong field, its inertia increases dramatically due to relativistic inertia increase effect. And that's why it showed the red shift. And at the same time, the overall signal level increases. And also you can see that the post edge shift from here to here. So it means that all these signals are from high orders, very high orders. But at the end, when the intensity is 10 to 22 watt per square centimeter, we have a sudden drop. And this drop is not physical, because this drop is artificial, because when I calculated this one, I limited the nonlinear order only up to 2000. But if I increase the nonlinear order up to 2 million, then we have this full spectral picture of the nonlinear Compton scattering. So this is the 2 GeV here. It is kinematic curve of the gamma ray photon. And the basic features are in the low order, so we have some sharp decrease, but we have a very long plateau. And around the kinematic curve, we have a sharp curve. So this is reminiscent of the X-ray spectrum generated through atomic harmonic generation. So in a sense, nonlinear Compton scattering is the 3D version of harmonic generation. Okay. So, but this is all single electron microscopic theory of nonlinear Compton scattering. But to understand the experimental result, well, many electrons interact with the focusing laser field, we need the more versatile simulation, and it is called, the method is called the 3D PIC simulation. Here, the general idea is, you know that the PIC simulation just solves the Lorentz equation and the Maxwell equation all together. And it is continuous. It describes continuous evolution of a system. But we noted that the continuous evolution of the Lorentz equation and Maxwell classical physics is over large scale, but the QED events can accommodate shorter time scale. Then we can treat the QED event as in a Monte Carlo fashion. So it is called the QED PIC simulation, and almost many modern relativistic PIC code have this capability, and we have used the Osiris program smartly in our study. And of course, when you analyze the experimental data, we do not perform toy simulation. We do the full 3D simulation, and this shows the result of 3D PIC simulation. And initially, we have electron spectrum like this, but after the interaction, it has quite amount of redshift, because through the nonlinear Compton scattering process, the electron delivers its energy and momentum to gamma ray photons, and gamma ray spectra are obtained in this way, and at the same time, we can obtain the spectrum of electron and the positron generated through nonlinear Brightwheel pair production. So these are, there have been many experimental experiments about the nonlinear Compton scattering, and the first was done at the end of the last century at the SLAC. They used the electron accelerator to generate almost 50 GeV electron, and so this graph showed the summary of the nonlinear Compton scattering experiment after the first seminal result. Actually, this is the electron energy, and this is the laser intensity, and this diagonal line refers to the chi value. So chi 1 value is here, and for a long time, almost all experimental results have been done below chi 1, so in this case. But very recently, even though it is not reported yet, we succeeded in making experiment slightly above chi 1 line. So what I'll show you today is the result of this 6 and 7. And the first nonlinear Compton scattering experiment used 50 GeV electron from electron accelerator, but now in the laser facility we have an easier way to generate GeV electrons, and it is called laser wake field acceleration. And okay, oops. Okay, this is the laser pulse going through a rarefied plasma, and then it pushes out the electron in the middle, and there develops a cavity of devoid of electrons, and then there is a very strong electrostatic field, and that electrostatic field can pull some electrons in the periphery and then accelerate those electrons. And the level of acceleration is up to several GeV over a centimeter or so. This is the way, it is called laser wake field acceleration of electrons. And if we use this method, we use this method to obtain the GeV electrons for nonlinear Compton scattering experiment. Okay, this is this is our facility, and we did the nonlinear Compton scattering experiment and published it in the 2024. And this is the experiment that failed. Okay, we have a laser beam, and it is split into two, the main beam and the scattering beam. Main beam is used to generate a GeV electron beam by the laser wake field acceleration process. And this scattering beam, actually, it interacts with the GeV electron beam generated through laser wake field acceleration. And here, the nonlinear Compton scattering occurs, and then the electron goes straightly and along with the Compton gamma rays, and in the middle we put the magnet to knock out electrons, and at the same time measure the spectrum of the electrons. The gamma ray beam goes straightly up to this pixelated scintillator. So when the gamma ray beam actually interact with the scintillator pixels, eventually the gamma ray energy is converted in the visible light like this, and from this we can reconstruct the gamma ray spectra. So even though it sounds straightforward, but the important thing is that this happens in the length of micrometer, several micrometer volume and several tens of femtosecond time. It means that you should be really accurate making the electron beam and the laser pulse collide at such a small space-time volume. Okay, so this is the result. And this is the electron spectrum. We have almost 2.5 GeV electron, and this is the resulting scintillator signal. And out of this signal, we reconstructed the gamma ray spectrum. This is the gamma. If we do have only conventional linear Compton scattering, and then this is where the first order edge should reside. But we have a high signal of this line, and this high energy signal can generate it only through the nonlinear Compton scattering. And the estimated highest nonlinear order is around 337. It means that in net, 300 laser photons are absorbed into one gamma ray photons. It is a highly nonlinear process, and the estimated chi value was 0.46. And this was reported in our paper, and then we could increase the laser intensity in the meantime, and then now the estimated chi value was increased up to 1.4, and then the estimated nonlinear order was over 10,000. So it means that we are safely in, it seems that we are safely in the strong nonlinear regime. Okay, and then what's next? Actually, this roadmap made by John, and it shows the general idea of the strong field QED research or the way to go. And the horizontal line is the chi value, and the vertical line is the power of the laser. So we are more or less in this region where the basic processes, I mean the nonlinear Compton scattering and the nonlinear Bright-Wheeler pair productions are demonstrated. We are at that stage experimentally now. But if we go beyond the chi equal to 1, then we have the type cascade, shower type cascade, and over 10, we expect the avalanche time cascade, so that eventually we hope that we can generate 3D plasma consisting of electrons, positrons, and gamma rays, all move at the speed of light. Actually, such a capability of generating QED plasma has some relevance with extreme astrophysics. For example, as you are very well aware of, as you know very well know, all the highly energetic compact objects in the heaven, they are all surrounded by strong field QED process and QED plasmas. For example, in the pulsar magnetosphere and the magnetized magnetosphere, the field level can be 50 times of the Schwinger value, and all the QED process can occur in a highly non-perturbative, highly nonlinear regime. And I think even though these are all, there is a kind of common between these processes, like because these QED processes occur under the influence of the very strong field, there should be some common aspect between the laboratory nonlinear Compton scattering using lasers and this astrophysical QED processes, but we should find the exact connection between them. And another sense is that, another point is that the laboratory-based QED plasma generation is gives a way to do some QED plasma research with some relation to the environment around these energetic compact objects. So strong field QED may provide some extreme laboratory astrophysics, so-called. We want to work on the astrophysics in the laboratory. And in that sense, for generating QED plasmas, nonlinear Compton scattering is not the best option, and there are many ideas, and the two most well-known ideas are colliding two ultra-intense laser pulses, and then we have a lot of the QED plasma generation, pair plasma generation here, and when we irradiate the solid target with a very strong laser pulse, and then they expect a lot of generation of electrons and positrons and gamma ray photons, and these are the more, I would say, the promising ways of generating QED plasmas. And the conclusion is that, let me paraphrase the famous term expression coined by Phil Anderson, that he said that the more is different, and I would say that the stronger is different. In the sense of physics, that when you increase the strength, we have qualitative changes in the dynamics. And this strong field QED, not an exception, and the nonlinear Compton scattering we have demonstrated in the strongly nonlinear regime is kind of the very beginning, stepping stone into this line of research. And it is a unique combination of new regime in microphysics of QED and relativistic plasma physics, which showed the relativistic collective behavior. And kind of fruit we can obtain in pursuing this strong field QED is that it can, because it happens in the in an extreme physical condition, it gives us some chance to make QED plasmas on the Earth. So that's why we work on the strong field QED. I would say that we just started. We started the very beginning hurdle, and then we should go on in this direction. Okay, thank you for your attention.
Thank you. Thanks a lot for nice talk. We have time for one short question.
Chermin, do you hear me?
Yeah.
It's
congratulations.
Congratulations to you and your colleagues. I
Thanks.
have one small question. Did you observe something which has not been predicted theoretically?
Pardon?
Did you observe some effects which has not been predicted by Ritus, Narozhny, Nikishov, and others? Some effects. Did you see in your experiment which does not, which is not described by the theory?
I would say that I would say no. We could not.
Also good.
Actually,
also good.
Actually, okay. I would say that, okay, the simulation is, even though the simulation uses, does not use the Ritus-Narozhny formula, but uses some approximations of a quantum synchrotron model, but generally, as the envelope wisely, they more or less the same. So within our experimental accuracy, we cannot say that we observed something is much different from the expectation from Ritus-Narozhny formula. Our level of the experimental accuracy cannot touch that problem, cannot touch that condition at the moment.
By the way, as an example, I can say just what comes to my mind. The effect of a very narrow spot of sharply focused light, which is not plane wave. First, and second, not a constant local constant phase approximation. Do you see these effects experimentally?
Actually, you see that our actually, as far as I know, the discrepancy between the exact field profile and the locally constant field approximation is manifest in the low energy regime, low energy part. But so it was actually we could not see the low energy part because the low energy regime, the signal gamma ray in the low energy part, I would say this around below 20 MeV, they are superposed with the Betatron radiation. So we deliberately try to knock out that part in the experiment. So with this high energy part, I think that it will be difficult to discuss the discrepancy between the discrepancy due to locally constant field approximation.
Okay, thank you. Thanks a lot. Let's thank the speaker again.
Okay,
So,
thank you for your attention. Yeah.
Next speaker, Yuan Ming Wu, who will be talking about nuclear physics and astrophysics driven by intense laser. So let me set up the, which one was it? This one. Okay, please, you have 25 to 30 minutes if you, thank you. Okay, please. A moment.
Okay. So good morning, everyone. How I can? No, I mean to.
I think it doesn't work.
It doesn't work. Okay. I will talk about nuclear physics and astrophysics with driven by the intense lasers, and it's not working.
Let's try again.
Hello. Is it working?
Can you hear? Yes.
Okay. First, I would like to mention that the title of the talk given by the organizer is too general. So I will at first briefly introduce the topic in a very general way, and then I will focus on two kinds of process. One of them is the nuclear excitation by electrochemistry, and another one is the nuclear reactions with the applications in the astrophysical environments. And at the end, I will briefly summarize my talk. And I will first give a very brief and general introduction for the topic of the laser-driven nuclear physics and astrophysics. We can actually, this here shows the basic idea of the basic development of the laser technology, and we are now here at more or less the intensity of the 10 to the 23 watt per square centimeter. And I would like to mention that here, as actually we are still a bit far away from the Springer critical field, but still with this very powerful tool, we can already have very often a lot of new opportunity for the study of the nuclear physics and also astrophysics, and because it's a powerful tool for the acceleration of many particle source, and also it can provide a lot of extreme environments with the high energy density plasmas. With this kind of conditions, we can have a lot of difference from the between from the traditional conditions and for the study of the nuclear physics and also physics. And here is now I will start with the first topic that we have focused a lot in the past few years, the nuclear excitation. And before introducing the process, I would like to mention at first the nuclear isomers, which is relevant for very close relevance to the process. And nuclear isomer is actually the is long-lived excitation of nuclear, and it's very important for the study of nuclear structure, and also very important for the nuclear astrophysics, because in the astrophysical environment, you always have plasma. Many places it has plasma environment. So many of a large portion of the nuclear is actually in the excited state. So actually, this is the point that actually from the conventional accelerator to extend to the astrophysical environment, this is the missing part. Actually, most of the case is the missing part, because most of the case in the laboratory, the nucleus is in the ground state, not in the excited state. So this is actually very important, but we still need a long way to go to really analyze, really understand the excited state, the influence of the excited state. And also it has a lot of application. For example, we saw here the isomer depletion, because it's a very stable excited state, and it has most of them has very high energy. For example, a few MeV here, but we can here we can the decay down is very low. It's low, but we can hit. We can pump them to the above Leibniz state and then decay down very fast. Which means that we can serve as a nuclear energy storage and releasing of the energy, if we can drive the transition between the asymmetrical state to the higher Leibniz state. And also another case, very interesting now, very hot topic now is the nuclear clock, which is relevant for the very precise and stable across using the nuclear transition, nuclear isomer of the 229 with a very low energy, about 8 electron volt. But we can show it here that, I mean, the process that we are now interested in the most is the nuclear excitation by electrochemical, and we can see here that in the process is the ion capture one free electron to the bound state of the autonical system, and then excite the nuclear. And we can see here this is actually the a process in the interface of the between the atomic physics and the nuclear physics. And why this is important, because we can show here a few of the reasons. First is proposed the theoretical sleep actually 50 years ago, and the first experimental observation claimed only a few years ago, and it's very, very relevant for the fundamental studies of nuclear physics. And also we can see here that in the astrophysical environment, we always have a plasma environment. We can have this kind of thing can always happen there, and it's very, very, very important. And also, as we have already mentioned, the process is actually the interface between the atomic system and the nuclear system, which means that we can manipulate the states by this kind of process, by the manipulation of the ions and electrons, which is more simple to direct interaction with the nuclear states. And there are a number of scenarios we can study for this kind of scenario, for example, the plasma, this is a very general case that we can study the scenario, and also we can have other kinds of scenarios. We can have the ions and the electrons, and in the following, I will focus at first the process for the isomer depletion, and then we will discuss the first kind experimental observation of Nick, and then we will discuss the production of isomer using this kind of process. And we first introduce here is that the nickel for the isomer depletion, as we can already see in the very beginning, that there is this case of the molybdenum isomer with the energy of 2.48 MeV, but the transition from this isomeric state to the cycling state to bumping the energy is about 5 kV. So we can use if we want to really drive this transition, the first choice should be using the S-ray. But however, if we consider the very intense S-ray or the high power lasers, we can have the intensity here. We can create a plasma here, and then this process can happen. And our calculation shows that with the high power laser available today, actually the nickel efficiency can be more than 10 order of magnitude larger than the S-ray laser that we can achieve at this moment, currently achieve. We can see the importance of this process. And as I have already mentioned at the very beginning, this process can also have the chance that we can manipulate the nuclei by the electrons, and I here also shows one of the possibility of the manipulating of this process by the shaping the electron wave function. In this case, we can use a laser, or we can use a phase mark to interact with the plane wave electron, and then to introduce an angular moment, orbital angular momentum to the electron, and which we normally call it as the vortex electron. And with the vortex electron, we can see we have the orbital angular momentum clearly here in this case, and with the angular momentum, we can couple to the nuclear system that we may have interesting results. And we can show here the results, the comparison between this is the comparison between the cross-section between the vortex case and the plane wave case. We can see the different Castro channel there shows the oscillation. The oscillating of this phenomena, actually, we can see here. This is the manipulating between the orbital angular momentum to the nuclear system, and we can show here that this is the plane wave case, and this is with the different angular momentum of the electron, and we can see here that the best channel can be shifted between with the different quantum number of the electron beam. And here is actually we saw only the very preliminary result of the vortex electrons with the to the nuclear system. And I would like to mention also, actually the interaction of the vortex electrons actually is a quite hot topic in the laser-driven nuclear physics, and we can show here that actually, if you are really interested in this topic, we can show there are a lot of developments in the recent few years about the interaction with the vortex electron with the nuclear excitation, or the vortex electron in the intense electromagnetic fields. And we saw here that, for example, the focusing of the from the Coulomb field to with the electrons for the electrons and also other kinds of interactions. And we can, if you are really interested, we can show. You can read a number of our recent publications. And here is a bit out of the main topic, but now I start with the recent experiments about the NIC, this process. And as I already mentioned, that this process actually, the first experimental evidence was LIPO in 2018, a few years ago. And in this experiment, iron beam established a target to create molybdenum 93 isomer, and then this iron beam established a secondary target and slow down and stop it here. And during the stopping process of the iron, at some point it will the velocity of the iron actually slow down, and then at some point it can meet the resonance condition of this process, and it reports in this experiment a very high probability of the isomer depletion about 10 to the minus 2 per isomer. And they claim this is the first experimental evidence of NIC because there is no other known nuclear process can provide such high probability. But however, our calculation followed by the experiment shows that it has more or less 8 or 9 order of magnitude smaller than the report excitation probability, and other calculation from other groups also more or less confirm our calculation results. So we can see there is a big gap, huge gap between the theory and the experimental result. And also there are other discussions from the experimental side. Is that the background analysis in the experiment is a bit it's not so clear because these two targets they are very close and they are more or less in the order of millimeter. So most of the ion beams can interact with to enter the detection area and make case cause a very complex background. And with this split, we in the collaboration with the group in the Institute of Modern Physics in Chinese Academy of Science, two new experiment was performed using in this type of the ideas that after the nuclear reaction to create the isomer, all of the ion being introduced into this about 40 meters of the secondary beam line to select the isomers we really need to interact with the secondary solid state target. And then we can see here this is the new experimental results. The first one we performed actually two experiments. One is in the this shows here with a slightly lower energy, but with this energy we don't have any relevant signal. But however, with the later experiment with increase the energy of the ion beam, we can see here we observe the new the excitation and the probability. We can show here that compared with the previous report one, it has a few order magnitude smaller than the 2018 experiment. And we would like to mention here that here is the probability of the leak from the theoretical calculation, and also these two curves shows actually the probability from the nuclear inelastic scattering. So we can see here actually the theory and the experiment fit each other very well. We can see. So in this sense, actually we can basically conclude that actually the leak observation is not so conclusive. So it's important that we have the conclusive NIC observation, and for the purpose of doing this, we have to have, it's better to we can have a well-defined initial and final states, and also the clear, very clear signal. And in the following, I show a number of cases that we can actually do in the very clean environment. For example, the nuclear clock case, which is actually this is not our main purpose. Not doing the nuclear clock is because we use this kind of nuclear is because the information of these nuclear levels, they are very we have very detail of the information of the nuclear level. So with this advantage, can have the control the experiment in the better way. So with this in this case, we are not exactly excite the nuclear from the ground state to the asymmetric state. Instead, we do in the opposite way of the isomer depletion, that we hit to a second the second excited state, and then from the second excited state we decay down to the asymmetric state. In this case, we can detect the asymmetric state, so we can confirm this kind of experiment. From the experiment, we can confirm this process happen. And with the calculation, we can see that the cross section in this case is not that bad. And with the value, with the detection of the asymmetric state, also combined with the SLA photons from the autonomic transistor and 30 nanoseconds delay of the gamma photons, we can as a combination, we can have actually a very clear signals in about 10 days of the experiments. However, I would like to mention here that actually from the nuclear calculation, you will always have a quite large uncertainty. We can show it here that actually from different models, actually you can have 2 or 3 types of different of the cross section we can expect. So in this case, what we can do is actually 10 days, or sometimes we can have 2 or 3 times more of the times. And another case we saw here also, we hit to another case that we use another case that is also similar. We hit to a higher energy and then decay down. But in this case, the production of isomer can also happen in the plasma environment, and then we started from the plasma environment to pending check to detect for background clean detection of the asymmetric state to confirm the happening of this process. And now I finished the part of the process of NIC, and then now I discuss the nuclear reactions with the astrophysical applications. And I would like to mention here at the beginning actually the nuclear reactions in the plasma environment. Actually, the nuclear reactions in the plasma environment. Actually, what's the problem? And you can see here that the general features of the nuclear reactions in plasma environment is actually the combination of the distribution of the ion, and also the penetration of the Coulomb barrier. And we can show here at the very general picture. And the main problem of the nuclear reaction in the plasma environment is the low energy reaction. So we normally don't have the such low energy experimental data for such low energy nuclear reactions, and always you can have need to have the extrapolation of the cross sections, and also the direct measurement of the cross section in the plasma environment is actually one of the challenge of the in this kind of it's minimal because we have mentioned already there are a lot of excited states and also a lot of other environments that which, for example, the screening effects, for example, the ions and electrons there, we can have the screen down of the Coulomb barrier of between the interacting ions, so we can have the enhancement from the plasma environment. But this is also, there are a number of issues. For example, here the interaction between the screening effect in the plasma environment actually depends on very much on this parameter we introduced here. This is the average Coulomb energy between the interacting ions and also the thermal energy of the ions. So this is the very key parameters very important. And then we can see here that if we reduce the temperature or increase the density of the plasma, we can see the coupling is from the V case to the strong coupling case, and then to the even the very strong case, the P-nuclear regime. And I would like to mention here is that there are a number of models that for the screening effects for the nuclear reactions in the astrophysical environment. But however, now it's no experimental data actually so far we can get really from the these screening effects. And I would like to mention here is that with the laser plasmas, generally with the high power lasers, we can actually with the temperature and then the solid state density, we can actually see there is some effects from the enhancements from the laser generated plasmas, and then we can also separate. Actually, we can distinguish the different models. For example, the widely used models in the astrophysical environment and also the quantum plasma models, we can separate actually the difference of the different model and to really test the model. And also another case that we have analyzed the direct measurement of the nuclear reactions in the plasma environment, which is similar to the case of the astrophysical environment. But however, we can see actually in the laser experiment, we cannot really reach the density of the in the star or in the core of the star. So we can here is actually we can only use the for example use the Newton source. We can have a very intense Newton source to so we can produce the Newton release isotopies, and also we can have the simulating of the R process in laboratory. We can see here actually with the condition we can achieve in the next few next 10 years, I would say probably we can, with the intensity, we can have we can more or less see, we can see how some events we can at the beginning at the same time to catch 3 or 4 newtons before the decay of the before the beta decay of the Newton release isotopy. And now I will briefly summarize my talk. And in this talk, we have already shown that the nuclear excitation by radiation catalyst can play important roles in the isotope depletion and the production. And the conclusive observation of this process highly demand, and there are a number of cases that we can offer the chance to manipulate this process and also provides the signal for the observation. And the high power lasers can offer opportunity for nuclear reactions in astrophysical environments. And I would like to thank you for your attention.
Thank you. Thank you. One short question, because our next speaker is online already for some minutes. So if some question we can ask after the next.
I would like to have many questions but unfortunately I was busy on something else. But I will take the occasion tonight to take the record of your lecture and listen. I'm sorry for my not being, but it's extremely interesting. And I would like to return to you tomorrow after this in the afternoon.
Okay.
But if you have
Professor Sobuti, can you share the screen? So next speaker is Professor Sobuti from Institute for Advanced Studies in Basic Science, Zanjan from Iran, who will be talking about self-confined quarks, a general relativistic perspective on strong nuclear forces. So if you kindly share your screen, the presentation.
Hello, Remo. Do you hear me?
Yes, we can hear you, but we cannot see
You hear me.
presentation.
Thank you very much.
Okay.
Should I begin?
Yes, please.
Do you see my slides on
Yes,
displayed or not?
Perfectly, yeah.
Okay. The title of my talk, Quarks and Nucleons, a general relativistic perspective on strong nuclear forces. The authors are myself with 5 others. I'm trying to begin with a very simple thumb rule. Quarks inside nucleon are not point particles. To comply with Heisenberg, they have to be waves. They have to have a wavelength lambda of order femtometer or smaller to fit into the nucleon. A wave of about 0.65 femtometer gives the energy h bar omega equal h bar kc equal 300 MeV. 3 quarks, 900 MeV. It's a very simple rule to get the emergent mass of the nucleons and hadrons. Very simple. Quarks are waves, and waves have to fit into the hadrons and nucleons. Now, you can explain this to any first or freshman physicist student of physics. Now, my second slide. 2 foundational questions in physics. There is no established wave function for hadrons or their constituent quarks that may parallel standard wave functions such as Dirac fields. There is a second gap. There is no definitive understanding of the physical nature of strong forces, except that they are strong and confining. Now, to be able to answer these 2 questions, we make 2 assumptions. Quarks as spin 1/2 particles are Dirac spinors. The second assumption, quarks as massive entities curve their own surrounding spacetime. We demonstrate that the general relativistic gravitation of quarks, not strong forces, the general relativistic gravitation of quarks is sufficient to confine them within hadrons while simultaneously allowing them to remain asymptotically free. we conclude at femtometric scales, strong and general relativistic gravitational forces are one and the same. These formulas we've taken from Miguel Alcubierre. I forgot which country of South America is. Spacetime, let's assume spacetime metric ds squared, alpha squared, dt squared, a squared, dr squared, and so on. These are the Dirac spinors that Alcubierre provides. This is a spinor, Dirac spinor, with a spin plus 1/2. The other below is the Dirac spinor with a spin minus 1/2. And according to our assumptions, to the assumptions I mentioned, up quarks or down quarks with a spin 1/2, we're presenting it as a Dirac spinor. And down with the spin down, again with the second one. Now, note there are two functions here, 4 functions actually. Alpha, A, metric coefficients. F is a function of R, G is a function of R, and we have to determine these 4 parameters. To do this, the 4 differential equations, they satisfy F prime equal omega plus m g, g prime equal 2 by g plus omega minus 1f. If you combine these two, you will get equation 2, the second differential equation, r squared g double squared, r prime, so on and so forth. K is a propagation vector. Omega is the frequency. M is the rest mass of the quark. These are energy momentum tensor components, SRR, STT, in terms of F and G are these. So these 4 coupled equations are our starting points. Equation 2 is a spherical Bessel function of order 1. It is not square integrable. A Yukawa amelioration is needed. To have Yukawa amelioration, with Yukawa amelioration, I mean to devise a scheme to curb the infinities. To have this, instead of real wave vectors, we introduce a complex wave vectors, k plus or minus I kappa. Kappa should also be of the order of fraction of femtometer. And make a transformation from radius to z according to these equations. That second order Bessel equation turns into this one, 5. This is also a modified Bessel of first order. The word modified is added to it. 5 is now the modified Bessel spherical Bessel function of order 1. We know its solutions. The solutions that will serve our purpose. One group, Fi and Gi, the other group, Fe and Ge. In terms of Z, these are given as this: sine kz divided by kz. Gi, k minus, k flan, and so on. Now, let's note the asymptotic behavior of these Fi and Gi. Fi and Gi are finite as r tends to 0 and are infinite as r tends to infinity. This Fi and Gi can serve for some internal radius. F external, G external have a different asymptotic behaviors. 10 to infinity at r equals 0 and 10 to 0 at infinity. So those linear equations which we have, the solutions should be a linear combination of these four, and such that the inner regions up to certain radius to use Figi, for the outer regions larger than R transition, use F external and so on. This F star F G star F times R squared is the probability density of existence of quark. Quark at position R exists, and its probability density is this curve. These are the internal solutions, and this is the external solutions. External solutions tends to 0 exponentially. This is what Yukawa amelioration does. Transition distance radius is of the order of 0.55 femtometer. Not exactly, but close to that. Now, if we go to these equations, solve them with what we did in the next two things. Alpha internal function of R is this monster thing. Note here, there are sinusoidal functions and hyperbolic functions, sine and cosine functions, and hyperbolic functions, cos, cosh, and shin. This alpha A. This may not show much, but let's see their plot of it. This is alpha squared, the metric coefficient. Let's look at it. Its maximum at the center declines to a minimum here, and then goes up and tends to 1 exponentially. This is A squared here, function of R. Again, maximum at the center, no minimum, tends exponentially to 1. Origin is an unstable equilibrium. This 0.97, it is a stable equilibrium. And we've named it charge radius. I mean, particle physicists have named it as charge radius. I'll explain. Gradient of this A squared, alpha squared, is almost a gravitational force. Quark cannot stay in this maximum because it is stable, it is equilibrium, but unstable. Gravitational force somehow proportional to the slope of this curve, push them to this way, up to this point. But then the slope changes, the forces turn inside. Before this 9.7, forces are rightward. After this 1.7, forces are leftward. So, forces on quarks. So this is the zone that quarks are driven to. That's why nuclear physicists have called it charge radius, because if they are here, they will manifest their electromagnetic properties strongly around this region. Let me read more. Alpha squared minus 1 is proportional to gravitational potential. Its descending slope is outward force on quarks. Its ascending force is the inward force. The two forces should balance each other. This is the root of von Loh's stability condition for quarks. I think published in early 19th centuries. There is no force on quarks. I'm reading this. No force on quarks in the vicinity of the charge radius, because the slope is 0 here. This gives them asymptotic freedom. But this rising slope, which tends to exponentially to 1, prevents them from escaping. No escape to infinity because of the exponential. Sorry, what is this? No escape to infinity because of the exponential decay of metric coefficients to 1, which means flat spacetime.
Could you please share your screen? Sorry, because we lost the screen share. Share the presentations again. Let's see.
Okay, go down.
Okay, we have
it. Okay. Now, how much energy, how much gravitational potential energy exists in this space-time? This curve is the distribution of the emergent gravitational energy inside nucleon, general relativistic. It is 0 at the center because there was no force there. You see, gravitational potential energy density is the square of this slope. Slope is force, and force squared is proportional to the gravitational energy density. That's why I have these words. Gravitational potential energy is 0 at the center, reaches maximum at this R. Particle physicists have named this radius as the mass radius of the proton. And the J-psi project of the Jefferson Lab shows that it explicitly states that the mass radius is much smaller than the charge radius. Anyway, this energy drops, potential energy, drops to 0 at charge radius here. There is no gravitational energy, and rises out to a maximum. So the gravitational energy goes up, down to 0, and again up. This second maximum is very minuscule, very small. This upper is 13.6. This one is 0.17. It's a very small one. If we had a quantum theory of gravity, I would have said gravitons are concentrated in this region, and a small cloud of gravitons concentrated on the very outer edges of the nucleons. Particle physicists for this phenomenon say gluons are concentrated in around mass center and have emergent mass energy, and there is a dilute cloud of gluons also in Jefferson Lab's findings, which I do not have in this diagram, but conclusion. Quarks are normalizable Dirac spinors. They are massive and curve their surrounding spacetime. To ensure square integrability of these spinors, we introduce a complex valued wave vector a la Yukawa. Assuming a static spherical symmetric spacetime metric, we find, thanks to the wave nature of spinors, as opposed to point particle feature of it, there is no singularity in the resulting spacetime. Inside the nucleon, spacetime is flat at the origin. Outside the nucleon is spacetime. The spacetime is asymptotically flat. There are two distinct equilibrium points to the spacetime: the unstable one at the origin and the stable one at charge radius RC. Quarks occupy the force-free environment of the stable charge radius. While asymptotically free, they are confined by the exponential decay of their wave density outside the zone. That was the first diagram, the first figure I showed you. Eventually, we have demonstrated a direct structural correspondence between our general relativistic model of nucleons and the experimental mass profile published by the J-psi 007 collaboration of Jefferson Lab. Far out a nucleon, this is for astrophysicists. Far out a nucleon, there are R-1, R2, R squared, r minus squared and r minus cube forces. The first one may be of interest. This one dies out, decreases much slower than the other two. The first term, r minus 1 term, may be of interest to those who may fancy to explain the Thale-Fisher relation, i.e. the flat rotation curves of spiral galaxies. We acknowledge that treating alpha squared minus 1 by 2 as effective Newtonian potential is a simplifying assumption that may draw scrutiny from general relativity purists. Nonetheless, if you don't accept this as a specialist, as a nuclear physicist, this work demonstrates that the general relativistic forces at femtometer scale is remarkably strong and capable of replicating the known features of strong forces. We will not be surprised to see the day that experts ultimately classify the fundamental interactions of the nature into two categories: the electroweak, which is already done, and the gravo-strong, which is waiting. Thank you for patience.
Okay, thank you. We have room for some short question if
Show the,
Yes, you have a question first.
show the room.
How you construct energy momentum tensor for quarks? Does it minimal coupling of Dirac field to gravity or not?
All we've done, this is our first work. All we've done is say that Dirac as a spin 1/2 is, sorry, quarks as a spin 1/2 are Dirac spinors. Secondly, quarks have masses and can curve their own space-time structure and get confined by themselves. That's what we've done. We have not gone through many details that particle physicists have come across, which is a different topic.
Yes, thanks.
Other question?
Any more questions?
Strange. I will be thinking about this, but I have to tell you that one of the last meeting I had with Abdus Salam in ICTP, he was proposing something very similar about strong gravity, and it will be interesting to think over. But for the today, I would like just to congratulate you and to have established in Zhejiang such a fantastic institution, which is just one of the few places on the planet in which everybody can go in the library even in the night time. And the splendid meeting that you have, and we are honored of the fact that your president and your established center have requested the entrance in ICRANet, and we will proceed accordingly. I still remember the day I visited you for the first time in Iran, when I was invited in Shiraz, where I was invited to give the Pahlavi lecture, and you prepare this occasion. Unfortunately, We never gave the Pahlavi lecture, but I have a pleasure to see today you still active in the memory of a great pastime. Thanks. And your experience with Chandra has always been present. Thank you.
Thank you very much. Remo, 1 point.
Okay, thank you. Let's thank
Am
speaker.
I online? Regarding to what you mentioned from Salam, singularity, let me add one sentence. You see, point particle assumption anywhere is in contradiction with Heisenberg's principle of uncertainty. If we assume that we have a mass point or a charge point or anything point, we assume that we can fix it at a definite place at rest. This violates Heisenberg's principle of uncertainty. In quantum mechanics, we cannot confine any particle, we cannot assign a definite space coordinates and momentum coordinates to anything. See, that's my objection about those singularities. All singularities you see in Schwarzschild, in Kerr matrix, in Kerr black holes, they all stem from the fact that at one stage, the gravitating mass is the point particle assumption in it. Thank you.
Okay, thank you. Let's thank speaker again. Yes. So the next
Thank you.
talk, let's prepare the. Which one was it? Here. So the next talk, you say last but not least, the yes for this morning session, the review of SRG Rosita All-Sky Survey result in the Eastern Galactic Hemisphere by Professor Marat Gilfano from MPA Garching and IKI Moscow. Please.
Do I switch it on or is it on?
It was on.
Okay. Oh, now it's on. So hello, everybody. Thank you, the organizers. Thank you, Remo, for having me here. It's always a pleasure to come to Pescara. I like ICRANet, and I must say I like this place so much I even come here for holidays sometimes with my sons. Right. So I'll speak about, we're changing gears, and from theoretical physics, we're switching to high energy astrophysics and to more observational data and some theories and interpretations. Is it?
No,
I have to do it manually, right?
Here.
Okay, good. I'll give just a very short introduction to eROSITA Spectrum Röntgen Gamma Satellite eROSITA Telescope. Just a couple of slides. It is a Spectrum Röntgen Gamma observatory, which actually
It has a long history. It started 1987 when I was a PhD student, and then it was closed once. It was a much bigger, much more different mission, and it was closed down in early 2000, and then reincarnated in 2007 in completely different concept. And it has present concept. It has two telescopes, which is Eurosita soft X-ray telescope operating up to 9 keV, and Pavlinsky Arctic Sea telescope operating above 5 keV to 30 keV. It was called after Mikhail Pavlinsky, its PI and creator, who passed away after the first year of operations, unfortunately. And it is Arctic Sea built in Russia with contribution of Marshall Space Flight Center, who did the mirrors. And they still, NASA works, Marshall scientists, they take part in analysis of the data. And Eurosita is a German build, and the bus, the satellite, it's Russian built, and it was launched from Baikonur, as you can see here, with a Proton rocket on 13th of July 2019. Few of us, well, actually quite a few of us had a chance to go there. It was a spectacular launch. I actually went there twice because the first attempt in the end of June didn't work. There were some difficulties, so it was actually taken back to the hangar and disassembled, reassembled, and on 13th of July it was successful. It went up. The plan was it would go to L2 point, which is 1.5 million kilometers away from the Earth, as you know, and would be moving on a very broad halo orbit with size of about almost 1 million kilometers as well. So got there in October, and as you see on the next slide, the main plan was to do all-sky survey, and in December it started all-sky survey. Unfortunately, in 2022, in February, Eurosita MPE team requested to switch Eurosita. It was a political decision. Scientists were not very happy with this on either side, in Germany and in Russia and in the world at large. But it happened, and SRG continues to operate in the interest of Arctic Sea Telescope, doing beautiful things like a deep scan of the galactic center. Some of you, like Remo, you were in Yerevan, and there were a couple of talks about this, about the beautiful Arctic Sea results, and now continues all-sky survey. So the guaranteed time for SRG was 6.5 years, which expired earlier this year, but everything is going by plan, so it was extended for another 5 years. It will be operating for another 5 years. And there were a number of attempts on both sides to switch on Eurosita back. It is in the safe mode, so, and we're checking telemetry, it's functional, to switch it back, but it doesn't work. It hits a wall of bureaucracy and something what I think is not good thinking. Anyway, and Russian Space Agency is prepared to switch it anytime. We discussed this many times. Yeah. So this is a bit of introduction. As I said, the plan is to do all-sky survey. The way it is being done, spacecraft rotates, making telescope axis making big circle on the sky. Rotation axis points at the sun, roughly, between sun and Earth. And this is sun, this is Earth, this is spacecraft, and the Earth and spacecraft move around the sun, and so that they the rotation plane of the big circle moves gradually, approximately 1 degree per day, and it covers full sky in 6 months. And the plan was to make 8 surveys in 4 years. As I said, it was Eurosita stopped, and 4.4 surveys were done. We expected to have average exposure of 2 kiloseconds, much deeper exposure in ecliptic poles, because all the scan paths, they would cross the ecliptic pole, and we have like 150 kilosecond exposure here, and we get maps like this. this, to me, it looks like an optical image, ground-based optical image, and it has a source density of almost 1,000 sources per square degree, but it is confusion limited, but it's, we can deal with that. Now, it's, it was posed initially as a Russian-German mission, and so the data, eROSITA data is divided 50-50, and it was decided that like this is galactic coordinates, the western galactic sky will be responsible, German scientists will be responsible for data analysis there and for publications there, and eastern galactic sky will be for Russian scientists to be responsible and to analyze the data. Initially, like in, you know, in before launch, after launch, we envisage a lot of collaboration there, and actually it happened. The first all-sky map was published together. It was a Nature paper in 1920, I think it was, led by Peter Predel, where the full sky map was published, where all the data were combined together, and we envisage quite a few more projects like this, but unfortunately it's now frozen. So now where, and I'll be talking about eastern part of the sky. I'm a part of the Russian consortium. Where we are, this is a landscape of all sky or broad narrow angle sky surveys in X-rays with different missions. This is area of the survey, very small pencil beam, and all sky is here, and this is the depth. It's not the full picture. There are now surveys by Chandra down to 10 to minus 17, but that gives a general idea. This is, so to say, a main sequence of sky surveys of different angles, and it's like this. Well, ideally, of course, you want to get here, but you need a lot of time, and you need a sensitive instrument. And why they all align along this diagonal here? Because every observatory has its resources. It has its sensitivity, and it has its time resource, time budget. And you either go, suppose you get, you know, you can get with Chandra, you can get almost a month, but you can spend this month looking at a very narrow field and going very deep, or doing much broader, a more shallow field. As I said, of course, you want to get here. It's very difficult. Now, this is where eROSITA now. It's not what we expected, like 25 times more sensitive than Rosat, the only previous and the only all-sky survey in X-rays, but still, we're good enough. We are 15 times deeper, and there are many funny, interesting things coming out. This is the all-sky map, which was obtained after the first half a year, after the first survey. And this is what I mentioned earlier, that it was a joint effort by Russian and German consortium, which I was active part. And yeah, so this is the sky. I'm not going to discuss this galactic plane, but I'm not going to discuss details here, but I still mention these are famous eROSITA bubbles and so on. There is a lot of stuff here. For people interested in the interstellar medium in the galaxy. I will be talking about compact point sources, and I'll be talking about this half of the sky. So all the numbers refer to the half of the sky. You can multiply them by 2 to get the full picture. So we have about 1.5 million of X-ray sources after 2 years of operation. This number, you may hear different numbers. It depends on where you put your threshold for statistical significance. You may go deeper. You can get, well, our catalog contains 2.5 million sources if we go down to below 3 sigma. But if you go down to below 3 sigma, you have more than 10% of false detections, which are just Poissonian fluctuations. It's actually very convenient to work in this band because it's all Poissonian statistics, actually, to quite good accuracy. This number, I don't want to have a sample where 15% of sources are false fluctuations. So this number, I chose a threshold so that only 1% of sources, less than 1% of falses are false detections. And of this, we have over 1 million of quasars. We have 240,000 stars, according to Gaia. We have a bit more because Gaia doesn't, these are Gaia stars which have parallaxes or proper motions. We have more, of course, because Gaia doesn't measure it for all stars in our galaxy. And we have about 30,000 classes of galaxies. Again, if you lower the threshold to 3 sigma, that would be almost 40,000. So we have, like, you can imagine, you have 1.5 million sources. But it's a two-dimensional picture. It's flat. You want to do something, to do anything productive, you need to solve 3 problems. You need, well, of course, you need multi-wavelength data. With just X-ray, you cannot do this. To use multi-wavelength data, optical data, infrared data, you have to do identification, because often in an error circle of X-ray source, there is more than one optical source or infrared source. So you have to decide which is the best candidate, most probable candidate. Then you have to classify the source. Often they are point sources. They are redshifts of 1, 2, 3. Optical sources too, and then you have to classify whether it's a star, a galaxy, or quasar, and if it's extragalactic source, or even if it's galactic source, you want to measure distance. And while we developed it, before the launch, we started developing, in Russian consortium, we started developing 2 approaches. One was machine learning based, a random forest algorithm as a first step, and then neural networks, led by Alexander Mesherikov. And then there were, I was favoring more physically motivated algorithm, because I said we know properties of stars, galaxies, and quasars, and they are different physically. We know what their spectra are, we know how they behave. But it turned out that machine learning turned out to be more efficient. So I admitted that, and now this is our main tool. Just a flash through a few examples how we do it. This is how we classify. You choose colors using optical, infrared, radio, X-ray. This is just one version. And red are quasars, these are galaxies, and these are stars. And you see they are separated, not without an overlap, but they are separated. And then if you use multi-dimensional, these are just 2 coordinates, but we fit into our machine learning random forest algorithm or neural network, we fit like 10, 15 photometric signatures of sources, and they do it quite well. This is another way, this is another set of coordinates. You can also, these are stars, these are quasars, these are quasars, these are galaxies, and these are sources of unknown nature. Just looking at this without any machine learning, you can say all these must be quasars. This is for Lockman Hall field. Also, for the metric redshifts, machine learning works much better than the template fitting, which also people using. And this is a spectroscopic redshift for some test field, and this is photometric redshift. And we do quite well. Of course, we have, as everybody else, we have some catastrophic errors, but they are not a very big fraction. We can do the same for classes of galaxies. It works even better because there is no AGN. So now this is some general introduction, and now I'll give more details on my more specific topics. I'll discuss, well, just show X-ray luminosity function of quasars, quasars as standardizable candles, and they're used for cosmological purposes. Compton-Fick AGN is a very interesting question. What is the fraction of those in the universe? Transient sky tidal disruption event, X-ray emission from stars, stellar flares, and SS433. But looking at my watch, I probably wouldn't get this far. So this is some subsample of eROSITA AGN redshift luminosity. As usual, this is a flux-limited sample, so this is instrumental, because we have some flux limit, and for nearby objects we go to lower luminosities, and for more distant to higher. And here is physics. I'm not going to discuss this. I'll just say, like, you can see cosmic downsizes, like in present quasars are fainter, and you can see, we also know from individual studies that sources above 10 to 46 are mostly blazars, but it should be topic of a different talk. I'll just show an example. This is our first attempt to do luminosity function. It's not that trivial, but it's doable, and we're doing this. This is a very small fraction of the data, just 1% of eROSITA data. We used DESI early data release, which covered some few hundred square degrees, and this is about 10, 15,000 quasars here, and this is their luminosity functions all the way up to almost, well, you can say we don't achieve much here, but still, I mean, we have potential to go to redshift 5 and a bit beyond. And actually, on the previous slide, if you look carefully, we detected AG and quasars at the redshift of 6 and beyond 6. Of course, it's a tricky business to select them and to do spectroscopy and so on, but we do that. So far, it's a very small subsample of eROSITA data, just as I said, just over 10 or 15,000 objects. No discoveries. This is solid line is IRT's luminosity function, LADE model, if you know what I'm talking about, and it fits what we see. Now, next topic. There is a possibility, which was discussed for probably over a decade, that quasars can be used as a standardizable candles, although they all have different luminosities, but they can use for purposes of cosmology. The point is that there is X-ray luminosity, optical luminosity, UV luminosity, and the relation between X-ray and UV luminosity is non-linear. It has a slope of 0.7, roughly, give or take. It was discovered, realized about 10 years ago. There is actually a whole sequence of Italian papers on that topic. Well, it's governed by accretion physics, just because when you change mass accretion rate, how your accretion disk changes, and X-rays are coming from corona. It acts differently. But it gives an opportunity to make quasars as standardizable candles. If you know Fx and FUV and redshift, luminosity is Fx multiplied by luminosity distance square, and UV is the same distance square multiplied by UV flux, and then you put here, and then you can measure DL just using two fluxes, because the relation is non-linear. But then, if you also have redshift, you can build a Hubble diagram, because you have a source, you measure two fluxes in two bands, you derive luminosity distance, and you measure its redshift, and you do Hubble diagram. There were attempts, they are not super successful so far, but it's workable, as I'll show later. Although I don't get it to Hubble diagram yet. However, to do that, we have to understand what is the scatter of that relation. And people were doing that in some smaller sample, like 100 objects, few hundred objects. We also need, as you see later, correctly determine the slope of a relation, because there are quite funny effects of the flux-limited samples. You also see it later. And we did it with SDSS eROSITA sample of quasars. We correlated. If you just correlate, we have tens of thousands of objects. We carefully selected redshift range, cleaned, and so on. I'm not going into the details. This is the end sample. This is the UV luminosity. This is X-ray luminosity, redshift. And this is a flux-limited sample signature. And you can see here, this is redshift distribution, which shows a range from 0.5 to 2.5, so that the UV band 2500 angstrom is within SDSS frequency range. You have that. There was two papers on this topic led by our PhD student Prokhorenko, very bright guy, by the way. And this is what we get. UV luminosity, X-ray luminosity, these are all the measurements, SDSS data combined. Well, I mean, we match, and then for each object we have X-ray and the SDSS luminosity. Well, you fit it, but the fit is a not simple thing. It's actually a two-dimensional maximum likelihood fit to the distribution of sources on LX LUV plane. We account for flux cuts and some number of other factors. It's a bit of math here, which I'm not showing. And this is what you get. This is the dashed black line. This is our best fit. You may, when you see it first, you say, well, look, points are here. Your best fit should go here. This is a mistake people did initially. But if you do, as I said, if you do it all accurately, then you get this is where it is, and it actually matches a few of the previous studies, more or less, give or take. We get a slope, beta, between Lx and LUV, which is 0.7. And so one of the points of this study was to measure intrinsic scatter, because you see there is a lot of scatter here, right? It is coming from variability because UV and X-ray observations were not taken simultaneously. It's coming from the flux measurement errors, which you could see here, especially for X-ray band is important, and also intrinsic variability. So we constructed the likelihood function, which separated these three contributions to scatter, and we measure intrinsic scatter, which is this number in logarithmic in log Lx. If you convert it like to linear quantities, it amounts to some 77% on X-ray luminosity and 11% in UV luminosity. This is the current status. You may say it's a big number, but well, if you look at the first Hubble diagrams built by Hubble, scatter was even bigger, but still didn't stop him from making right conclusions. And so we're working on this. We're now getting to DESI sample, which would be much bigger. There is 2,500 sources there. DESI sample would have, after selection, what we did already, would be over 10,000 sources. And then DESI observations were closer to Eurosito observations. So we remove the uncertainty of the scatter due to variability of the sources. We may get a better result. But even this is good, because if it's a Gaussian or symmetric, then, or, you can still fit the data and you get what you want in the end. Now, spectra of Eurosito AGN. This is a distribution of photon index. Photon index is the slope of E to minus gamma photon flux distribution of the energy. For some, it's not all, it's just some objects, some 6,000 objects in Lockman hole. This is gamma 2. It's a typical number when you speak about what is the spectrum of AGN, you say it has slope of gamma 2 or 1.9. This is same but for full sky, but in the hard band also gets gamma 2. But we see this tail here to the soft, like 3, even 4 gamma, and to very hard, like gamma equals 0. It's super hard, as you see on the next slide. Of course, here it's all gammas, all photon index measurements, they have statistical error, right? So statistical uncertainty will smear the real distribution. Now, this is a different way to present this data. So this is gamma photon index, and this is upper error for the gamma. And well, again, it takes a minute to understand this plot, but just tell you that this red line, everything below this red line have photon index harder than 1.3 at a 90% statistical confidence. Okay, so this is our sample for Lockman hole we're working with. Why is it gamma 1.3? In a way, it's an ad hoc number, but this is the justification or why we chose it. We believe that X-ray spectra of AGN and X-ray binaries are produced in Comptonization. IXP gave even more confirmation to that, just determining geometry that it's more like a cloud along the disk, above the disk, below the disk, rather than something jet or lamppost or something. So it's Comptonization. Comptonization cannot produce two hard spectra, unsaturated comptonization, which is taking place in all these objects. It cannot produce, these are very trivial simulations which a student can do. So these are spectra for different values of the comptonization parameter. This is what determines the slope. For different values of a comptonization parameter, and this is the slope which you get as a function of y parameter, comptonization parameter. And typically all the sources, they have y parameter around 1, not much bigger than 1. Because if it goes bigger than 1, then this spectrum becomes a Wien spectrum, which is completely different. I mean, and Wien spectra, we never see Wien spectra in AGN, right? So, and this is ad hoc boundary of gamma 1.3, and you see it never gets there in any reasonable parameter range. So this spectra, like if I go back here, this spectra cannot be produced by unsaturated comptonization in a standard paradigm. But photon index of gamma of around 0 is a signature of the reflected emission of the neutral medium. Here is like what we have, a disk reflection or torus reflection. And this shows two simulated spectra. This is just a very simple simulation, of course. This is a normal AGN with gamma equal 2. This is in new F nu units where photon index of 2 makes a flat spectrum in these coordinates. So this is gamma equal 2, just absorbed by some internal absorption. And this is red line. It's a spectrum of the reflection of the torus. And yeah, it gets photon indices harder than 1, close to 0, depending on the parameters of the problem. And so what we, a plausible theory, which I think is very plausible, is that, well, this is the standard picture of supermassive black hole, some accretion disk, some clouds, torus, and what we see in these objects which have very hard spectra, we don't see the supermassive black hole itself. You don't see the direct comptonized emission, but we see that comptonized emission reflected over torus. And these are what is called Compton-thick AGN. And so in that search, we were finding Compton-thick AGN, and like for, this is for Lockman hole. Well, if you don't know Lockman hole, this is a place on the sky where we have lowest galactic absorption. Like it's really, really low. It's like 10 times lower than anywhere else. And it has some size of some 10-ish degrees. And our PV phase, one of the observations, which I suggested, was we have a deep mapping of the Lockman hole region down to 10 to minus 15 flux. So now we're studying these objects individually. And by the way, on the whole sky, we have about 1,000 candidates, which have to be investigated. But now we can use this. There is an interesting question. What is the fraction of Compton-thick AGN in the universe? It is related to the construction to the nature of a cosmic X-ray background, to explaining its spectrum. And we did this for Lockman hole. And so the range is between 1% and 25% roughly. It's still a rather big range of possibilities, but when we do it from for a whole sky or bigger areas, we get much more narrow constraints. I'm not going into how we did this, but I mean, it's easy. I can explain in the coffee break. Among these sources, which we selected as Compton-thick AGN, we found a very funny one. There was it's a 1 megasecond XMM Newton observation of this source. And it has bright spectrum. It's like, I think photon index here is like 0.5. So it's reflected emission, but it has this feature, which is an iron line. And this is a quasar at redshift of 1. We fit, well, the standard spectral model or common popular spectral model is REXIL, which accounts for everything, reflection, iron line, KH, everything. And if we do that, we get a spectrum which is completely dominated by reflection, where contribution of a direct comptonized emission is very small, less than 10%. It has an iron line of the right parameters, and it doesn't require like, any extraordinary spin, something like 0.5 with actually quite large error, which is almost consistent with the very small spin. So what is this source? We don't know. In the literature, there are just few of this kind, because the problem is, so we have reflected spectrum which has been doing like this, and the supermassive black hole, we don't see supermassive black hole, but somehow we see reflection from the accretion disk. And the breadth of the line tells us that we get reflected, that the disk goes all this 3 RG and last marginally stable orbit, and we see photons reflected there because that's the only way to produce this line. So it's a puzzle. We're working on this and looking for other sources of this kind. Well, as predicted, I'm running out of time. So non-stationary phenomena. As I said, we do full sky survey in 6 months. Every 6 months, we come back to the same point. So like we had 4 or 5 measurements for every source on the sky. Here we have continuous light curves covering 2 years, and also inside this we have 40-second resolution. Well, we have much better resolution, 50 milliseconds, but we have 40-second spans with a resolution of 50 milliseconds. We found, when we were operational with Eurozeta, we found like every day we would find 3, 5 objects which change their luminosity by a factor of more than 10 as compared to the previous sky. It's, it's a big number. And then we started looking at the sources. Of course, these are stellar flares. Surprisingly, variable AGN, it's difficult for AGN to change luminosity by a factor of 10 in 6 months, because viscous, at least in conventional picture, viscous time scale is like 100 to 1,000 years. Tidal disruption events on the next slide. Gamma ray bursts, hostless transient, X-ray binaries. I'm not talking about this today. Tidal disruption events. We have a sample of 100 confirmed with optical observations, like we used about 50 plus of them were covered by Keck, and also Russian telescope, 6-meter telescope, 1.5-meter telescope, and so on, and also Spanish Canarian 10-meter telescope. Mean rate is about 1 in 100 for like mean rate, really mean rate. It's like mean temperature in a hospital. In 100,000 years, there is a couple of interesting facts, like dichotomy between optically bright and X-ray bright. We found 3 events. It's Van Velsen's paper associated with ice cube neutrinos. And this is illustration to what Zvi was talking about, saying yesterday. So this is a tidal disruption event in a dormant, unremarkable, absolutely unremarkable dwarf galaxy. If it's not that, we didn't know whether there is a black hole or not. With measuring this event, we know there is a black hole. Green is, by the way, ZTF optical, and this is Eurozeta X-ray, and this is Swift, and it behaves. It's a classical tidal disruption event. And also, speaking of TDs, we can do spectroscopy. They have soft spectra, and we can measure with the uncertainties of the X-ray spectroscopy. Of course, we can measure mass of a black hole and luminosity, and you see like masses are all less massive than 10 to the 7. It is, 10 to the 8 is a boundary when the tidal radius becomes smaller than RG, or 3 RG. And this is also very selection effect. As you go to more massive, the spectrum becomes softer. This is also what we see. And also they are many of them are close to the Eddington limit and even super Eddington. This is an interesting fact, which is related to the neutrino detections. If you give me 2 or 3 minutes, I'll speak about stars. This is completely different. These are much smaller objects, but there are many, many stars in our galaxy. And I'll just show example of studies of nearby open clusters. This is Pleiades. And this is a fraction of Pleiades stars detected in X-rays. This is 100%. This boundary is where convective envelope disappears. So stars earlier than F5, they don't have convective envelope, they don't expect to have X-ray emission, and they don't. We have just few stars here, but they are, we checked some of them, they are binary stars. And what we're having here as an emission, these are, they have low mass stars, later type stars, and this is what producing X-ray emission here. Not like A star do not make X-ray emission, I'm pretty sure. And then we have like, 100% of stars detected, and then here at later M stars, it falls down just because they become faint. It's a sensitivity limit. There is a very interesting, this is the main discovery so far of Rosetta for stars. Like we found, these are two open clusters, we found dichotomy. If you look at the quantity, what fraction of budget goes to X-ray emission, Lx to L ball, there is a very clear, very significant dichotomy on this distribution, and they differ by more than order of magnitude. So F and G and mostly K stars, they have low Lx to L ball. M stars, they have high, high meaning 10 to minus 3, which is 0.1% of the bolometric luminosity, but still it's 30 times higher than for this. We see similar picture in Hyades, which is another open cluster, and we knew that M stars are bright in X-rays, but this dichotomy is a very new thing. And it also, for this, we also have a difference in spectra, like coronae here are 2 times hotter than here, and we have completely different abundance patterns, but I don't have time to show this. Stellar flares, this is how we see them. Like we have some thousands, each point is one. This is one sky survey, and during a sky survey, we pass through the source 5, 6, 7, 10 times. And this is every passage 40-second measurement, separated by 4 hours, stellar flare. Another one, this is closer to ecliptic pole, and it had like 15 passages. There are very long flares, and these are all stars we checked. And there are very short flares, and there is a lot of variety. Now, if we look, again, this is Pleiades cluster, it's work done by Yasmin Nema, my PhD student. We see, this is again distribution of all the studied stars, all the Lx to L ball, and these are stars from which detect stellar flares. And they are all at high Lx L ball, and they are mostly all M stars. This is also, it's not well unknown, but this is a very clear illustration on 1,000 objects samples, how it works. Right, just one word about planets and then one more source. We have planets, and for some of the stars, host stars, we detect X-ray emission. And for some of them, it's like, this is 2024 work. Out of 4,000 plus stars with planets, 176, we detect X-ray emission from host stars. And for some of them, like a few dozen, it's so strong that actually planets is evaporated at a very substantial rates. For 9 planets, the rate is more than 10 to 11 grams per second, which means at this rate, well, there is a caveat to this, but at this rate, a planet would be evaporated in a couple of, Earth-sized planet will be evaporated in a couple of billion years. Of course, it doesn't happen because these rates are computed for atmosphere, not for the hard surface of the planet. But still, this is super important because when you have evaporation, you can study that ionizes gas, atmosphere, and you can study composition of atmosphere with JWST, for instance. And this is very important result. Finally, 2 slides. SS433. This is Rema. You remember this source from 70s, right? It was a unique source which showed precessing jets and iron line which was moving because of jet precession. This is how Rosetta saw it during all sky survey. It's a paper led by Rashid and with several people here, including myself. So this is what it looks. It's galactic coordinates. This is source itself. These are jets. The size of this is about a degree or couple of degrees. Interestingly, even here, you see galactic plane is here, so ISM becoming more dense in that direction, and you see that this jet is shorter because it's getting to, penetrating to more dense ISM. Now, This is RGB. It's here. Here is the size. Here's the size. So this is now RGB image, X-ray RGB image. Like red is soft, green is hard, blue is very hard, but there's no blue. So here is the central source. I must say that those jets which precess and for which we detect iron line, they are all inside here. Okay. So these are large-scale structures which we didn't see before, basically. It's more or less that graphically, we see them for the first time. And so the size, you ask about the size. So this way, it's the full size is 1.3 degree, which is 115 parsec. I can convert to light years, but there is a number, 375. This way it's 0.9 degrees. It's a bit shorter because this is where galactic plane is. The gas is denser, and it's 80 parsec. Now, if you look at the spectra, well, we see this, you know, this is hard, this is soft. Apparently, this is shocked gas, and this is non-thermal large-scale jet emanating from the system, similar on this side. And if you look at the spectra, we see thermal spectra here, with a temperature of 300 electron volts on this side, and they are non-equilibrium. They are shock heated 10,000 years ago. On this side, we have thermal emission, which is a bit hotter, but also not in a collisional equilibrium. But this stuff, green stuff, it's non-thermal, absolutely no features, and well, slightly different gammas. Well, whatever, absorption or whatever it is, but it's a different spectrum. Yeah, still, there are a number of questions. Like one of the big questions is why this boundary is so sharp. We still don't have an answer. People are doing simulations. This was published last year, and it initiated, motivated some few studies. And its final image, I think, slide. And this is again the same X-ray image in slightly different color palette. And this is radio. This is radio cocoon, the famous radio cocoon around SS433. And we see that it envelopes, like all X-ray stuff is sitting inside the cocoon. So I finish here. There are several topics, very important, clusters of galaxies, cosmology, but it wouldn't fit in one talk. I thought concentrate on this. And clusters, we detected about over 30,000 clusters. So thank you, I stop here.
Thank you. It was quite informative, rich in data and science. I personally have many questions and comments, so let's see.
So I think the last slide have already answered my question. My first question is that about the clusters of galaxies that you detect.
You mean this slide?
Yes, as extended sources, because it has a very large overlapping region with SDSS, and where you can have optical cluster counterparts, and we can do a lot of science, including the Union survey, where we can provide the weak lensing measurement of those galaxy clusters and to measure the X-ray, the temperature mass relation. The second question is that I think from the Germany side, they have already made some of the catalog public. So do you have some kind of a data policy that make the cluster catalog make it public?
Well, right now, we don't have a plan or timeline for releasing all the data. Right? Also, German side, we released only for 6 months. We didn't do that yet. We don't have a timeline, and it depends not only on scientists when the data may be made public. On the other hand, that being said, we're very open to collaborations. We're collaborating with US scientists, those willing to do it. We're collaborating with Chinese scientists, with European scientists. So basically, you know, if you have a sensible project, but which is not like, give me all clusters of galaxies. Of course, that wouldn't happen. Okay. But if you have a sensible project of some, you know, with some clear scientific perspective goal, just send me an email. We discuss them, and we can discuss the forms of how this can be achieved. We have certain constraints, we have certain consortium rules, but from my experience, I'm receiving such requests basically every month or so, and we often find solution which is acceptable for both sides.
That sounds very promising. Thanks.
Yeah, sure.
Yeah, thanks. A very exciting talk. So my question is about reflection-dominated AGNs. Are they too faint to observe them with XP? Because it would be really interesting to look at them in the polarization.
Well, I don't have. Well, they are not very faint because, for instance, like this plot here, these are all sky objects having signal-to-noise ratio larger than 5 in the hard band, which means they must be somewhere around 10 to minus 12-ish, right? Yeah, we basically, when we do this here, we did signal-to-noise ratio 5, meaning not just detection significance, but flux to error. I can check fluxes. I mean, I can check what is the brightest sources. I didn't look at from this perspective. In Lockman Hall, they are fainter because we had 10 kilosecond exposure per point. They're 8 kilosecond per point. So they are fainter. They're probably more towards 10 to minus 14 ergs per second.
Okay, thank you.
Okay, more questions?
I was impressed by this last view of SS-3. So,
if I can, what is the largest cluster which you have seen in your data? And what is the farthest?
Most massive or most distant, you say?
Largest in terms of size or mass, doesn't matter, yeah? And most distant, yeah. Yes.
Well, I remember I'm often showing examples of clusters of galaxies and to illustrate how easy they are to find in X-rays. And that example is 10 to the 15 solar masses, or 4 times 10 to 14, but around 10 to the 15 solar masses, virial mass. We probably have a bit larger. I have a comparison. I have a draft of ACT comparison with ACT. There are masses there. I can check it up, but it's probably we don't have much beyond 10 to the 15 solar masses. And the most distant one? Also, from what I remember, it's a redshift point. Well, that one, which was 10 to the 15, which I mentioned first, it has a redshift of 0.8. We don't go much beyond redshift 1 because the way, you probably know this, right? The way how it works, we are more sensitive to more nearby, even less massive clusters. Nearby meaning redshift 0.1, 0.3, 0.5, 0.6. And microwave, as the effect, is more sensitive to more distant ones and less sensitive to. So that couldn't fit my talk, but I have a graph where we have all ACT clusters and all Eurasita clusters, and they are ACT clusters do like this, and Eurasita clusters, they do like this. They feel lower redshift and lower mass domain.
So you had comments. Okay, in parallel to this machine learning that you said, also we have been developing the same thing for redshift and classification, the same sources. But I noticed that we have been using different methods. So you have selected some features, but in our case, we have already published in other set of data. We have used the different kernel size, so it finds by itself. It shows
different kernel size.
Yes.
What do you mean, kernel for what?
In the machine learning.
The machine learning algorithm.
So
yeah.
it finds featured by itself, and it shows very promising results. So it would be good if we have your data or collaborate.
Well, you can talk. So the leader, we have a subgroup in my AGN Cosmol cluster, quasars extragalactic astronomy group, working group. We have the leader of all these exercises or methods is Alexander Meshcherikov. You can find his email easily, or just get in touch with me. I'll give you his email.
Okay, thanks.
And I'm sure he would be interested to talk to you.
Okay, thanks a lot. You had question?
How do you get the redshift of the clusters from the optical photographs?
How we get redshifts of clusters?
Yes, those are X-ray. Is that
No, we don't get it from X-rays. X-rays, I mean, there is a handful of clusters where we detect iron line from eROSITA, because eROSITA has a quite funny sensitivity curve. It has a like 2000 square centimeters at 2 keV, but then it falls quite significantly, and at 5, 6, 7 keV, it's much smaller. It's all optical, and for clusters, we do. There are big galaxy catalogs with redshifts, with photometric redshifts for galaxies.
Red matter, it's red matter cluster, right?
Yeah.
As space.
Yeah. And then we develop a technique where we search, we analyze clustering of galaxies, so we define objects which we call clusters and measure their redshifts.
So the mass of the clusters, the mass is referred from the abundance matching red matter clusters?
No, masses which I was mentioning there from X-rays.
X-rays, the TM relation.
Yeah.
Thanks.
Of course, people in our group, they do that as well, doing masses actually from Weiss data, cross-calibrating things. But right now the accuracy of X-ray mass measurement, of course, it's not perfect, but it can give you an idea of how massive cluster is.
Okay, thank you. Let's close. You have some.
You have shown this beautiful picture of SS43, and really fantastic, especially the one that you go to the radio all the way in way in. Yes, incredible. And what can you tell? Do you tell? Of course, the reason we were very interested initially is the central object. Do you have anything new on that central object?
Not much. I mean, we have a spectrum, of course, but the problem is it's piled up. You see, it's a big spot. It's not because the source is big. It's actually all black hole, or neutron star, most likely black hole, and all these jets, they are within point spread function of eROSITA, so we don't resolve it. It's, repeat, this big round spot, it's just PSF and saturation, CCD saturation. Piling up, yes.
Very beautiful picture anyway.
Well, but this, of course, this is full of anything, free of anything. It's real distribution.
Let's prepare a presentation for the Boston meeting next year.
I'd be happy to do so.
To select a few key topics to focus next year.
Well, I think by the next year we have more results.
Yes.
You would need to give more time.
Okay.
Well, anyway, I always it's a stack. So new results coming, being produced, published, and you have just so much space for results, and just moves like this. So all the results, they get discarded.
Okay, let's close this interesting session and see you.
Thank you.
Thank you.
Sorry that I couldn't be there in person. And so the focus of this talk is the Fast Radio Burst project at the Northern Cross. So because of this audience and the very interesting conversations I've heard also in the previous days, I wanted to give some food of thought to all of us. This is mainly based on observations and what we have gained from our observations, but I basically want to give you ideas and questions more than answers with this talk. So yesterday we had the excellent reviews by Bing Zhang and Di Li, so I will not remind you everything about fast radio bursts, but just briefly, in order to get into the topic of my talk, fast radio bursts, as the name says, are very short events. They last some milliseconds. They're very energetic. Their energies can be 10 to the 36, 10 to the 41 ergs, and they're only observed in radio up to now. One very interesting thing, it was noted also last week here in China at the FRB 2026 meeting by Duncan Lorimer, their discoverers. In 20 years, we now know for about 4,000 fast radio bursts, which is about the same number as pulsars that we have discovered in 60 years. So of course, the project in this field has been very fast. And this is mostly thanks to, as you can see here, the CHIME Transit Telescope in Canada, which has discovered most of these objects. And one very important thing, I think it was also highlighted yesterday, is that within this population, only about 2% are events that show repeated bursts. So most of the events are just one-offs, and then a small fraction are repeaters. And so one outstanding question in our field is, are there one, two, or multiple populations of fast radio bursts? And so if we want to have a look at the possibilities, I will first deal on one-offs, which is something that's actually less close to what we usually do, because of course, if we want to understand FRBs, it's much easier to look at repeaters because we can see them more than once rather than observing one-off events. But still, of course, these were the first events that were observed, and still the majority of the events that we observed. So one can wonder if these come from similar events to what makes the population of gamma ray bursts, GRBs. And so, of course, here there's theories that predict that binary neutron star mergers or maybe even neutron star black hole mergers could produce this strong radio emission. Or the famous Blitzer theory that was elaborated already in 2014 predicts that this even a regular, let's say, neutron star pulsar can collapse, and in this collapse, the stellar surface behind the sort of event horizon is hidden, but the magnetic field lines snap with violence, and so this can turn regular pulsar into a bright radio, so-called blitzer. And here the accelerated electrons from a traveling magnetic shock will dissipate a significant fraction of the magnetosphere and produce the massive radio burst. One way that we could try to test the theory of whether one-off FRBs represent a population on their own is, for example, to try to connect them to GRBs. And this is one of the works that have done so. So they took all of the Swift GRBs and tried to look for spatial and temporal coincidences of the two events, of the two kinds of events. And actually, up until now, it looks like there's no coincident events. Of course, this is a very tricky question that I would like you to remember, because, of course, there's one problem in this case. So, for example, if we think of the whole sky and of the whole rate of events, it is, of course, hard to find two events that are coincident. But at the same time, it's also hard to think that a radio telescope, with its limited time on sky or sensitivity, can see all of the bursts, even from a single source. If there's a spectrum, we will be able to see, especially from the farthest away sources, we will be able to see the brightest events, not the tail of regular events, let's say. And that's why maybe we're just sampling the tip of this population, and FRBs are all repeaters. So going to repeaters, as I was saying, it's easier to work with them because they repeat and we can study them more closely. One thing that has emerged, it was also highlighted yesterday, is that it seems that magnetars can be a central engine for FRBs, because if we think, as Bing Zhang was saying yesterday, of their brightness temperatures, of the fact that the emission is so short and coherent, there must be a compact object here playing some role. And then, of course, if we think of the objects we know, neutron stars come to mind, and we all know and study very well the pulsars, which are rotation powered. The energies that are observed from FRBs clearly exceed the rotation power that could be coming from such neutron stars, and so the magnetic field power comes to help. And so magnetars can be a very good progenitor, not only for FRBs, but as was presented in this work, they can also be progenitors to GRBs. They can link a lot of different kinds of transients because with their energies, they can do, let's say, a lot of stuff. But then, and this was actually from Ming Zhang review in Nature in 2020, there's a wide variety of models that predict emission from magnetars or neutron stars or compact objects in general. And they can be divided into these main two classes. On one side, the magnetospheric models, where the emission comes from the magnetosphere of the neutron star, and the so-called GRB-like models, where there's an interaction with the surrounding medium that can be magnetar wind nebula and hypernebula, and then interaction with the shock in an upstream magnetized medium will produce radio emission. One thing I would like to highlight here, which will be useful for a following part of my talk, is that all of these models predict emission also outside the radio band. So, as I was saying, while we believe that magnetars could be easily a progenitor for FRBs, there's very different ways, again, that this can happen. And for example, the same progenitors, as we mentioned before, for one-off events, they could also be, in a way, progenitors for repeated events. Because if you think about it, the cataclysmic event, like a binary neutron star merger, an accretion-induced collapse, even a white dwarf collapse, or a white dwarf merger, all these events could potentially produce a neutron star. And in this case, of course, there might be ejecta, there might be some absorbing medium. So observationally, of course, this makes it very difficult to be able, first of all, well, this more from the theoretical point of view, to predict when this neutron star will start being active as a radio emitting magnetar, let's say, or source in general. On the other side, observationally, if there's a lot of material that still surrounds this neutron star, the radio emission will be absorbed, in particular the lower frequencies. So at some point, we might be able to see the higher frequency coming through this material. And this is something that actually we did with our observations. We tried to target the site of the gravitational wave and short GRB event 170817, trying to look for a possible remnant, so a very young magnetar that had happened and that could be the progenitor of a fast radio burst. But we didn't detect any emission in this case. But as you can see from these predictions from Anthony Pirro, of course, the age at which the radio source might start emitting or being observable in radio are quite varied. One other messenger that could give us some answers, and this is in particular if we want to compare models that are magnetospheric from outer magnetosphere models, so wind, let's say, models, is the possible emission of neutrinos. There's two predictions mainly for the generation of neutrinos. So in the case of a thermal shock with acceleration at the shock, there could be ions. And so the theory predicts that there might be photohydronic processes that could create neutrinos. Here in this work, they actually show that probably it is still at a level that's hardly distinguishable by current instruments. And indeed, there was a search in IceCube data. It was actually a stacked search of all the possible coincident events, again, to try to look for neutrinos, and this was yet unsuccessful. But there's also another prediction, and again, this is another flavor of the outer models. In this case, it doesn't matter what the central engine is. We have a sort of accreting system where we have a hypernebula and a hyperaccreting system, so systems that are above the Eddington limits. And in this case, at some point, so outside the magnetosphere, if the jet points towards us, we could see radio emission, so outside the accretion area. And in this case, again, there's predictions that neutrinos could be produced, again, via hadronic proton-proton reactions and photohadronic interactions. Here, in this case, the predictions are that actually there could be contributions to the background of neutrinos that is observed. And this is something that we're also going to work on now is a participant in KM3net. So that's something that can be, again, tested against predictions. And of course, I think you all know of this event. A regular galactic magnetar had a sort of FRB-like event. This was very peculiar because there was a forest of X-ray bursts just happening on the days before, and then on starting on April 24th of 2020, and then on April 28th, a single burst, actually, let's say a sort of a regular burst in X-rays, was accompanied by emission in the radio. Now, this changed in a way. I mean, I've said that magnetars are believed to be the culprits of fast radio bursts, but at the same time, given the population of magnetars that we know of in our galaxy, which is about 30, they're sort of middle-aged, only 5 of them emitting radio, and we've never observed similar events. People tended to believe that, of course, these highly energetic events could only come from a newly born, very energetic magnetar. So this was an event that made us change perspective a bit. And as I said, this was a simultaneous event. So again, this is, as prediction said, of radio and X-rays. Here, if you see it in the so-called transient phase space, where we have duration of events and spectral luminosity, this event was actually very close to the energetics of regular extragalactic FRBs, even though it was a few orders of magnitudes below the typical energies of luminosities of FRBs. And so people are struggling to define this as an FRB. Also, in this case, it looks like the progenitor magnetar could actually be a source of repeated FRBs, but it was actually only observed once, except that we actually saw some more bursts. Yesterday, the fast bursts were presented. These were the first 2 that were observed by Westerbork after the close to fast radio burst. And basically, it makes it look like there might be a sort of, sorry, these were the other 2. It makes it look like there was a continuum. There is a continuum of range of luminosities that can be covered by radio bursts. And so what makes an FRB, what doesn't, is still a very open question. This was another work that we were involved on, which had a similar result. So there was the other magnetar that shows radio emission. Here you can see the X-ray profile light curve, and here is the X-ray profile. And there was an X-ray burst followed by 2 radio bursts. Here the energy is still below the rates that were observed for SGR 1935. But again, it's to testify that there seems to be a wide range of radio emission in millisecond duration. And so again, it is difficult to understand whether this is the same the same mechanism all through the observed characteristics. And so here is one first consideration that one of the things that I think we need to do right now is to look for other probes, either in the multi-wavelength, multi-messenger regime, or very close by candidates in order to try to understand what's at the origin of FRBs. And here, let me get to observations and to what we have been working on. But first, an introduction to the instrument. So this is the Northern Cross. It is not actually a cross, it's a T-shaped array that's located near Bologna. And here you see the north-south arm and the east-west arm of the Northern Cross. Here is a clearer picture on a clearer day. The Northern Cross, as I said, is the oldest Italian radio telescope. It was thought of originally in the late 1950s under the supervision of Professor Ceccarelli from the Institute of Physics of the University of Bologna. And then it was opened in 1964. And the Northern Cross conducted a number of observations in the 60s, 70s, and 80s, and even a catalog of radio pulsars led by the late Nicky D'Amico. But then it became sort of obsolete, and it was not more in use in the late 90s. However, early in 2010s, it was reopened for space surveillance activity, so space debris follow-up. And finally, when the FRB science started to become more popular, we also decided that this could be, just like Molonglo was in Australia and CHIME was becoming in Canada, this could be a perfect instrument for fast radio bursts. Observationally, just to explain this to you, when we look for fast radio bursts, because we know right now that they come from outside our galaxy, we expect to be able to see them all over the sky. And so a single dish telescope, which has a small beam, can only point to some directions and only for some time. While an instrument of this kind has a wider beam, it can observe for longer time on sky. And so it's the perfect instrument to look for new fast radio bursts. Here is just a shout out to the team. Our PI is Gianni Bernardi. I'm a vice PI. And here also a shout out to two mentors, two people that made it possible actually, because they really believed in the project since the beginning, Professor Setti and Marco Tavani. Here's the technical part of the team. And these are the students and postdocs that we hired in the recent years and some external collaborators. So these are some technical details about how the Northern Cross works. Basically, the full north-south arm. So the first refurbishment only addressed the north-south arm of the Northern Cross and only some cylinders. So the full north-south arm is composed of 64 cylinders, but at the beginning we only had 6, then 8, and now 16 that are giving us more and more collective area. And here is just a summary of our first results. Of course, our first light was directed towards the first repeater that repeats periodically. This is called 180916. And this was sort of the first choice for us as for observations, because it's a source that's periodically active. So we know when to point our telescope at the sky in order to see it. And these are our 3 first detections. And here's a summary of the first campaign on other repeaters, which, however, did not give detections. One thing that I would like to stress about is that even among repeaters, we don't have the same activity levels. So some repeaters have only repeated twice. Some other repeaters have been active, very active for some time, and then they stopped. And as was mentioned yesterday, FAST managed to observe some repeaters with rates of 700 bursts per hour, of course, down to their sensitivity. So one thing that we try to do is to characterize activity periods and activity spectra of these fast radio bursts to try to understand what triggers their activity and why some repeaters are more active. There's only 2 repeaters, actually 3, let's say, that have been basically always active since they were discovered, while most of them have had some activity phases that then disappeared. Here is our first survey project. So since CHIME was already out there and doing wonders in the FRB world, of course, we had to find our own niche. In this case, we pointed at 7 nearby galaxies that were selected based on their star formation rate. And this means that we were targeting galaxies where we expected to have magnetars, like the ones we have in our galaxies, or the ones from core collapse supernovae, and maybe even younger sources, to try to understand how common they can be as a progenitor of regular fast radio bursts. And here you see the final plot that we obtained from this work. There were no detections that we could definitely pinpoint to those galaxies. And this, combined with other literature results, gave us a rate of less than 0.25 bursts per magnetar per year, which means that in a way, we do not expect this as the most common formation channel for FRBs. So this means that we disfavor the fact that magnetars, such as the one that did the galactic flare, should be the progenitors of especially some of the hyperactive repeaters. And this was confirmed by our later study. Here, in this case, we targeted galactic magnetars to try to see whether actually we could observe radio bursts, either with similar fluencies or lower fluencies, but still to try to make the connection. And again, no detection, in this case, in more than 500 hours, which again lowered even more the rate of bursts that we expect from magnetars of this kind. So both of our works in this case disfavor a population of core collapse supernovae magnetar as the most likely progenitor for extragalactic FRBs. And we, as I was mentioning before, we do not only do surveys, but we also do targeted observations, mainly towards known repeaters, and in particular to active repeaters. And here is one, as I was mentioning before, this repeater has been active for almost 1 year after it was discovered. And this was in 2022. It's been silent, quiet after that. So this was a very interesting case. And our results, in this case, that we compared also with other FRBs, they sort of show spectral flattening in the rate of repeaters with growing energy, which is something we interpreted in a way that seems to connect repeaters and non-repeaters as a same population, because here you can see that at the highest energies, we expect to see a flattening of the index, which means, a steepening of the index, which means that we expect to observe many less events at higher energies. And of course, again, if you project it to further distances, this means that we don't expect to be able to see repeated bursts, for example, from faraway sources. Here are some of our continued programs. We're also monitoring the Crab pulsar, also in relation to fast radio bursts, because we know that the Crab pulsar has giant pulses. And so it is interesting to study the connection, because as I was saying, it looks like between giant pulses, magnetar events, and FRBs, there might be a continuum that's worth investigating when one is studying emission mechanisms. And finally, I mentioned that we use the Northern Cross as a facility on its own, but we've also used it as the base for multi-wavelength campaigns. And I told you that most of the models that predict FRB emission, they predict also multi-wavelength emission. So we use the Northern Cross and the Italian dishes for our campaigns in together with optical and X-ray telescopes. These were the results of our first multi-wavelength campaign. And just to give you an idea, what we saw, for example, with XMM Newton in the X-rays, was that we didn't detect emission. So we have an upper limit to the burst luminosity of 10 to the 45 ergs per second, which means that there should be an energy ratio from X-ray to radio of about 10 to the 6. At the time of these first observations, we could only compare with the giant flare of a magnetar in our galaxy, SGR 1806, and the energy of this burst was about 10 to the 46 ergs. So basically, our observations could already exclude that such a giant flare can be related to FRBs. After the galactic magnetar was observed, in that case, we observed a different fluence and a different energy ratio. So we were able to do more comparisons that I will talk about in 1 minute. And here you see that in our second round of observations, we also had simultaneous optical observations. And there's a hint here of a burst that was observed in optical very close to a radio burst. What we have found, because again, we haven't found coincidences in optical and radio, is that we can exclude some of the models. So for example, the models that predict that a very bright optical burst should accompany the radio burst. But what we have found with our observations is that until we have observations simultaneously of different optical telescopes, we will not be able to know whether there's a radio event, an optical event connected to the radio event, because it looks like they are not simultaneous, which is something different from what happened in X-rays. In the case of X-rays, I'm sorry that I'm going back and forth, but here you see a ratio. And in the case of the galactic magnetar, the ratio was sort of 1 order of magnitude lower. So we're still, we cannot still probe that kind of emission with current X-ray instruments, because XMM Newton is the best. And here we do some predictions on how long it will take. Basically, with the current X-ray instruments, it might be hard to find an X-ray counterpart. And I see that my time is almost running out. So just to speak a bit of the recent updates, we got funding from PNRR to refurbish not only finish the refurbishment of the north-south arm, because as I said, we only used a part of the north-south arm for now, but also the east-west arm. And this will be combined with multi-beam capabilities and real-time processing, which will basically make us very similar to what CHIME does. Plus, we will have a 10,000 square meter of collecting area from the full north-south and 20,000 square meters from the east-west, which will give us very high sensitivity in a very big part of the sky. I'm not going into more technical details. I will say a bit more in a bit. Another thing that I wanted to say is that thanks to this funding, we also were able to participate to the CORD project, which is the Canadian follow-up, let's say, to CHIME. Here you see CHIME, the transit instrument, and here's a rendering of CORD, which is going to be 500 dishes, with the idea that CHIME plus CORD plus 2 so-called out-trigger sites will not only discover a lot of FRBs like CHIME is already doing, but they will be able to pinpoint them to very precise locations in the sky, which, as we heard yesterday, is what is needed if we want to use FRBs as probes, but not only, if we want to see their sites and their emission regions. And here you see a graph that shows how CORD will be one of the instruments that in the upcoming years will see most FRBs and will also be able to localize them very precisely, which will give it outstanding capabilities in this field. And as I was just mentioning, localizing them means that we can trace the baryon, the gas contents in the host galaxy, the IGM medium, and the Milky Way, which gives us a handle and a new probe on cosmological issues that have been there for a while. What the Northern Cross can do in combination with CHORD is that, of course, we have slightly different skies, but also a superposition. And as the source can, the Northern Cross can also point, we can follow up sources that are discovered by CHORD with the Northern Cross, so get more sensitivity on them. But also we can have the Northern Cross being the trigger instrument to give information to CHORD of possible new sources. And here is a scheme of a possible strategy of observation that it will give us at least one burst every 2 days for the north-south arm. And if we combine it with the east-west arm, this will be at least one burst every 3 days with a high sensitivity. And so about 300 bursts per year from the Northern Cross. Just briefly, we have also got some other facilities in Italy, the single dishes Sardinia Radio Telescope, and then Medicina and Noto. And with this, we can cover a range of frequencies that much higher than what the Northern Cross can cover and the other instruments. So we can use our instrument as a big spectrometer, let's say, and we can characterize energetical properties of the sources. And finally, continue on our multi-wavelength follow-up. So this is my summary. The Northern Cross, which was the oldest Italian radio telescope, is now capable of observing FRBs. And this is an owned instrument, which means we can actually observe FRBs all the time when the Northern Cross is operational. And we've built an enthusiastic group around it, which we are proud of. And we can run observations all the time, as I said. With the addition of the other Italian antennae, we can cover soon from 190 megahertz with the LOFAR station in Medicina up to 100 gigahertz with SRT, which will give us a vast spectral coverage. And we've already built in these years a synergy with optical and X-ray telescopes that will hopefully at some point give us a detection outside the radio band, which is definitely one of the keys, I think, to shed light on the emission mechanism. And then, as I was saying, we will have a survey instrument, but we also have a synergy with the future flagship for FRBs, which will be CHORD. So the future is bright for FRBs in Italy, I think. And this was it. Thank you.
Okay, thank you, Maura. So we pass for questions. Please, Professor Fini.
Very, very beautiful. Missed the first part of the talk, but I will at the record and update myself on the first part. But if I understand correctly, you have been also in China with Dili. Did you start the plan? You mentioned.
Yes, I'm not hearing everything properly, but I think you mentioned plans of collaborations with the Chinese FRB groups and FAST.
Yes.
Yes, so we are very enthusiastic to have started this collaboration. It was actually mainly, I guess, thanks to Remo. And of course, the Chinese have the most sensitive instrument in the world. And we heard about it yesterday. And FAST has the highest sensitivity, but it has some limitations. One is sky coverage, of course, because it cannot be moved, so it cannot see the whole sky. Yes. And the second one is that until now, it can only observe at one specific radio frequency. So if we want to do the spectral coverage, like I was describing now, it is very important to have other facilities around the world. So they were very happy to collaborate, and we are very happy to collaborate to try to characterize the full spectral energy extent of FRBs to try to understand the emission mechanisms behind them.
Yes, I hope we will have an answer, because we jointly apply to fund to the Italian foreign minister. If you have any news, let me know. And if I will have any news, I will let you know. But I think this project is fantastic to see the multi-wavelength growing thanks to your. Very, very important and very impressive. Congratulations again, and we plan to collaborate within ICRANet with you and with all the other colleagues internationally. And I've seen the beautiful expansion in Canada. That also is very impressive. After all, we gave them a Grossman Award already, and this is very nice to see that they keep going up with leadership. Congratulations again, and let's stay in contact. Bye.
Yes, yes, thank you.
Thank you. Other questions? Okay, there seems to be no questions. Thank you very much again.
Thank you.
Now we can pass to the next talk, given is by Sergei Grebenev. Can you please?
Okay. Do you see? Do you see my talk?
Yes, we can hear you.
Okay, I will start. I'm Sergei Grebenev from Space Research Institute, Moscow, and I will present my computations of radiation spectra from high temperature plasma in a thin layer, and I will show several new results, which the most important of which that the quantized spectra of such plasma depend not only on its optical depth and electron temperature, how it is generally assumed, but also on its density. And the second main result that the intrinsic spectra from such high temperature plasma are enough to explain the black bodies, the canonical spectra from black holes in their accretion state, low or hard state, and it is enough. No any external seed photons are needed to support quantization and explain the spectra. The figure you can see here at the left show this result in much slower view. You see the bottom curve shown here. It is the spectra produced from a seed photon of black body with temperature 10 electron volts, and you see that in fact this is the just standard approach to quantization, that there is a quantization of seed photons, because the density of these curves is very low. It is 10 to 14 centimeter minus 3, and you see the slope of such spectra in X-ray band is photon index 1.6 and exponential decay. So it is a typical spectra of Subnov X1 X-ray and X-ray nova in such a state. But if we increase the density of the plasma layer to the densities are typical for black holes from inner regions of accretion disk, these are about 10 to 18, we see that the slope of the spectra changed drastically, and at densities about 10 to 19, the contribution of soft photon is negligible. This is just intrinsic spectrum of hot high temperature plasma of such optical depth and temperature. There are two different, no, I will show this later. And now I will remember some important fact of history, of quantization history. The first is that the observed exponential cutoff at high energy of the power law spectral black holes points on its thermal origin. And this means that such spectra are produced in high temperature plasma of central region of accretion disk. You see the idea of how to produce such spectra were proposed in papers by Early 75, Shapiro et al. 76, and later Sunyaev-Trumper 79 and Sunyaev-Tatarchuk 1918, which show that quantization of soft external seed photons can explain the formation of the spectra and found the analytical solution describing such spectrum. You see the picture, the first comparison of such result, such analytical result with the first measurement of the high energy spectrum of Cygnus X1. These were obtained from balloon flight in 1969. You see, and this is a good agreement. And after such a work, a paper, the main idea of describing the spectra, hard spectra of black hole is that this is quantization of seed photons. The more data of more high quality were obtained by Trumper with balloon flights carried out by IIT, Tübingen, and MPI Garching groups during 75-77, and this is a real comparison with Sunyaev-Tatarchuk formula describing the hard X-ray spectrum, and we see that the agreement very good, but the only things that the temperature of the plasma is rather small, 27 keV. Usually we observe the Cygnus X1 spectra in much more high temperature state, and the similar result we obtained by Granat during observation of Cygnus X1 in 1990, 1991, and the plasma temperature was approximately twice as higher. The direct analytical solution describes the spectrum much worse. You see the dotted line here, and this is best result which was obtained. But we show that this is mainly connected with the analytical approach, approximation of the spectrum, because if we compute the spectrum in the same assumption, but with fully relativistic approach of Monte Carlo method, describing the spectrum in not very high optical depth of the plasma, we have obtained much better agreement, and this was accepted for long year, and many papers were published on this different approach, different variety of such a result for different sources, and the conception of soft seed photons quantized in the high temperature plasma was 50 years already in the literature and the, our understanding of this physics. The seed photons which need force quantization, there were different sources proposed. For the first, this is photon from outer part of the disk, which is cold, dense, emit like a black body, and some of the photon from this cold part are and penetrate the high temperature plasma in the inner region of the accretion disk. And this is the model of truncated disk, which describes the different state of the black hole source by changing the boundary between the inner high temperature plasma region and the cold standard Shakura-Sunyaev disk, and if the radius of this boundary is high, there we observe the hard state of source in the hard state, but if the cold disk approach to the black hole very closely, we see the
soft state of the source, and you see the different spectra, how were measured by different really observatory, and this is our understanding of this phenomena. The other models, this corona model, when the soft photons are produced by underlying cold disk surface, emitting like a black body, but these photons penetrate in the corona, in the hot corona, and componized in this corona. There are also several papers which devoted to synchrotron and synchrotron photons, which may be produced by hot thermal or relativistic non-thermal electrons. There are, you see, the afters of this work, and there are very interesting results we obtained in this work. But now we decided to solve Compagnie's equation. You see the equation shown here, and computed the intrinsic radiation spectra of such a plasma. This is a layer of the plasma, high temperature, semi-opaque with optical depth in Thomson scattering about 1 to 3, and this is we assume that this cloud layer is located in the inner zone of accretion disk. In compare the result of our computation with the observed X-ray spectra from several well-known accreting black holes in their hard closed state. Normalization suggests that the circular region between the radii 3Rg and R1, this is outer boundary of hot region. This is about nearly 50 Rg. Rg is the gravitational radius of the black hole, and we observed such a circular region from in the perpendicular direction from the top, and assume that this source is located at the distance of 2.5 kiloparsec, like suppose X1 located. The computation were based on the computer code developed by me and Sunyaev in 2002 to investigate radiation spectra forming in spreading layer of accreting matter over the surface of neutron star. The code was slightly adapted for the current problem, but it is still non-relativistic, and now we developed another approach to produce a relativistic code. The spectra are formed under combined action of Bremsstrahlung processes, emission and absorption, and Compton scattering. The most important that our estimates show that the electron density should be very high in such a plasma, about 10 to 18 or 10 to 17, but not smaller centimeter in cube. In most cases, we consider the black hole to be 10 mass black hole, and other parameters are shown here. The typical spectra is shown here. You see that this is computed spectra, blue solid line, and you see there are several regions where are responsible for different part of the spectra and different physical processes. In the A region, the absorption, Bremsstrahlung absorption is very strong and produce the Planck spectrum, Rayleigh-Jeans spectrum in this part at such low energy. In point corresponding to frequency mu1 is where the absorption depth of the plasma become equal to unity. but the absorption is still work because there is Compton scattering, which lengthens the free path, the path of photons, and due to this, the probability of absorption is higher than in the single act. And you see what the spectrum is for pass below bottom from the Planck spectrum. This is Planck spectrum for the temperature of the plasma, and with the same parameter. This is the free or Bremsstrahlung spectrum, assuming that the plasma is optically thin. And you see that, to our surprise, that the spectrum here is in the region, ultraviolet region, is very close to the Bremsstrahlung spectrum. At frequency in the range C, the Bremsstrahlung absorption is very small, is negligible, and we just see the Bremsstrahlung photon emitted by plasma and undergo some Comptonization, some Compton scattering. And Comptonization is really work starting from frequency mu2, but in this region, in region C, the effect from Comptonization is small because it is proportional to frequency of photons. And the real effect from Comptonization is visible here in the region D. We see that the real spectrum is much flatter and extends to higher energy in comparison with the typical Bremsstrahlung spectrum. The parameters are shown here: the temperature 50 keV, the density 10 to 18 centimeter cubes, and the optical depth is 2, and external radius is 50 Rg. To our surprise, when we compare such spectrum with the observation of several black holes, you see Cygnus X1, GRS 1758 minus 258, and the 1E source, great annihilator. We see that the spectrum which we computed very nice agree with the observational data. In fact, we only slightly changed the external radius of the hot region and slightly changed the optical depth and the temperature, only less than 10%. All the spectra are really described by nearly the same plasma with nearly the same parameters. This is a very nice agreement, and it is show that in fact the obtained radiation spectra are computed correctly and correspond to real physics of the phenomena. Interesting to note that the spectrum with the X-ray photon index are extended to unvariable shape to very small energy, to ultraviolet and then to optical and infrared band. And only at energy smaller than 1 electron volt, we see what the spectrum converted to the Rayleigh-Jeans spectrum. It is very important, and I will show why it is important. Is it possible to obtain the spectrum of desirable slope and shape by changing the parameter of the plasma layer? Yes, we show here. First, we investigated the dependence of electron number density on the shape of the spectrum on electron number density, we see that really on density only normalization is changing. This is the same multiplied by such combination to show that in the exponential decay the lines are parallel, and this is really the normalization depend on density of the plasma. And it is easy to understand because the intensity of Bremsstrahlung photons are determined by density in square, and if we fix it the optical depth, then the dependence is only on density in the first degree. But dependency of the shape of the spectrum from the temperature and optical depth is different, and it is more shape is changed strongly, and then the temperature is higher. We see that the spectrum is become flatter, and there is saturation at such high temperatures, and the optical depth when increased to 3 and 5, we see again the saturation of the emission is corresponding. This is a swing component which are P and corresponds 3 kT exponential decay. It is easy to reconstruct the spectra using the analytical solution. Just using the Syunev-Tarchuk formula for the spectral formation in a photon layer of bicomptonization of soft photon with fixed energy, shown here. We use this spectrum and convolve it with the Bremsstrahlung spectrum to find the spectrum produced by comptonization of Bremsstrahlung photon. This is the formula, and here the comparison of the analytical spectra shown by blue line with the spectrum computed from our direct solution of the Compagnie's equation. And you see that only here there is small deviation between the spectra, and this is connected with some different approach to distribution of very soft photon, which in our computation it is the uniform distribution, but in Syunev-Tarchuk this is slightly more concentrated distribution of soft photon to the central plane of the disk. But in general, it is very good coincide between the analytical and computed decision. There is a different choice of the smallest Bremsstrahlung photon which participate in the comptonization, because we know that there is a relay genes cut off of the spectrum of Bremsstrahlung spectrum due to Bremsstrahlung absorption. It is difficult to believe that the whole photon inner zone of the disk is thermal and homogeneous, how we assumed initially, and we consider different distribution of temperature and density of the plasma over the hot inner zone of the disk. You see the temperature is depend on radius like this expression, and we see that the blue line, it is the integrated spectrum, and these two dotted lines, the spectra of inner circular region and the outer circular region between the zone, because we divided the zone in 5 circular region of equal width in radius, and with different temperature. You see the most hottest region and the temperature and the region with smaller temperature. When we combine them, we receive the integrated spectrum. And this is comparison of the result of spectrum with the spectrum of single temperature disk. We see that in general it is very good agreement between the approach, different approach. This is the same, but in this case the temperature is constant, 50 keV, but the density changes according to this equation, depend on the radius like this. And we see again that the different zone give some contribution, a little different at the smaller energy and at the high energy, but in general they are go in parallel in the most part of energies and of the spectrum and form the integrated spectrum, blue here, which can be approximated by, again, single zone model with the uniform density and uniform temperature, but outer radius of such zone should be smaller because the density of outer circular zone of the hot region are smaller. This is the same, but for the two temperature model of Shapiro, Erdely, and Tukolsky. And you see with the dependence on electron density, electron temperature, and optical depth. And again, we see that the produced integrated spectrum can be approximated by single temperature model with very nice agreement, except for very small energy of the spectrum. Now we decided to check what changed the spectrum if we include in the problem the source of external soft photon. In our model, it is most easy to make using the corona model. We just show that there is underlying surface below the hot layer of the disk, and this surface is emit black body photons with some temperature shown here. The temperature is much smaller than the temperature of high temperature plasma temperature of the high temperature hot plasma, which is 50 keV, and we see that spectrum changes drastically. Now the slope in the X-ray band, ultraviolet and X-ray band, is frequency in degree 2.2. It is not the spectrum which we observed in the low hard state of black holes. But when we decrease the temperature of such soft photon, we see that the intensity of this second component is decreased, but the slope again correspond to this slope of the spectrum. It does not change from the temperature of the photon. And when we take the photon with energy about 60-30 electron volt, the contribution from such photon to the resultant spectrum is negligible. These photons are not affect the spectrum at all. It is very important because it is show that the photon of some low energy and penetrating from outside to the hot zone does not affect the spectrum. And point with the below 50 electron volt, we see that the spectrum is not affected at all. This is a spectrum of intrinsic emission of high temperature plasma independent on the soft photon penetrating in it. And the other case is the green lines here show the black body spectrum of the underlying surface. It is shifted due to quantization, and we show here that we compute the same problem, but suggested that the optical depth of the layer is very small, 0.1, and we see that in this case the green and blue line are approximately the same. This is just because the quantization cannot change the spectrum. But again, we see that there is soft photons corresponding to the small temperature of the underlying surface, which does not affect the spectrum at all. We observe the intrinsic spectrum of the hot plasma. And it is very important. And it is necessary to say that our approach to describe the photons, external photons, which used as seed photons for quantization, really very huge. We have the surface, underlying surface under the whole hot region of the disk, which emit black body photons with very high temperature, and the number of photons is temperature in degree 3. It is huge. And in real situation, for example, in the truncated disk model, such number of photons are not penetrating the hot region. So we describe this introducing some fraction, suggesting that only some fraction of the underlying photon from underlying surface are penetrating the hot region. This is in percent relative to the black body number of photon described by Planck spectra. And we see that even we decrease the fraction of photon to 10 to minus 4 and 10 to minus 5, we still see some deviation in the X-ray spectrum from such photons. And again, the slope is about to photon index 2.2. Now we see what is changing when we underlying surface has temperature 500 electron volt. A fraction of photon penetrating the hot disk is 2%, and we changed the electron density of the hot layer of the corona, and we see that why we increase the density of the plasma, the spectrum change very strongly, and for density 10 to 19 and 10 to 20, we see that contribution of soft photon is negligible. We just observe the intrinsic spectrum of the high temperature plasma. And the slope is in the X-ray band is photon index 1.7, and in ultraviolet range it is 1.2. This is the same, but we assume here that the soft photons and external photons have temperature 10 electron volt and 1 electron volt, green lines. And we see that again there is some density where the contribution of soft photon affect the spectrum very strongly, and at higher density the contribution from such photons is negligible. Now we consider the case of small density, 10 to 14 centimeter in the cube. We see that it is easy to select some optical depth and temperature, and that the photon index of such plasma layer has slow photon index corresponding to the canonical black hole spectrum in the low state, and this is what this line is show this spectrum, but we see that for different parameters the slope of the spectrum can be very change very strongly. These cases correspond to the general approach that there is soft photon, seed photon, penetrating in the hot plasma from outside. But again, when we increase the density of the plasma in this layer, we see that the slope of the spectrum changed drastically. It is not correspond the value 1.66, which is typical for black holes. All the paper which were published for such comptonization of seed photon give incorrect result, because they are not taking into account the Bremsstrahlung photon, which also participate in comptonization. And this is very important. Several other results. This is show where amplification factor for luminosity of such a layer depending from temperature of the hot plasma and the optical depth of the plasma, of the layer in the vertical direction. And this is the same. This is intrinsic emission of the plasma layer, and we see what for typical parameter of the black holes with tau about 2, we see what the amplification factor is 6 to 4 for the typical temperatures from 16 to 100. This is this region. But if we include in comptonization the external photon, the photon with temperature 250 electron volt, we see that amplification is increased quickly, and this is fraction of such photon penetrating in the hot layer. There is main result of such of this part of the work, but now I will say few words. Few words about the optical emission. I already mentioned that the spectrum is extending to the optical infrared band with the same slope, and you see that in fact this is supported by observation. There is 3 X-ray nova observed by IBIS and SWIFT, and you see the photon power law spectrum measured in the X-ray band is being extended to the soft energy band. We see that this is excellently correspond to the observation. This is really fit was in the X-ray data, but here we just recalculated the column in hydrogen to the optical extinction and show that it is very good agreement with the observation. And even when the soft component is observed in the spectrum of the X-ray nova, we again see that the power law approximation of the spectrum to the optical and the infrared
we would like
band
to keep
is
hearing your talk for hours. It's so interesting, but try to reach a conclusion because
yes, just a minute. And you see that again this is power law extension of this spectrum, not the outer part of the disk. And you see light curves from the GX339 minus 4, and you see that the hard light curve and soft light curve are correlated, directly correlated. And this means that this emission is produced in the same band, in the same region where the hard X-ray are produced. And finally, I show you the picture of reconstructed from our computation with some arbitrary suggestion. And you see that there is spectrum, green line of the inner hot region. And there is the emission contribution from the outer cold disk for different suggestion about the external radius of this cold disk. And you see that in the optical and infrared band, there is significant contribution from the high temperature plasma. And the same in the case of the soft state of black hole, we see again that in this case it is necessary to add external photon to the hot region, and you see that the spectrum of hot region of the disk, which is small in this case, 5 Rg only, we see what this is spectrum of the hot region of the disk, and this is outer part or cold part of the external outer regions from the disk. And you see in this case, this contribute in the optical infrared band only the outer part. But in this region, the contribution from a hot region of the disk may be high. And this is the same if we can see, see the disk from large inclination, about 70 degrees.
Yes, it's very impressive.
This is conclusion. I already say this. There only may be necessary to add that all our computation have any controversial or questionable assumptions. This is just emission of the high temperature plasma of such density. No any suggestion. This is show that the emission of black hole is produced without external photon in the lowest hard state, but only intrinsic emission of high temperature plasma. And this is finally, thank you. Sorry for the delay.
Thank you so much. And very, 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 very impressive. Are there questions? Can you find the green book of Les Ouches for me in my lab? Are there questions? I'm surprised. These are at least 50 years of work by this group, at least. And I am extremely, extremely impressed because I was present back in 72 to, well, if there are no questions, I just make a few remarks. No, the book, the original. I have, okay, so it's all right. It's all right. And I want just to mention, this is a superb work. I am especially happy because very, very simply, apart the incredible amount of knowledge about spectra and variation, finally answer very simply, yes.
Yes. Yes, this is just emission from the hot plasma.
The high state and the low state being related to the two different rings of the Sunyaev computation. Very impressive. The low state and the high state, and the corresponding spectral changes. But I would like to just to tell to the audience this started in 1972, and I think I have to mention this historically, because at that time there was very difficult to come out of Soviet Union, and there was a person who managed to have permission to come in the West. And that man was Novikov. And Novikov took with him a manuscript. I think I have to say that because it's very important. He took with him a manuscript given him by Sunyaev. And he came to Les Houches, and you can see here the book, the original book, and he took this Sunyaev work and elaborate himself with Kip Thorne.
Yes.
And came an article in this book of Thorne and Novikov. Nobody in the scientific community mentioned that work any longer. And I think Sunyaev had the strength to develop in this group in Moscow the fantastic work to explain. If you try to, in the 72, in the literature, you find also discussion by Novikov and Thorne about high state and low state. I never understood this paper. But finally, we have in this fantastic paper the final result, where you see relating the high state and the low state to the Shakura-Sunyaev result. All this was bypassed in the Les Houches. You can look at the Les Houches because fortunately I was there speaking about another topic, but I testify this terrible happening of this thing that then nobody kept mentioning apart the proceeding of the book. And in the literature today, thanks to the fantastic work and constancy of 50 years of work, which are here presented by Grebenev, this is really and historical, and I would like him to show the difference of the high state and low state using the Sunyaev computation of the ring. Can you show us again that image in your work, Grebenev?
You mean
the high state and the low state? Yes.
this one?
No, before, where you see the ring, the ring around. No, where you see the high state and the low state, and the Sunyaev.
The really this what?
No,
This
previous in the early part. Anyway, we'll
this one.
No, it's in color, and here it is. Here, how beautiful. The the hot inner region, the hard state, and as soon as the ring of the Shakura-Sunyaev disk approach, you have the soft state and the hard state. This is finally clarified. This is a masterpiece. A masterpiece. Thank you anyway, and if there are no more questions, let me thank you very much for this beautiful presentation.
Thank you for inviting me.
To the next speaker.
Thank you.
I don't know how many of you are interested, but here we have the original 1972 paper with this paper I mentioned.
Okay, look.
Excuse me. Okay, let's go to the next speaker. It's good to put this in record, because Sunyaev always was too much of a gentleman, not making this explicit. But he did not explicit. He did with this work of 50 years. I hope you realize how important is this work. Okay, who is the next speaker?
Professor Ox is here.
Thank you again, Professor Grebenev.
Why is he not talking? Ну да, я понимаю. Последний.
Okay. Here is, if anybody is interested, this is the article which everybody interested should look. Not Sunyaev and his group, but Novikov and all. This is the article. Very few people. It's a long article, huge article, but you don't find citation in the literature. But it's good to have this, because this is really an important topic. And especially for our Soviet colleague, this is quite an adventure. It's a good occasion.
Non si apre.
Non sapevi la storia.
Posso reagire?
Ok, we can go?
Cosa succede?
Non si apre.
L'abbiamo già scaricato 2 volte dalla sua dove è mia. Volevo riavere, no, ma togliere quella. L'ho provato così, questo qua, ma non si apre. Non so cosa sia. Sì, is there. Apri.
The thing I said is also correct. Nobody in the literature after
Please make it full screen.
and whatever was published also people don't, because the work complete is the one presented today by Clever. It's fantastic. It's fantastic. It's a fantastic occasion.
You need a pointer?
No.
I don't. So these formats. These formats, this.
Yeah. Oh, please help me. Okay, it's okay.
It's okay.
Don't make me move the book because what is it? Yes. Okay, you don't take it away because it's 50 years I kept with me.
Okay, may I start?
Yes, absolutely.
So, ladies and gentlemen, here is the title. Let's proceed. Analysis, analysis of atomic experiments related to the distribution of the linear momentum in the ground state of hydrogen atoms revealed really huge discrepancies. The ratio of experimental and previous theoretical results was up to tens of thousands, as noted in paper in Journal Physics B. This was the motivation behind, the figure above shows the ratio of theoretical high-energy tail of linear momentum distribution to the experimental one, and it is seen that the relative discrepancy between theory and experiments can reach many orders of magnitude, 3 or 4 orders of magnitude. Namely, the experimental distribution falls off much, much slower than the theoretical one. And this was the motivation behind our theoretical results in that paper of 2001. The standard Dirac equation of quantum mechanics for hydrogen atoms has 2 analytical solutions. One is weakly singular at small r, and the second is more strongly singular at small r. For the ground state, the radial part of the coordinate wave function for the second solution is inversely proportional to r squared, and it is usually rejected because normalization integral diverges at r equals 0. However, the situation changes after allowing for the finite nuclear size and especially for the actual experimental charge distribution inside protons. So in that paper of 2001, we derived general class of potentials inside any nucleus, for which singular solution outside can be actually tailored together with derivative with the corresponding regular solution inside the nucleus at the boundary. In particular, this class of potentials include those that correspond to charge density distribution, CDD, that has flat top, no cusp, and then fall off to the periphery. Thus, the regular solution, in this figure, this CDD inside protons, experimental one, showed by the solid line. And it is seen that experimental CDD in protons has indeed the flat top and then falls off to the periphery. Therefore, the regular solution inside the proton can be actually tailored with singular solution outside the proton at the boundary. So in that paper of 2001, we derived analytically the corresponding wave function outside the proton. As a result, this huge multi-order discrepancy got completely eliminated. And the reason is, for the singular solution outside the proton, the much stronger rise of the coordinate wave function towards the proton at small r translates into much slower fall off of the wave function in the momentum representation for large momenta according to the properties of the Fourier transform. And the corresponding derivation used only the fact that in the ground state, the eigenvalue of operator k is -1, and therefore it's valid for any state of hydrogen atoms characterized by quantum number k equal -1. Those are the S states, states of zero orbital momentum. This second kind of hydrogen atoms having only the S states was later called second flavor of hydrogen atoms. Here is why. Both the regular and singular solution of the Dirac equation outside the proton correspond to the same energy. Since this means additional degeneracy, then according to the fundamental theorem of quantum mechanics, there should be an additional conserved quantity. In other words, hydrogen atoms have two flavors, differing by the eigenvalue of this additional new conserved quantity. Hydrogen atoms have flavor symmetry. Thus, the elimination of this long-standing huge multi-order discrepancy constituted what? The first experimental evidence of the existence of second flavor of hydrogen atoms, because no alternative explanation for this huge discrepancy was ever provided. By now, there are two additional experimental evidences from two different kinds of experiments, from electron impact excitation of hydrogen atoms, from electron impact excitation of hydrogen molecules. For all of them, the second flavor-based explanation removed large discrepancies, up to factor of 5, between experimental and previous theoretical results, while again, alternative explanations were never provided. So the second flavors seem to exist. For eliminating discrepancies between all of the above experimental results in the previous theories, the ratio of second flavor to usual hydrogen atoms in the experimental gases was estimated as 2 ± -1, and we will use this ratio later on. One of the most important applications of the second flavor is complete solution of the long-standing neutron lifetime puzzle. The lifetime of free neutrons was puzzling because in the beam experiments it was greater than in the trap experiments, well beyond the error margins. And it would have been explained by two-body decay into hydrogen atom plus antineutrino if the branching ratio compared to the usual three-body decay into free proton, free electron, and antineutrino would be about 1%. Because in the beam experiments, they count only the protons from three-body decay, and this missed the two-body decay. However, the previously known theoretical branching ratio for such two-body decay was 4 × 10⁻⁶. Alternatively, Fornell and Greenstein suggested that neutron might decay into some unspecified dark matter particle. However, in 2024, Jobbio et al. Performed experiment on hypothetical dark decay of helium-6, and from the experimental data, they deduced the upper limit of the branching ratio for neutron dark decay as 10⁻⁵, while 10⁻² is needed for reconciling tau trap and tau beam. In our papers of 24 and 25, we brought to the attention of the research community that with allowance for this second solution of the Dirac equation for hydrogen atoms, the theoretical branching ratio for the decay into hydrogen atom is increased by about 3,000 to become about 1%. And this is in the excellent agreement with experimental branching ratio required for reconciling tau trap and tau beam. So this solved the long-standing neutron lifetime puzzle completely. Below some details. The probability of neutron two-body decay is proportional to the square modulus of the electron wave function at the proton surface. And the second solution wave function rises towards the proton much faster than the first solution wave function. Therefore, the outcome of the two-body decay of neutron is with overwhelming probability the second flavor rather than the usual hydrogen atom. And I propose several designs of experiments that will constitute both the first experimental detection of the two-body decay of neutrons and the experimental confirmation that the two-body decay of neutrons produces overwhelmingly the second flavor. I presented these designs at all the major neutron research centers around the world, and now suggested breakthrough experiments are in preparation, in particular at the Los Alamos National Lab in the United States and at the Forschungszentrum Jülich in Germany. So, how the discovery of the second flavor can shed light on the possible nature of baryonic dark matter. The primary feature of the second flavor, since they have only the S states, then according to the well-known standard selection rules of quantum mechanics, the second flavor do not emit or absorb electromagnetic radiation. They remain dark. I can provide the details if you ask.
It's okay. Just mention because we have to have the coffee break.
I got 20 minutes slot. I'm not at fault that the previous speaker, you see. So the existence of second flavor explains the anomalous absorption in the 21 centimeter line from the early universe. There is perplexing observation by Baumann et al. Of the anomalous absorption in this line. The absorption signal was found to be 2 to 3 times stronger than predicted by the standard cosmology. And this indicated that the hydrogen gas temperature was significantly smaller than predicted by the standard cosmology. Barkana suggested that some unspecified dark matter particles provided additional cooling of the hydrogen gas by collisions. And by his estimates, the quantitative explanation required the mass of these unspecified dark matter particles to be of the order of baryons masses. And thereafter, McGaugh examined the result by Baumann et al. And Barkana came to the same conclusion. The explanation of anomalous absorption requires baryonic dark matter particles of the mass of the order of baryons masses. In our paper of 2020, we considered the following. What if these unspecified dark matter particles were the second flavor hydrogen atoms? And it was explained that in the course of the expansion of the universe, the second flavor decoupled from the cosmic microwave background due to having only the S states earlier than the usual hydrogen atom. And for this reason, their spin temperature controlling the absorption signal was smaller than for the usual hydrogen atoms. And this explained anomalous absorption qualitatively and quantitatively, and made the second flavor compelling candidate for the baryonic dark matter. Some details. The usual hydrogen atoms decouple from cosmic microwave background at the temperature proportional to the energy difference between first excited and ground states of hydrogen atoms. To visualize at temperature smaller than that, there are no more excited states of usual hydrogen atoms to be radiatively coupled to the ground state. The second flavor decouples much earlier. And this is because second flavor do not have at all any discrete states to be radiatively coupled to the ground state. If we denote by A of t the value of extension parameter of the universe, as the second flavor decouple from CMB, their kinetic gas temperature decrease inversely proportional to A squared, while the CMB temperature decrease slower, inversely proportional to A. Therefore, at the time when the usual hydrogen atoms decoupled, their kinetic gas temperature was greater than for the second flavor. So the second flavor did cool down the usual hydrogen gas by collisions. Now, cosmological formation of the surplus of second flavor compared to the usual hydrogen atoms from recombination epoch to the structure formation epoch. Both kinds of hydrogen atoms were formed at the end of recombination epoch. In other words, a pair of free proton and free electron can lose energy by emitting photon and end up as usual hydrogen atom or as a second flavor. For the usual H atoms, the direct recombination into ground state is ineffective for increasing the number of them, because the energy of emitted photon is sufficient to ionize nearby usual H atoms, so the number of them did not increase as a result. Therefore, the increase of number of usual H atom is two-step cascade process, first formation in the excited states, and then transition through with emission to the ground state with emission of corresponding photon that cannot ionize nearby H atom. In distinction, the second flavor, direct recombination in the ground state is effective because the photon emitted by a pair of free electron, free proton cannot ionize nearby second flavor because second flavor doesn't couple to electromagnetic radiation. Consequently, the rate of formation of second flavor in the ground state is slightly greater than the rate of formation of the usual H atoms in the ground state. And this created a small initial surplus of second flavor compared to the usual H atoms. During the dark ages, the share of each kind of H atoms remains frozen. At the beginning of gradual end of dark ages, the first stars are formed, and the structure formation started by using both kinds of H atoms with initial surplus of the second flavor. The UV light of the first stars gradually starts to ionize what? The usual H atoms, but not the second flavor. Therefore, ionization of the usual H atoms with subsequent partial recombination into both kinds of hydrogen atoms slightly increases the surplus of second flavor. Later, neutron stars form. Some neutron stars release neutrons into star atmospheres and interstellar medium. And those are old neutron stars and neutron stars whose mass becomes slightly less than 0.1 of the solar mass. So they release neutrons, they undergo 3-body and 2-body decay, and the 2-body decay produces overwhelmingly the second flavor. And this process further increases the surplus of second flavor. And there is observational evidence of this. It's presented in our paper in New Astronomy, and I can provide the details if you ask. So the subsequent structure formation, that is formation of the first galaxies, uses more of the second flavor than the usual H atoms. Thus, till the end of the structure formation, the halos of modern galaxies contain more of the second flavor than the usual H atoms. Now, there is also a second flavor of helium plus ions. The CDD inside alpha particles distribution shown in this figure has exactly the same shape as CDD inside protons. Therefore, the second solution of Dirac equation for helium plus ions is legitimate for all S states of these ions. There is second flavor of helium plus ions, abbreviated SF helium I. And there is experimental evidence of the existence of this. There is a large discrepancy between experimental and theoretical cross-sections of the excitation of state 2s of helium plus by electron impact. The theoretical cross-section was up to 2.4 times greater than the experimental cross-section measured by Dolder and Piart. And they measured this cross-section by applying electric field to mix state 2s with state 2p and then to observe Lyman alpha line. However, the second flavor helium I, the electric field cannot mix 2s with 2p because second flavor do not have p states. So therefore, by this technique, one significantly underestimates this cross-section if there was second flavor in the experimental gas. Again, no alternative explanation for this large discrepancy was ever provided. For eliminating this discrepancy, the ratio of second flavor helium to usual helium plus was estimated between 1.4 and 1.0, 1.4, and we will use this later. So the formation of galaxies used not only more of the second flavor hydrogen than usual H atoms, but also more of the second flavor helium plus than the usual helium plus. Some interesting ratios. Penton et al. Studied Lyman alpha forests from large-scale galactic filaments at 10 to the 4 Kelvin and deduced from observations the following ratio of luminous baryons to all baryons, 0.29. And in combination with observed astrophysical data from Planck corroboration, this translates into the following ratio of baryonic dark matter to the luminous matter, 2.2. By studying large-scale galactic filaments in regions of higher temperature, de Graaf et al. Deduced from observations the ratio of luminous baryons to all baryons 0.28, and this translates into ratio of second flavor helium plus to usual helium plus 2.3. Now we combine second flavor hydrogen, second flavor helium plus with respect to corresponding experimental and observational results. We find the following most probable value of the ratio for from atomic experiments, 1.8. And the following most probable value from astrophysical observations, 2.2. What does it mean? It means that the second flavor hydrogen plus second flavor helium plus most probably constitute about 80% of all baryonic dark matter in the current epoch. And cherry at the top, from observations of the bullet cluster, the ratio of dark matter self-interaction cross-section to the mass of dark matter particles is the following, and this condition is satisfied is that if dark matter is made of particles somewhat heavier than protons. And the mix in the proportion of abundances of hydrogen and helium second flavors yields the average mass of dark matter particles is 1.7 times the proton mass, in good agreement with the observations of the bullet cluster. So, in summary, the last slide, the most important points. First, the theory behind second flavor does not make any assumptions, does not change physical laws, and being based on the standard Dirac equation is within the standard model. Therefore, it is favored by the Occam-Razor principle, stating that when several theories compete, the one that makes least assumptions is the most probable to correspond to reality. Second, therefore, the existing second flavor hydrogen is more favorable than all exotic explanations of the anomalous 21 centimeter signal. Third, the exotic particles assumed as alternative were never discovered experimentally, while the existence of second flavor hydrogen is evidenced by 3 different types of atomic experiments, plus it's completely solved the long-standing puzzle of the Newton lifetime, and the existence of second flavor helium plus is evidenced by 1 atomic experiment. Fourth, the second flavors are dark because of the quantum selection rules for atom having only the S states, not because the word dark was fancifully attached to the words atoms or particles, as in many hypotheses beyond the standard model. I can provide the details if you ask. And the last point, from the comparison of the data from atomic experiments, from those atomic experiments, with corresponding astrophysical observations, followed that the second flavors of these two species most probably constitute about 80% of the baryonic dark matter. Thank you for your attention. Grazie per l'attenzione.
Okay, it's unfortunately terribly late, so probably if you have any questions, you can ask it during the coffee break. So now we have a coffee break, 10 minutes at most, so let's try to gain time for the program. Thank you. Dr. Usman, can you hear us?
Hi,
Hello?
yes, I can hear you.
Yes, hello. So we are resuming the session. Unfortunately, we are a little bit late, but please, you may
No,
start. So it's a pleasure to introduce Muhammad Usman. The talk is the Higgs vacuum and the cosmological constant. Please proceed.
hi everyone. Hello. Thank you for having me and giving me opportunity to present my work. This work I'm presenting is done by my PhD student Ittihad Hassan, and he'll be defending his PhD on the work very soon, hopefully. So let's start. I'll be talking about the accelerated expansion of the universe and how it can be explained in terms of the Higgs field
Can you speak
or more.
a little more loud or closer to the microphone, please?
Yeah, okay. Okay, so I'll be talking about the Higgs field or the scalar field in the context of the accelerated expansion of the universe. Uh, can you hear me clearly now?
Yeah, it's better. Yes.
Yeah. Okay. Okay. Very good. So so this is going to be the brief talk of my the brief plan of my talk. I'll be talking about the accelerated expansion of the universe, which we all know. A little bit of introduction about the quintessence field and how do it usually gets explained in the context of dark energy. Then we'll be talking about, we'll be studying the Heisenberg Langevin quantization of the quintessence field, and then we'll see some feature, which is the equation of one feature, essentially, which is the equation of state parameter and how it gives us something which is the dark energy, which is actually quintessence, and yes, the Higgs field, because the only scalar field which is present in the standard model of particle physics is Higgs. So we all know that the universe is accelerating with the expansion of the universe is accelerating, and there was the 2011 Nobel Prize because of this discovery. So this discovery, which led us to the identification that the universe is accelerating, universe is expanding with the acceleration. How do we explain it? We explain it usually with the cosmological constant. We introduce a term in the Einstein field equation, which is the third term in equation number 1, g mu nu lambda. And there lambda is the cosmological constant. This is very well known. We all know that the lambda is cosmological constant, which may be causing the accelerated expansion of the universe. But how does this lambda come to be this small, which can explain the current rate? And then where does it come from? The vacuum energy. So usually what physicists or cosmologists do is try to explain the dynamical feature of the quantum field or quintessence. How do we do this? We take a Lagrangian of a scalar field, which is given by equation number 2, and we find out its equation of state parameter. And the equation of state parameter is given by this equation number 3, which is essentially t minus v over t plus v. And if we look at this, and if we assume that which is very good assumption, that the field phi is spatially homogeneous and slowly rolling with time, then the first term is essentially negligible and the omega is minus 1. So this is closer to the cosmological constant. But this explanation is classical. The phi field, how does it behave quantum mechanically? We do not know, or we do not we do not see. We do not try to see because the calculation is very difficult. What I will try to do right in this presentation is show you some calculations of this of the quantization of this field phi, and try to explain that what the quantization lead us to. Okay, so what the omega, which is the equation of state parameter in the last equation, which is essentially for homogeneous field and slow roll in the slow roll approximation is approximately -1. We want it to be -1 or closer to -1 or at least less than -1/3 to explain the accelerated expansion of the universe, which is given or which can be proven from equation number 9. These equation number 8 and equation number 9 are the two Friedmann equations, very well known equations, and where omega effective essentially is the combination of all the components or all present in the universe. We know that the components in the universe, one is non-relativistic matter, the other one is relativistic matter. Then there may be other matter components which we call dark energy. And the dark matter component is essentially present in this matter form because the dark matter is non-relativistic, and thus the omega for non-relativistic matter is 0. So the first term in the equation number 10, the numerator first term in the equation number 10 is 0. Now let us see that how the field behaves quantum mechanically, that field phi. Now the quantization field in quantum field theory can be written as phi is equal to phi 0, which is vacuum expectation value or the 0-point energy, and then delta phi, which are the vacuum fluctuation. This is very this is something textbook material, right? So the dynamics of this field, this quantum field at Friedmann-Robertson-Walker universe, FLIW universe, can be evaluated, and we get equation number 12. Now I just have shown the equation number 12. What I will emphasize here that the calculation is slightly complex in my presentation. I will try to make it as easy as possible and try to show some results. But if someone wants, we can discuss how these equations come to be. Then the correlation function and the power spectrum is given by right after equation number 12, delta phi 0. Now we need to look at this correlation function and power spectrum. Now these correlation function and power spectrum have ultraviolet divergences, and because of these ultraviolet divergences, one do not care about how these fields behave quantum mechanically, because these have ultraviolet divergences. We need to have a very small vacuum expectation value, and thus one by hand assumes that the ultraviolet divergences somehow cancel out and we get 0. But how do we get it? We just have done that work. Okay, so let's go through this slide. Now we already have discussed that the correlation function and the power spectrum have ultraviolet divergence, and this is the problem for us. Now this can be avoided. These ultraviolet divergences can be avoided if we assume or if we approximate that the quintessence field can be approximated by a system of rigidly coupled harmonic oscillators. This is something which we know. Now, if the quintessence field is described by a system of rigidly coupled harmonic oscillators, then the coupling is definitely infinitely stiff. Thus, there is no elastic potential in it, and this leads that the gradient energy, especially gradient energy of the Hamiltonian, is essentially zero or can be neglected. Therefore, the quintessence field will be a discrete set of local oscillators, phi I. So the quintessence field will have a discrete set of oscillators phi 1, phi 2, phi 3 up to phi n, which may be infinite and may be finite. Now, if we assume that there is no non-rigid coupling, then we need to solve one by one, each harmonic oscillator one by one. And this is, of course, not possible because in the case of infinite harmonic oscillators, it's not possible. So, and one other thing or one other motivation to take rigidly coupling is that a single oscillator dynamic oscillator dynamics facilitates the application for open quantum system techniques such as Heisenberg-Langevin formulation, and this is what we are doing right now using. So let's go through Heisenberg-Langevin quantization for all for our quintessence field. Now, the dynamics we are on the second point. The dynamics of rigidly coupled damped oscillator in Heisenberg-Langevin approximation or approach is given by equation number 13, where F is the noise operator. Now, one can take the noise to be zero, one can take the noise to be non-zero. We will see that if we take noise to be zero, what happens, and if we take noise to be non-zero, what happens. Now, noise is essentially, one can consider that the noise which we are calling here is just the coupling of the quintessence field with the background, where this mu of t minus t prime, the term in the second term of the equation number 13 is the damping function.
You have 3 minutes
Now,
left.
Okay. So, cosmological implication tells us that equation 13 just goes to equation number 14, where mu of t minus t prime is equal to 3 delta of phi. Now, this equation 14 is the equation of dynamics for damped quintessence field. Because I have very less time, I would just go through quickly in the coming slides. Now, if we impose the cosmic acceleration condition such that m squared must be very, very less than Hubble scale than I squared, tells us that damping force must dominate the oscillatory action, then this means that phi dot. Now, if the damping force is very, very less than, phi double dot goes zero, and equation 14 may be written as equation 15, where we have introduced new parameters zeta, which is 2m square over 3h, and g, which is f over 3h. And in terms of ladder operator, one can define the field, which is very textbook material, and this gives a dot and a dot dot dagger as to be equation just before equation 17, where g, which is essentially the noise feature, is given by equation 17. Now, g of t, which is the operator, noise operator, is defined in terms of f, and they are just like the noise operators, which create and highlight noise states, like background states. The solution of Langevin equation after some complex calculations comes out to be equation 18 and equation 19. And now if we see equation 18, look at equation 18 and equation 19, and if we remove the noise, which is f and f dagger, take it to be zero, then a and a dagger, the commutation relation comes out to be exponential of minus beta t. And so this is just a damping factor. But if we include the noise, then a and a dagger commutator relation comes out to be 1. Hence, if we look at the Heisenberg uncertainty relation, and we try to not violate it, then the noise is we get the result that the noise is an important component. It means that the coupling of the quintessence field with the background is very important.
Can you please jump to
Now,
your conclusions because the time is out?
Yes, sure. Now, we just have concluded that the coupling of quintessence field with the background is very important. Now, to get something, some result which we can understand, let's calculate the equation of state parameter. Now, this is omega, which is p over rho, and if we calculate this in a discrete large number of approximation, then the omega comes out to be approximately -1. And this is interesting that in the open quantum system dynamics, when we have proven that the quintessence field also behaves like a cosmological constant or similar to cosmological constant. Why similar? Because we have done some approximation, and if we do not, if we try to solve the equations exactly, then it will definitely be different from the cosmological constant, but very slightly, like the dynamical feature. So we will have something where the equation of state parameter would be changing. Yeah. So that's my conclusion. Thank you so much.
Thank you very much. Thank you very much. Okay, unfortunately, we have no time for questions. Therefore, we should proceed with the next speaker.
Thank you for having me.
Thank you. So our next speaker is Professor Hochman, and his talk is about dynamical system approach to teleparallel cosmologies. So I can attach this somewhere. Okay, and switch.
Okay, thank you very much. So first of all, I would like to thank the organizers, in particular Remo Ruffini and Grigory Vereshchagin, for inviting me to give this talk here. My field of research is gravitational theory, so in particular modified theories of gravity. And I was asked in particular to give a talk on scalar torsion theories of gravity. And since the audience of this conference is very broad and very diverse, I would like to embed this a bit, this topic in the general topic of the conference, and in particular make connections to the cosmological aspects of these kind of theories. So I would like to focus in particular on the dynamical systems approach and the related topics here. So what is the motivation behind this? Well, we are motivated by the open questions in cosmology and gravity, in particular accelerating phases in the history of the universe, dark energy and inflation, also the relation between gravity, quantum theory and gauge theories. And if you look at these, at the standard model of cosmology, the so-called lambda CDM model, which is comprised of general relativity with the cosmological constant and cold dark matter, then we find that this is challenged both by theory and observations. So the general topic here I would like to discuss is the so-called teleparallel gravity. And the main difference from general relativity is that instead of the curvature of the Levi-Civita connection, which we use in general relativity, we use a different dynamical variable, which is the flat connection. And there are different flavors of this class of theories, either metric teleparallel gravity, where we have so-called torsion as the dynamical property of this connection. There is a symmetric teleparallel gravity where we have non-metricity instead. And if we have both of these quantities, then we speak of general teleparallel gravity. There are theories based on these connections which are equivalent to general relativity, but we can also find deviations. And then we have so-called modified theories, and there are many different classes of these theories. To mention just a few, there are the so-called f of t, f of q, and f of g theories, where we have a general function of the scalar which otherwise appears in the Lagrangian. We can have other scalars appearing in the Lagrangian, which are the most general Lagrangians that are quadratic in the torsional non-metricity, or we can couple scalar fields to the Taylor parallel geometry. Then we get to these scalar torsion, scalar non-metricity, or scalar Taylor parallel theories. And here I would like to look in particular at cosmology, where we use the cosmological symmetry in order to find the most general geometry. Then we get from the field equations, we can derive as modified set of Friedmann equations, and these we can then treat with the method of dynamical systems. So to give a general overview of these different classes of geometries that we have here. So in the setting of general relativity, we use the Riemannian geometry, which is in this sector here, where we have a Levi-Civita connection, which has vanishing torsion, vanishing non-metricity, and is characterized by curvature only. While here in the Taylor parallel case, we assume vanishing curvature. So R is equal to 0, and so we are in this circle here. And depending on whether we allow non-metricity or torsion to be non-zero or not, we are either in this metric Taylor parallel or Weizenberg geometry, the symmetry Taylor parallel, or the general Taylor parallel sector here. Now, if we apply the cosmological principle to these classes of geometries, then we get the following results. First of all, as you certainly know, if we apply it just to the metric geometry, the metric is still one variable in these classes of theories. We get the well-known Friedmann-Robertson-Walker metric, which we can write in this form here. I write it here as a time part and as a spatial part, dividing them apart like this, just to introduce here a bit the notation I will be using in the following. We have the Lebesgue function and the scale factor in here. The Lebesgue function we can usually set to 1 by making a particular choice of the time coordinate. If we apply the same to the connection, then we find that we can write the torsion and the non-metricity also as a set of functions. In particular, in the torsion, we have two different functions here. I've called them T1 and T2. And in non-metricity, we have three different functions, and this is due to the symmetry of these tensors. So in general, we have 5 different functions that describe these quantities, torsion and non-metricity. These functions are not completely free, because what I have not yet implemented here is the connection of vanishing curvature. So the connection that we employ here must have vanishing curvature. This gives us additional conditions, and I will come to these in a moment. First of all, let me just introduce a bit more of notation. I will define this time derivative here with respect to the conformal time, and introduce this conformal Hubble parameter, because it's most convenient to write the equations in conformal time. And then we can write down the condition of vanishing curvature in this form here. And this is a condition that has many components, many tensor components. And if we write this out in the cosmological symmetry, we get this system of equations here. And solving this system of equations is actually not very difficult. One finds that there are a few branches of solutions. Depends on whether we choose u equal to 0 or not 0. U basically is the spatial curvature parameter that comes from the metric. So this is this u squared is essentially describes the spatial curvature of the Friedmann-Robertson-Walker metric. If we solve this, then we find the following branches of solutions. We find one branch here where we have this T2 equal to 0. Here we have u squared is not equal to 0. And here is the second branch, which is also spatially curved. So these two are the spatially curved branches that we find. And we find 3 spatially flat branches, which appear by taking suitable limits for u going to 0 from these branches here. I'm not going into details how exactly we have to take these limits. Basically, the limits are taken by fixing particular combinations here being non-zero, and then taking the limit for u going to 0. This shows then that we get these different branches. And if we impose additional conditions, here non-metricity being equal to 0, then we see that there are only 3 of these solutions survive. These 2 here will not survive, because as you see here, there are certain conditions where we have the non-metricity being not equal to 0, but if we impose it to be equal to 0, then we get a restricted set of solutions. The same if we apply the torsion to be 0. Here we see in this branch we have explicitly torsion not equal to 0, so this one will not appear in here, and so we have only these ones here. And we can actually find that these are connected, these different branches here, that if we take the limit for non-metricity or torsion going to 0, then we will basically connect these different branches of solutions here. Now let's have a very short aside. The f of k, where k is either torsion, non-metricity, or the combination of both, can be connected to the corresponding scalar teleparallel theory. So if I start from this kind of theory here, I can introduce a Lagrange multiplier in order to enforce this condition here and write this then as a theory with two scalar fields here. This is totally equivalent action here just by introducing an extra variable for this field, or this variable k here. I set equal to a field phi and put this in here. And now I can integrate out, first of all, I can derive the constraint equations that I get from the variation with respect to the scalar fields. I can integrate this out, the psi, and then I get this kind of action here, and I get a scalar teleparallel theory that is completely equivalent to the original f of k theory in this case. In principle, I can also integrate out the other variable in case this f prime here is an invertible function. Let me not go so much into detail, but basically this is how you would write this kind of theory in this case. And here you see very familiar non-minimal scalar field coupling and a non-trivial scalar field potential, which is very close to the dynamics of scalar tensor theories. To go to one particular example, let's have a look at the f of t cosmology, in particular the spatially flat one. Spatially flat means that we have a spatially flat Robertson-Walker metric, which we can describe by this ansatz for a tetrad or Vierbein field. So we have this kind of metric here. And then the perfect fluid matter, as in the standard cosmological ansatz, takes just this form here. And what we get is then the cosmological field equations, which are basically a modification of the Friedmann equations, where now this function f, this free function f, here appears in these equations. If we put in here, in this case, as the matter, simply take a mixture of dust and radiation. So we have these energy densities and pressures here for the dust and for the radiation. We can introduce some different variables here, x being the ratio of radiation to the total energy density, and I'm introducing here a different function w to replace this function f, which I now write as a function of the Hubble parameter here. Then it turns out that this gives a very simple dynamical system, two-dimensional system, which takes this form here. This is basically just a continuity equation coming from the dust and radiation matter, and this is where the gravitational dynamics is then hidden in the dynamics of the Hubble parameter here. And just to give you an example here, for a particular function f, let's take the simple power law model here, which is one of the most studied models. And if we put this into the dynamical system, we get this function w here, and this gives us certain values of these parameters here. For example, if either alpha is positive and n is in this range, or alpha negative and n in this range here, then we get a dynamics that looks like this, where we have basically a Big Bang somewhere here, where we have the expansion rate going to infinity. Then we see that the expansion slows down, and in this case here settles to a finite value. So here we find then a fixed point of the system, which is a de Sitter fixed point, an attractive fixed point, which means we have a constant accelerating expansion, so like a constant dark energy essentially, or cosmological constant solution. Another example where I'm now looking at the so-called newer general relativity class of theories. This is a theory where we have torsion equal to 0 and non-metricity not equal to 0 instead. There are different classes of theories. Let me just give you one example, or actually, yeah, these examples here. We have different branches of solutions in this case, And here are the three branches that we have studied in this case by basically taking these cosmological branches that I've shown you on the previous slide and putting them into the dynamical field equations. I'm not going too much into detail what are the basics. So this is the theory where we have an action which is quadratic in non-metricity. And if we calculate here the dynamical systems model, we get three different solutions or three different classes of solutions for these different branches. Here's just one example. This epsilon here is a theory parameter that describes the deviation from general relativity. And for this particular value, we find a phase diagram that looks like this here. On this axis here, we see the, this is the Hubble parameter basically. And we see that here we find solutions where the Hubble parameter dynamically goes to 0. So here are some fixed points marked. And yeah, let me go a bit more through these different dynamics and show you the different fixed points. I will summarize them in a moment. So we see if we put in here different values of this epsilon parameter, we get very different cosmological dynamics here. And we see here, for example, this one has a repulsive fixed point here, where we see that this corresponds to some kind of Big Bang solution if we plug in here the values and calculate the values of the Hubble parameter. And then we see that the dynamics here evolve along these lines depending on what exactly are the initial conditions we put here. And we get then different attractor solutions. Again here, some expanding solution with a de Sitter-like fixed point. Yeah, here only the hemisphere of expanding universe is shown. There is, in principle, we can also show the dynamics for h smaller than 0. Yeah, let me come to the this example. Let me just skip. It looks very similar. Let me just come to the summary. So depending here on which values we choose for this parameter epsilon here, we get different solutions, either a bounce or a turnaround. And we find that here we get some asymptotically expanding solutions as well. So to summarize, these teleparallel theories allow very different classes of cosmological solutions with a different number of dynamical functions in the cosmological symmetry. We can solve them with the dynamical systems approach, and we can find some interesting solutions. In particular, we find dark energy attractors here. And one particular interesting aspect here is that dark energy here is dynamical, so we can address questions like the Hubble tension. And we're working on a complete classification of these here. And let me just show you as the last slide here my references and point out in particular the this review here by the Cosmoverse network, which is a very exhaustive review of these particular solutions, and this first review here on the teleparallel gravity. Okay, thank you for your attention.
Thank you very much. We have time for one short question, if there is any urgent. And well,
so of course I could not understand every detail of parameter, but from what we know of the universe, could you exclude some of your theories or your versions of teleparallel?
Yes, actually, quite a number of these parameter values are already excluded. So here I have shown only those parameter values which are in line with, for example, post-Newtonian limit within the solar system. So the post-Newtonian limit excludes already a very large class of theories. And here by the cosmological solutions, we can further exclude other parameters which, for example, do not yield a Big Bang, do not yield an accelerating expansion. So yes, there are quite a lot of parameters we can exclude.
thank you very much. Okay, let's thank the speaker again. Okay, our the next speaker is Bobir Toshmatov, black hole shadows as diagnostic of nonlinear electrodynamics.
Okay, can I start? Okay, thank you very much. Okay, good afternoon, everyone. I am Bobir Toshmatov. Before starting my talk, I want to thank the organizers for organizing this conference and making my attendance possible. Okay, now I am going to talk about this black hole shadows as diagnostics of nonlinear electrodynamics. Okay, now before starting or before presenting my main results, let's set the stage by introducing general information about this background and formalism in a couple of pages. For example, we start with the singularity problem. We know that black holes in general relativity actually suffers from the singularity. Like all the black holes, like a Kerr and Schwarzschild black holes, has a curved singularity at the center of the spacetime that cannot be explained by the general relativity itself. And at this singularity, actually, we have this. At this point, density, curvature, and gravitational field intensity strength becomes infinite. It means it cannot be explained by the physics laws for now. This is why actually we are expecting that this curvature singularity will be explained by the quantum gravity, but quantum gravity is not that yet developed yet to explain this all. This is why we have another method. Like now, in the next stage or the next way. Now we avoid the singularity in our theory. This actually, for the first time, to avoid this one, actually, Bardeen in 1968 proposed his model. This metric is still referred as a Bardeen black hole solution.
Can you remind us of this Bardeen work?
Sorry.
Remind us of the Bardeen.
Yes, I will show this one a bit later. Yes. Yep. And Bardeen proposed the model. Just he was proposing only the space-time metric. If the space-time metric is given in that form, actually it says that there is no curvature singularity. But he didn't show that it's a solution of the Einstein equations or not. But after 30 years, in 1997, Eloy Ayonbeyote and Alberto Garcia actually coupled this general relativity with nonlinear electrodynamics and showed that in particular choice of the Lagrangian density, one can obtain this Bardeen solution. And in terms of the magnetic, okay, we do here, actually, electrodynamics is given in this expression by varying this action Einstein equation max. It is given in the last equation. Now, unified metric proposed by this Fan and Wang. And here, this, and if we insert these two Einstein equations, we get for our function. This Lagrangian has been chosen. Actually, the motivation was before that they were like regular black hole solutions were already known. Most prominent and hybrid solutions. Now, by choosing this Lagrangian density, they unified this to more single form, even generalized this. Here, if the new two part in and well, new really this all three analyze this of the dynamics in this weak field limit. Regime is we are having this Schwarzschild plus electromagnetic field related term, which is again like 1 over r. It's falling off as. But in the case of Bardi, it's like magnetic field. In the case of Bardi, William one, because in the weak field, both density, the metric function is also like behaving like a linear electrodynamics. This is what we call hybrid cases like this situation, because the function of the Bardian one in the weak field limit is behaving like 1 over r cubed, like electromagnetic field related term is falling off as 1 over r. Or it's like a falling off. You see here, cases, this with like a tending to the Maxwell electrodynamics. You know that electrodynamics actually dynamics is verified by why that in at least in the weak field limit. From this point, and hybrid solutions are suffering. Actually, this is why we call them. But it has a correct limit. This test actually passes. Now, I think that's in the structural black hole, we have only one horizon, it's constant, 2m. But in the case of, if you put the charge to this black hole, in that case, this black hole starts to have these 2 horizons. One of them is inner, next one is outer. When we increase the charge, these 2 horizons, outer one is shrinking, inner one is reach the extremal bottom. Then these 2 horizons merge, and beyond, it means it becomes, for example, like Riemann-Nernstrom solution, it becomes simply Riemann-Nernstrom naked singularity. But in the case of regular black holes, we say naked singularity because there is no singularity at the center. We call this one as a no horizon or horizonless spacetime, no object. We call it simply this one, right? See that the same things are happening, that we are showing only the outer horizon because inner horizon is not really much important for the external observer. We only care about the outer one, right? This is why, as you see, when the charge is equal to 0, we are having the all are at 2. It's really perfectly compatible with the Schwarzschild one. When we increase the charge, again, as we say, outer horizon, at some point they vanish. I mean that the curves are corresponding to this like an extremal. That just is Maxwellian one. Blue one is Bardian. Nernstrom solution as a result. Here, I can have a bit black hole is the widest one. I mean, it's simply possible range it has. This one first. Starting studying the photon motion, we need to take the account. Like standard job. A photon follows the null geodesics of the spacetime. Dynamics is not so. Effective spacetime, not by the null geodesics of the original spacetime, but effective spacetime. Effective spacetime is constructed by this about the first formula. Okay, and it takes this form. As you see here, the effective spacetime this wall like a model. Like a first density divided f is equal to 1. The original metric. Dynamics, for example, in Maxwell dynamics, null geodesics of the effective geometry, original geometry, again. Okay, now let's follow one space-time is given. I want to calculate the one. Space-time, right? In that case, I go on sphere following graph for this again 4 including the right one. This all radius also decreases. Now, if I know that fact that I must take obtain the another the right analog. In that case, you see, initially they behave the same, like building the value, and after that, it's again almost like a linearly, it's increasing. It means for any value of the charge, it does not vanish. It means it always, this regular, if the associated with the non-linear dynamics, it always has the photon sphere. Yeah. Now, this to the shadow. Shadow is, if you do not know the photon sphere, you can calculate the shadow, right? This is why now shadow is calculated by this formula. If you do not know the shadow, the photon sphere, it is, I mean, as I said, if you know, if you, for example, calculate the photon sphere by using the circular geodesics wrongly, for example, in that case, your shadow radius becomes wrong. This is why, let's do this here. We have the radius. First, okay, now, as we said at the beginning, when the charge is equal to 0, all the spectrum are the Maxwellian, all are. As a result, mathematically, we should expect that every result times the charge is equal to 0 must reduce the result of the special one. But following calculations for the shadow calculations, when we do that, when the charge is equal to 0, Bardeen and hybrid solutions are not coming back to the shadow of the one. It means we have this mathematical what we frequency we are having, like a conflict we are having, contradiction, and it shows that actually the shadow, by calculating the shadow, show that initially, like a field limit problem we had, right? Can actually show that one. Okay, now what happens if get scalar perturbations in that case, we know high diagonal. Carlos and his colleagues has shown that this can be calculated in the real applied by angular velocity of the circular energy. On the image, we have over 1 plus 1 over 2 exponent. Now we want to this again this three or like black holes. What we have calculations have shown that here scalar and gravitational perturbations actually produce the same like a Quasimodo frequency as stated by the Cardoza and his colleagues, but for the electromagnetic perturbation it's not so. In the electromagnetic perturbations, instead of the circular geodesics, you need to use the photons. Circular geodesics is directly associated with the photons. Not, I mean the electromagnetic perturbations is directly associated with the photon sphere, not with the circular geodesics. Okay. In our previous paper, actually, we have shown that this effective geometry, when I showed this, like a Novello and other authors actually produced, was actually derived by using the geometrical optics approximation to the Maxwell equation, actually. But if we apply this electromagnetic perturbations to this regular black holes again, we can also generate this effective geometry by by using the effective, by using the electromagnetic perturbation as well. Okay, now let's check this. Circular geodesics, like the angular velocity of the circular geodesics for this electromagnetic and scalar perturbations. We have Oh, as you see, the q is equal to 0. The most important part is q is equal to 0 case for us. Now, q is equal to 0, both are coming to the same point. It means everything's fine. But when we consider the electromagnetic perturbations, or like a photon sphere, we are having again this discrepancy. When the q is equal to 0, again, Bardeen and Haber solutions are not coming back to that point again. I mean, not coming back to the value of the Schwarzschild one. This is why, again, we can say that here, after that, again, we start with this one. But after further analysis, we have found that actually the shadow radius is just a reciprocal or inverse of this angular velocity of the photon sphere. And in terms of that one, we can write the atonal frequency in this form, like in general form. And okay, let me finish it. Okay, now let me conclude this. Actually, we have shown that the shadows and atonal quasi-normal modes are powerful tools to test the physical viability of the nonlinear electrodynamics. Next one, only the Maxwellian family correctly recovers the standard physics in the weak field limit. And the Bardeen and Haber regular black hole models contains a hidden Lagrangian flow that's exposed by the light that travels around them. Thank you.
Thank you very much, Babir. Listening to the speaker. Unfortunately, I don't think we have any questions because we're really running very late, but I think you can ask questions after the session. Okay, thank you very much. Okay. So the next talk is by Kirill Zhirkov. You are here, okay. Can you put your microphone here?
Раз.
Okay. Okay.
Good afternoon, ladies and gentlemen. My name is Kirill Zhirkov from Steinberg Astronomical Institute and part of the Master Collaboration, which is a network of optical robotic telescopes. And I'm going to present our results on the observation of high-energy neutrino events, which were detected by IceCube Neutrino Observatory. This is Master Collaboration. Until relatively recent times, the only objects which were available for study for neutrino astronomy were solar neutrinos and neutrinos from the famous supernova of 1987. However, in 2013, Neutrino Observatory IceCube, located at the South Pole, reported on the detection of astrophysical neutrinos with energies of hundreds of tera electron volts and more. Unfortunately, due to the poor angular resolution of IceCube, on the order of 1 arc degree, their source was unknown. Majority of models regarding production of high-energy neutrinos revolve around active galactic nuclei, specifically blazars whose powerful jets are capable of producing neutrinos with sufficient energies. The first source of high-energy neutrinos was found in 2017. That was flaring blazar TXS 0506 pass 056, as well as the neutrino event IceCube 170922A. The blazar was found to be flaring in every electromagnetic band, from radio to high energy gamma ray. And the variability in high energy gamma ray was enough to reject the chance coincidence on the level of 3 sigma. Since 2017, there were found several other correlations, such as correlation between tidal disruption events, radio blazars, general correlation of blazars and neutrino events. However, they either mostly utilize radio data or are based on general statistical correlations between catalogs. So it's hard to use them to find sources immediately after the neutrino event, such as minutes or hours after it. To do that, you need to find correlations between activity of blazars immediately after the neutrino event and neutrino event itself. That is one of the advantages of the Master Global Robotic Network. That is a network of 10 robotic telescopes located all around the world, in Argentina, Mexico, South Africa, Canary Islands, and Russia. It is a network of 40 centimeter paired robotic telescopes with a field of view 2 by 2 degrees, and are capable of slewing on any point of the sky within a minute. The master telescopes mostly observe short-lasting, powerful astronomical phenomena such as GRBs, high-energy neutrino events, and fast radio bursts sometimes. Master telescopes observed this blazar, TXS of 506 plus 056, 2 minutes after the neutrino event. And it was found that blazar was in a dim state immediately after the neutrino event and brightened by 2 times to 2 hours after the event. Here you can see the light curve of this blazar, points a week before the event, immediately after the event, and 2 hours after it. As you can see, the pretty peculiar phenomena. Amplitude of this brightening is 0.81 magnitude. Second potential source of high-energy neutrinos is PKS 0735 plus 178. It was the first neutrino event which was detected by several neutrino observatories. Baksan, Underground Scintillating Telescope, Baikal GVD, ARCA, part of KM3net, and IceCube. This blazar was found to be flaring in every electromagnetic band, just as a TXS. And the first message on the potential source was made by master collaboration. Here you can see light curve of this blazar made by master telescopes and ASASSN. Red line points on the detection of IceCube and Baikal GVD. Orange line is BUST, and brown is, well, pink, ARCA. As you can see, before the neutrino event, blazar started flaring, then suddenly faded, stayed on this level for 3 days, and then brightened again, just as TXS. Magnitude of this fading is 0.21 magnitude. Intrigued by these 2 sources, we decided to search in our archival data for more blazars which show similar behavior. Since 2016 to the 15th of September 2023, IceCube published 129 public alerts. We used in GCN Global Gamma Ray Center Network. As a criteria for blazars, as a catalog of blazars, we used Roma BZ-CAT, and criteria for blazars, we decided to use Gaia data release 3, which has probability of galaxy-like nature. We used that probability is less than 0.2. We searched for blazars in a 90% localization field, with its dimensions increased 2 times. As a result, we imaged 161 blazars, of which 52 were visible. And we decided to call a source candidate if we find any optical activity. However, there is a question: what do we call optical activity of a blazar? For that, we decided to use a background sample of blazars which were not connected to neutrino events at all. For that, we used data of Catalina Sky Survey, which is an optical survey which observed sky from declination -30 to +65, excluding galactic plane. Typical upper limit of 19, 20 magnitude. And it collected data from 2005 to 2014. We also decided to estimate color of Gaia minus CSS. We used data of Gaia to calibrate our photometry. And we found that it was pretty close to 0. Well, for the background sample, we used every blazar from Roma BZ-CAT, which was imaged by CSS, and which use the same selection criteria. magnitudes were corrected for galactic extinction. And we used one random data point from each of the 1,744 blazars that were imaged by CSS. Here you can see a distribution of blazars based on deviation from the average magnitude. This is master data, this is CSS sample. As you can see, pretty symmetric. Here you can see the distribution by magnitude, master data, CSS data. As you can see, samples aren't really similar. Master data doesn't really see a lot of dim blazars compared to CSS. Well, judging on these samples, we decided to call optical activity if blazar after the neutrino event is either bright, approximately 15 magnitude, or it is flaring. Magnitude during the event minus average magnitude is less than -1. Approximately, yeah? 5 minutes? I'm close. Well, to estimate significance level of the difference between samples, we used the test. And it's a pretty simple test, ratio of a difference between a random value minus mathematical expectation divided by standard deviation. And we also corrected our selection bias, such as dim blazars that went visible in the master sample. For that, we considering that magnitude distribution for both samples is pretty similar until 17 magnitude, we corrected the CSS sample based on that. Number of blazars brighter than 17 is 20 out of 52 for master, 334 out of 4 CSS. Then corrected CSS sample should be about 894 blazars. And since the samples aren't infinitely large, the test is written differently, if anyone wants to read. We found that maximum significance levels were found under the following values. Blazar is brighter than 15.25 magnitude, and the flare amplitude is larger than 0.9 magnitude. Blazars in master sample which are satisfying either of the conditions is 12. 7 for the first condition, 6 for the second. In the CSS sample, it's 64. 44 for the first, 24 for the second. Significance level for both conditions is 0.8 sigma. On the first condition, 2.64. On the second, 3.53. Probability of the first condition in master sample is 0.13. For CSS, 0.05. Second condition, 0.12. And 0.03 in CSS. Here you can see the table with found source candidates. IceCube event, blazar, magnitude during the event, and deviation of the magnitude from the average level. As you can see, there are 2 events with more than 1 source candidate, which can be pretty easily explained by either a chance coincidence or the intensifying of the neutrino flux from those 2 blazars, considering that IceCube can't really separate the 2 sources due to poor angular resolution. Well, we found 2 criteria for the source candidates to be a neutrino source. This blazar is either brighter than 15.25, corrected for galactic extinction, or the optical flare is brighter than 0.9 magnitude. Significance level for each criteria is 2.64 sigma and 3.53. And this selection criteria can explain about 10% of neutrino events, which is pretty close to IceCube data. And chance for a blazar to be a source, according to criteria, is 63% and 77%. Thank you for your attention.
Thank you very much. Thank you. If there is one short question, please. Okay.
Thank you for your talk. Very interesting, curious result. Just a brief question. Have you tried to other types of sources, not only blazar? Because in IceCube, they also have a catalog of these AGNs that are
we haven't
not active.
We haven't really tried other sources since it takes a lot of time to scour archival data. For now, it's just Blazers. But we are. We will check other sources, mostly AGNs. That's all I can say.
Okay, thank you. Thank you for your talk. Thank you very much. And okay, let's come to the last talk of our session. This one. Pointer. So Andrzej Radosz. So we are going to hear him on spontaneous.
Is it okay? Can you
Yeah. Spontaneous pair creation in selected cosmological models.
Can you hear me? I'm sorry.
Okay. Yeah. Just hit this. Okay.
Yep. Okay.
What? You change the slides.
What about the pointer?
Yeah.
Yes.
Okay.
Thank you very much.
Please.
Thank you. Let me first thank to the organizers for giving me a chance to be here. I asked the last day of registration, 15th of June. Thank you very much. So I'm going to speak about particle production in expanding universe, but actually speaking about the particle production in cosmological models. Excuse me. Not here. No. Okay. Yeah, yes. Hopefully I know. So if you consider scalar field in Minkowski spacetime, then after quantization you can get a system of harmonic oscillators non-interacting. When you consider dynamic spacetime, then quantizing scalar field, you can get something different. Then you can get the situation when the particles are produced if the space-time is homogeneous, dynamically homogeneous, then the particles are produced in pairs, and the meaning is that energy is not conserved, but momentum is conserved. So considering different models, you may come to different situations, but the particles are produced if the space-time is dynamic. The story begins about particle production in expanding universe in mid-30s with idea first expressed by Erwin Schrödinger. Then real research started in second half of 60s of the last century from the studies by Leonard Parker, and then a variety of physicists contributed, among them Zeldovich, who in the 70s contributed heavily. Heavily means was described in one of the review papers in such a phrase as you can see here. And let me say a few words about Zeldovich. I haven't met him myself, but being in the Soviet Union at that time, long time ago in Dubna as a condensed matter physicist, I heard a couple of stories about his very sharp and deep intuition. And once I was told about the situation when Lwogunov, who is favorite of communist authorities at that time, was going to give a seminar on the general relativity, and Zeldovich definitely was not going to participate in this seminar and was about to leave before the starting point and made a remark about fundamentals of general relativity. And then Lwogunov responded saying something like this: Soviet physicists are having their own meaning of general relativity. And then Zeldovich turned and said a phrase. There are some people who can understand Russian in this. How many? How many of people could, well, yeah. So let me say this phrase in Russian, can I? Excuse me?
We could also forget about Lugonov, but anyway.
Yes, I will tell you what Zeldovich said that time, I heard. He said, using the phrase from Wysotsky song, he said, "Ty z inna grubość narywaешься," he said. In English, it sounds like, "Take care, otherwise I would be very rude," he said. And the other situation was that Zeldovich, was visited by his American friend, and this friend brought him a nice souvenir. It was Parker pen. And then Zeldovich came to the wall. In the Soviet Union, the walls were having the ears, and he said very loudly, "Unfortunately, I couldn't accept this souvenir," he said. So that was, what I'm going to speak about is about production of the particle. I mean, scalar field is quantized in the standard way. What means we are formulating scalar field in the background, and the background is dynamic space-time, and you are writing the Klein-Gordon equations, and then expanding a field, and then quantizing in the usual manner. And the example would be the conformal flat space-time, but it would be also different space-times. Actually speaking, the interior of the black hole may be regarded as a cosmological model, but this cosmological model is anisotropic, so the particles are not satisfying this momentum conservation. So if you think in terms of unitary evolution, then you may calculate Hamiltonian, and then you can see then you can see the set of the part corresponding to the set of harmonic oscillators, and then you can see this part corresponding to the creation of particles in pairs, and of course annihilation because the Hamiltonian must be Hermitian, and as you can see, they are produced in pairs with momentum conserved, and annihilated in pairs and momentum conserved. And if you write in such a way, excuse me, just let me, if you write in, sorry. Yeah. If you write equation of motion in Heisenberg picture, then the equation of motion is for no, that is something I can see. Oh, yeah, okay. I'm sorry. Silly me. Stupid. Then you can see the Heisenberg picture, and if you are able to solve this equation, actually speaking, the equation tells you that those operators evolving in time are described like a pseudo-rotation in two-branch space, subspace, k and minus k, okay? And then this problem of this operator equation may be formulated as a problem of differential equations for coefficients. Those coefficients, alpha and beta, turns out to be Bogoliubov's coefficients. So you can write differential equations for those coefficients. And if you are able to solve this equation, then you can describe the dynamics. And you can ask different questions. One of the questions is as follows. There is no unique vacuum state, but you can make you can take a vacuum state at some instant, defining vacuum state in a usual manner, and to ask how that vacuum state would evolve. And if you take a vacuum state defined in the usual manner, then you can ask for the for the unitary evolution of that state, and you are finding that the particles are born, are produced from nothing. That's the evolution of the vacuum state. The particles are produced. But you may ask the other questions. Is it possible that if the initial state is not vacuum state, could it be the situation that the number of particles in this during this evolution is diminishing? Or you can ask other questions. In other words, the question is as follows. If you know the evolution of the operators, if you know the picture, Heisenberg picture, what would be Schrödinger's picture? So how the state would evolve? You may ask this question. In general, it would be very naive to expect that the solution, the answer is achievable. But in this case, the situation is specific. And I will tell you about this specific feature, about the other side of evolution of the system. The other side is evolution of the arbitrary state. In this case, knowing the evolution of the annihilation and creation operators, what about the evolution of the state? Arbitrary state. So let us start from the vacuum state, as defined before, how that state evolves. That is temporal evolution, that is this unitary picture, and evolution is described by this operator. And you are getting the answer, and I will tell you how the answer is achieved soon. But the point is, excuse me, the point is that you will see how the particles are born in pairs, okay? So let me give you the flavor of these calculations. So we are looking for the, well, describing the state, you are developing the arbitrary state in the set of Fock states. So the coefficients are this kind of scalar products. And this, the meaning is that in K branch you have nk particles. And if you are rewriting this in that way, then you are making some calculations. As you can see here, the calculation is as follows. That is the elementary thing. What does it mean that you've got harmonic oscillator with an particles or an excited state? The meaning is as follows. And then you are applying this, well, you are applying the fact that operators are evolving in that way, and then you are claiming you know that what is the vacuum state. AK applied to vacuum state gives you 0, so only this term survives. Only this term survives, and I'm sorry, then you are making some more calculations. Finally, you are finding that such a state, this is that initial state, such a state is non-zero only if in kth and minus kth branch, the number of the particles is the same. And you are getting some coefficient. That is the outcome of some manipulations. And the meaning is, as I said, the number of particles in K and minus K branch is the same. That is the way how it works. So that is the I'm sorry. So now you can see how do we know those coefficients. They are non-zero only in this condition. And you can see what is the coefficient. The coefficient looks like this times this term. From normalization, you are getting this. And from the fact that these coefficients are Bogorov coefficients, so it means modulo square alpha minus modulo square beta is 1. 5 minutes, or that's it? That's it, you said? Sorry? 1 minute or no? 1 minute. Thank you very much. So that is the evolution of the vacuum state. And the general question is, what is the evolution of arbitrary state? So if you use the teaspoon, then you can eat a lot. So the next step is one particle state, and the following step is arbitrary number state, and then so on. So one particle state, you can follow the calculations, you are getting something, and the problem starts when you are having particles in the K and minus K branches. And then there is the problem, but the problem would be overcome. The problem would be overcome if you are having one particle in K and minus K, and then you are getting the flavor how it works. What about the combinatorics? And what about the other? So I'm not going to give you the final answer. I'm going to say that we are getting the road to the end. So that is how the system evolves in the Schrödinger's picture when you know the Heisenberg picture of the operators, what means the temporal evolution of the annihilation and creation operators. And then you may start asking the questions about the evolution of the system in this formulation, when the particles are born in pairs. Thank you very much.
Okay, thank you very much. Any questions? Last speaker. Well, apparently everybody's tired. Thank you for coming to this intense session, and we of course continue tomorrow, but I remind you that tonight we have a dinner at 8 o'clock, and you who participate, you receive all the details. So thank you again, and see you tomorrow. Thank you very much. Okay.